Hello everybody, thanks for tuning in today. We're going to be talking a little bit today about some C++ and DirectX game development. My name is Mickey McDonald. I'm an indie game developer and Microsoft technological evangelist. I spend most of my days making up game templates and examples to show you guys. I've worked with a lot of different platforms, including Windows 8, 8.1, the Xbox 360, Windows Phone. I get the chance to speak at a lot of industry events, so I get to share the knowledge that way. And that's a little bit about me. You can follow me at Twitter at ScruffyFern. Check the spelling on that. I spell fern a little differently than most people do. With me today, I've got Brian.
Hey everybody. Spend most of my time programming to all hours of the night. I'm a software engineer and game developer. I'm also an instructor at Trias College in Canada. And basically just spend my time making video games, playing video games, researching as much as possible. Research is important. And I've worked with most of the major publishers over my 12 years in the gaming industry so far. I've worked with Activision, Blizzard, Sega, THQ, Microsoft, all kinds of companies. And I spend most of my time instructing nowadays because it's fun to just work with other students, work with younger guys looking to get into the industry and sort of bring up the next generation of game developers. So that's why I moved into that and sort of out of the AAA industry, and that's what I spend most of my time doing nowadays. So today what we're going to do, we're going to go over C++, DirectX, really from the bare bones. We're going to break it down as much as possible, try to give you an easy way into going down this kind of development path. We're going to look at a little introduction first, getting started. It's a little early in the morning for some hardcore coding, so we're going to talk a little bit more about what you need to get started, the process you go through, and then we're going to move to what DirectX can do and creating the main game loop, very important part of your game, obviously. It runs everything. Then we'll move on to other topics such as creating, texturing, and moving objects, talking about state machines, how to build your game in a nice, easy-to-control manner to know where it is and what stage it's at all the way through. Capturing user input will be another module we'll do. Obviously very important. We're going to look at a couple of different devices for capturing input, not just mouse and keyboard or touch displays. We're also going to get the controller in there and sort of bring it all together and show you how to manage all of those inputs sort of in a friendly game manner. And then we're going to move on to physics and collision detection and just explore a couple little topics in there, as well as then moving on to AI and some other features we need in our game. So from that, that'll be all we're pretty much going to cover today, and why not get started? So the target audience for today, you want to talk about that?
Yeah, sure. So we're basically trying to target this towards the students, the beginners, the indie developers, right? Those with a desire to really, expand their knowledge of game development and learn the ins and outs of DirectX. We're not expecting you to know too much about DirectX. We're expecting you to have a little bit of basic knowledge around C++ and a little bit about Visual Studio. That'll definitely help. We're also expecting you've had a little bit of experience with Windows 8 and 8.1. You understand the interface and some of the features available to you that way. We also expect you to have a little bit of linear algebra and 3D coordinate systems knowledge. That's going to go a long way when you're working with DirectX, that's for sure. The requirements is obviously you got to have that drive to make your own game. And we suggest you have some snacks and beverages on hand. This is going to be a little bit of time, so you want to make sure you have something to munch on while we're chatting with you.
All right, so what about the MBA community? I mean, a lot of people already know.
I'm sure a lot of you guys already know because you're here watching us. But if you haven't already, make sure you join up with the MBA community. It's tailored for ID pros and developers like us. We've got over 1 million registers already, which is pretty impressive. It's up to date with the newest content and everything, so you can definitely check that out. While you're watching us, you're actually going to earn some points. You get 50 MBA points for watching us. The MBA voucher code's right there. It's Intro DirectX. So go ahead, click that link if you get the chance, and sign up that way.
All right, so that brings us into our first module, Introduction and Getting Started. And sort of what we're going to cover in this module this morning. We're going to look at the goals for the day. We're going to prepare to make a game, We're going to talk about how to sort of know your audience, make sure you have that clear understanding of who you want this game to be for and who you want to bring it to in the audience or sell it to and things like that. And then we're going to talk about picking the right tools for that kind of job, what you need to consider, what best fits the gameplay you're going to be working on or the system you want to roll it out for, and so on. And then we're going to move into really what you need to start this demo as well as other things like that. And then verifying that we have everything running, we're ready to go, and we're going to take a quick look at a couple of new features in Visual Studio's 2013 that'll help you do this development process. All right, so first off, the goals for the day. We're going to examine the process of preparing to make that game. We're going to create a C++ game for Windows Store using DirectX. That's our major goal for today, pretty much. And we're going to discuss common structures and patterns, implementations that are used when developing video games across the industry, whether you're indie or AAA. A lot of these things are sort of the backbone of how we build games, how we put it together. So we're going to look at those. And they'll pop up throughout all of the different sections. There's not just one section on that. And we're going to hopefully increase everybody's technical knowledge about threads, state machines, polymorphism, inheritance, other topics that are going to, again, just pop up throughout the day. And then at the end, we're going to have a couple of resources for you to continue your learning, somewhere to step on from here, move on with this game, bulk it out a little more, add your own flair to it, your own touch to it, experiment with it, and things like that. And ultimately, hopefully, have some fun while we're at it. So the preparing to make a game stage, early on, there's really two main approaches most people will work with. Either they have this great idea, they've been mulling it around in their head for years. They finally have all the tools at their disposal. They've got some time. They're going to detail it, lay it all out, write it all out in paper, prototype it, and then really start to get into trying to create it. And that's fine. That's a great way to do it, especially when you know exactly what you want to do. Other times, the other approach usually is that you just want to do something. I don't know, you have a week off, Christmas vacation's coming up for a lot of people, those kinds of things. We want to pick a main mechanic and a theme usually, and then develop around that, experiment with it, play with it a little, and just sort of see what comes out of that idea, that one little idea you started with, and just go wherever it takes you. That can really move you into an area of game development where it doesn't feel as structured. It's just everything's flowing. You take the path of least resistance. Some people call it extreme programming. They don't worry about tomorrow or the next day or what they're going to have to deal with. They just take the simplest and easiest approach, hammer it out now, see where it goes. If you like it, you keep it. If you don't, you cut it and you keep going on. And that can make great, fun, entertaining little games that are perfectly suitable to roll out. There are obviously some other approaches out there. You could do a satire of other games, well-known ones, make fun of them, make fun of whole genres. Sort of, we see that a lot lately going into different indie markets, and that people are just like, oh, I want to make a spoof of all the horror games that I used to know and love, or all the platformer games, and so on. You could revive an old genre that's being neglected right now. That's another great approach. There's been a lot of popular platformers come back in. The 8-bit era is sort of coming in, so instead of really bringing back a genre, they're just making all the art in all the genres where we wouldn't have seen 8-bit, now 8-bit. I'm sure you can think of a ton of games that fit that profile. And another approach is just to learn from others, what they've done well, clean up what they did poorly, and move on from there. That's a great way for people to do case studies. That's effectively what you're doing. You just pick a game, maybe in a genre you don't normally play or you haven't programmed for before, just to give yourself some more breadth in what you can do. You take it, you analyze it, try to pick out what went wrong, what was great, try to keep those, try to fill in any holes that you removed from taking out the parts that didn't work so well. And then finally, you could always just make a story and art game. People that usually do that want to show off their art skills or their creativity or something like that, and it's fine. We haven't seen them really take off all that much, but it serves a purpose. Some people really love them. It's more of a niche market, but you're doing it to accent your skills more than actually trying to create the next blockbuster. And that's absolutely fine. It's a great way to do different kinds of games. So, of course, you're probably going to need a team. So it could be other students, it could be other professionals that you know from other industries. Don't be afraid to share your game ideas with people. Okay, go to events, mashups, programming, game-a-thons, weekends, things like that. Share your ideas with people. A lot of people, when they start out, they're afraid that, oh, if I tell somebody, they're going to take my idea and run with it, and I'm not going to get any credit. Don't worry about that. They have their own ideas. Okay, you're going to come up with a new idea pretty quickly anyways if you tried. Okay, it might feel like it's the best idea ever, but it might not be, and you'll find that out when you start programming. So don't be afraid to share with people. You want to find people that are interested in that idea. They might be like, oh, that sounds great. Do you need an artist? Do you need another developer? And so on. And you really want to look for those people with a like mind that are going to help you initially really grow that idea and build it out. At the same time, you want to look for some people that offer strengths to cover your weaknesses. Okay. If you're all great at 3D math and graphics and programming and that, but you have nobody that can draw, your game is sort of limited in certain aspects. So you might want to find somebody else that can bring those other sides to the coin and complete your whole project. So you should also find still the people with talents that lie within your area, especially if that area happens to be what your game needs to bulk out. Having 3 or 4 programmers is great if you're going to have a lot of structured moments that you need to hand code every single one. Typically you don't want to do that with a game, but those are the kinds of people you may need if that's what you need in that development process. Don't forget someone that knows businessing or marketing or something. If you're going to take this all the way, you're going to publish it, you're going to get out there in the world, and you're going to be a huge success, you probably want somebody that you can trust, that you've worked with before, that knows a little bit of the marketing, businessing side. Because a lot of smaller companies really run into that issue. They think they can do it all themselves. They get out there, they're great programmers, they're great artists, they're great game designers. They know nothing about marketing, and that's where the slip up occurs. So try to keep that in mind when you're looking for your team of individuals to bring together. Of course, you could always fly solo. There's no meetings, there's no extra overhead. Whatever idea you like, you can put in there and you can get going. It's a great way to start things up or to prototype things. Different game elements, different mechanics. There's no pressure, it's just you. But then again, some people don't have the best dedication or drive. They get distracted by whatever games came out this week, and the research takes over their time, and not so much developing happens. So always try to make sure you have that extra person to give you that nudge, even if they're not necessarily in your team, somebody that can keep you on track if that's what you need. Okay, it is an important part. So those are the 2 ways to, sort of form your team and get started. Once you have that team, you have your idea, you really need to frame who is this game for. Okay, you need to consider your audience. You want to, sometimes a lot of companies or even individuals, I myself will do this, if I'm going to make a game that's for a niche group, you need to know that specific profile of person that looks for those kinds of games. And sometimes the best way to do that is to build a persona or a profile for them. Write it down or type it up, whatever. Get it structured, be detail-oriented. What kind of games do they like? What ones are they playing right now? And again, this is all subjective and hypothetical, but later on when you're developing something and you run into a problem, you can look back and be like, well, here's our 2 solutions. Which one should we pick? You look at your persona, you read over the details, evaluate it a little bit, and be like, well, this persona would have liked this decision. So that's what we're going to go with. Sometimes that's a great aid. So you want things like their age, their gender, your target audience, all those details. How much time do they play during a day? How much time do they play during a week? Right? Do they prefer co-op, single player, multiplayer, and so on, versus MMOs, anything like that? Those kinds of details are what you're looking for in that audience profile. And then whenever you have a question, like I said, about your game, you can go back to that, refer to that, and it helps you maintain your focus on the goals as the years pass by. In terms of platforms, which platforms are you making this game for? What differences are there between the selected platforms that you've chosen? We need to consider, are there control schemes differences? I've been in situations where we've designed a whole game And then somebody goes, oh, but we're also going to make it for the tablet or a phone. And the simplest things will slip by the entire design, thinking they can just, for example, scale the screen size, and everything will have enough room to play with, will have enough control space and so on, but you don't anymore, maybe on the smaller screen or a different format, maybe it's stretched a little bit more and so on. So those are important things to consider. Detail them. If you are going to hit multiple platforms, or you are going to roll out in different stores, you need to consider all those things ahead of time. Is there a large performance difference is usually the key one that everybody does consider. Oh, I'm going to run on the new Xbox One, but at the same time I want it to run on my phone. Those kinds of performance differences are going to be key to remember. Most people get that one. They usually forget the screen format, the touch controls versus a controller, and so on. It seems obvious, but you'll be surprised at what slips people's minds if you don't sort of write it down and actually consider it and think about it actively. Now, what hoops do you have to jump through on these different platforms? Some of them have certification requirements to get into the store and get it out there. Other ones have either none or a completely different set. If you're going to release it on the web, there's no real certification requirements. You just need to get it out there and away you go. But most of the phone vendors and other digital stores, you do have something that you have to meet requirement-wise, and that's important to try to do a little research into, make sure you're going to know the differences and that you can hit all of those differences. Also, what will those platforms be like when your projected game will release? Is the hardware going to change by then? Is it going to be a new console generation? Is it going to take you 10 years to make this game? You're going to have to be doing some crazy future planning. Hopefully it won't take you that long. That'd be a really long game to develop. You might have some issues doing that. But it's just something to keep in mind. Sometimes it plays a role. A lot of the smaller games, obviously we're not going to have those kinds of issues. Now, picking the right tool, also important. Should you use a game engine, middleware? Are you going to outsource some of the artwork and so on? You really just want to pick what fits your specific game's needs and goals. Some people will set out and do it the opposite way. What tools are available for me? What can I develop with? They'll just pick those, and then they'll develop a game that fits those tools. And that's perfectly fine. That's a great way to do it. At least you know you're going to be able to accomplish whatever you set out to do. But a lot of the times it's usually you have an idea or you've been handed out a contract or something where they want you to make a game a certain way, and you're going to need to find the tools that fit that. So can a certain tool fill an area or skill that your team is lacking? That's another great place for tools. For example, organizational skills. A lot of people lack organizational skills. And there are tools out there to help you with that, keep you on track. Okay, you can get Gantt charts and so on to keep everybody's tasks lined up. You know when everybody's going to complete the different tasks and move forward together as a team. So there are great tools for soft skills. There's all the tools we actually need that we're going to talk about today for doing the hard skills and the actual development as well. And using someone else's system, whether it's code that you've downloaded from the internet, or an engine, you have to realize that it was designed to do something else in a particular way or a particular fashion for whatever they were solving. And you're going to need to adapt that. You're going to spend time spinning your wheels trying to figure out why they optimize certain things certain ways. You're probably going to have to dig in and rewrite certain chunks of it. And if you don't have access to those chunks of source code, you're going to be caught and not really have anywhere to go at that point. You're going to have to change your game to meet theirs. So you got to be wary of bringing in other people's tool sets, especially when you don't have that low-level access, unless you, again, are building your game to the tools as opposed to the other way around. So another thing to consider, you do have other people working with you. Are these tools, are other people in your team comfortable working with these tools? Do they have experience with it? Or is everybody going to have a learning curve, picking this up, running with it, and trying to make something with it? You might want to pad out your planning initially for how long certain things are going to take you to accomplish in the early stages because of just the tool learning curve that everybody on your team is going to experience. And then finally, what are your deployment strategies and how are you going to manage your code and assets with multiple people? There are tools that help you with those kinds of situations, there are tools that plug right in with Visual Studio as well to help you manage, for example, your source code and push it up to a central repository that everybody on your team can grab, and you'll want to look at those tools and sort of see how they fit together, where can you get them, and wrap it all up. Deployment, same kind of idea. How are you going to build an executable, or how do you push to the different platforms that you're going to need? You're going to have to find tools that support that and make sure that everything works out really well. Bug tracking or getting responses from users when your game does crash is another kind of tool that you can look into. You can bind them right into your code so that when, unfortunately, somebody hard locks your game and it freezes up and crashes, it sends you back a little bug report on where it did, what possible data there was, so that you can fix it and get it back out there. Those are sort of the larger stages that the bigger companies are more concerned with. A lot of the indie developers don't necessarily have that in their little Windows stores, apps, and things like that. If it crashes, they hear about it on their forums and they try to fix it up that way. But there are tools out there, and that's what I want to make you aware of, that you can get and you can build into your systems to sort of handle that kind of situation. So Mickey, what do we need to really get started?
Well, I was going to say, actually, that was a really good overview of planning out a game. It does take a lot of time. There's a lot to consider, obviously, but if you go through those steps and you take that time, down the road, you're going to save yourself a lot of time, right? So, yeah, definitely planning is a very big part of making video games. A lot of us out there can code really well, but a lot of us have a little trouble planning. So, yeah, take the extra bit of time and definitely go through those steps. That was a really good overview, though. Yeah, so thinking of tools we're going to need for today, obviously you're going to need a copy of Windows 8, 8.1. There's some numerous ways you can get your hands on that. If you can't get a copy, you can also get a trial copy for this. If you're a Mac user, there's ways of getting that on your hardware as well. You can look at something like Parallels or using a virtual machine. You're going to need a copy of Visual Studio 2013. Ultimate or Premium are the best ways to go, I find. Anyway, they got all the bells and whistles for us to play around with. But if you only got access to Express, that's going to work fine for you as well. And yeah, that's about it. That's all you're really going to need to get started today with us. And yeah. So what do you think? You want to jump in and show them a little bit demo and what it takes to get a DirectX game up and going?
Yeah, we can do that. So let me just jump out of here. There we go. Sorry, it takes a second to switch over here. All right, so if we have everything set up, if you have everything installed, didn't mean wrong button there, you could just, to verify everything's in place, that you have everything you need. Again, Visual Studio 2013, when you install it and set it up, it has all the packages you will need for DirectX. There's no extra installing SDK pieces or other puzzle pieces that you need to find to bring in. So you could just fire up the Visual Studios here, and I'm in C# by accident. There we go, C++. And what are we gonna run here? Let's go with, does that one look good? There we go, let's do this one here. So one way to test, you could do the Windows Phone Direct3D app native only, and just create one of those. And effectively, if everything's good, should be able to just compile that and run that on its own right away. Of course, it'll pop up the emulator, and that may take a few seconds depending on your system once it's done compiling. But in the end, what we should get here, just to verify that we have everything we need for today's setup, is we'll see a nice little multicolored cube that you can spin around and manipulate on the emulator itself. So it's going to take a minute to load here. Coming online. There we go. It's got to install the application on our emulator.
First time always takes a little bit, and then afterwards.
There it is. So if you can do that, then you pretty much know you have everything you need to move forward with all the stuff we're going to do today. This is running in DirectX 3D, and that's about it. So it's a pretty simple little app. We will actually refer to this one again later on today as we go through different modules, just to show you how they pull this off, how they do the little different color bending between the corners, how to build a cube, and so on. And then we'll show you how we do it in our actual demo app as well, which if I pop that out, oh, didn't mean to kill it. There we go. I'll flip back over here.
So yeah, if you're been using DirectX for a while and you're probably kind of shocked. I was shocked when I first saw that, how easy it was to get a DirectX app up and running.
Yep.
You know, back in the day it used to take us, what, a weekend just to get a window to pop open, and
Yep.
you know, you'd be sitting there writing the engine all weekend, and then finally you get to dig into the game code. So yeah, definitely having that template is a huge bonus now.
Yeah, especially for beginners, just seeing how to do some primitive geometry and stepping through. There's so many topics you really need to get to a point like this where you actually have a little pop-up menu that you can tap on or click on. We got a little camera system here so I can jiggle it around. I'm the guy on the right at the moment, and you can move these little sumo cubes around, try to push each other, try to get them out of the area. And this is effectively the demo game that we're going to be looking at and going over. If I can get them off, there we go. Then we win, we tap it, and we get back into playing again. So that's what we're going to look at today, really. So again, we're going to use our cube that we just saw. We're going to look at how to build that cube out. We're going to place it in here. We're going to get this little cylinder for our playmat. And then we'll work with physics, AI, and all those other things. So this is effectively our end goal for today, is to try to get to this point where we can try to do, oh, he's fighting me good there. Come on, come on. And we'll be able to play this, and if he beats me, tosses me out of the ring there, then we lose. So that's what our end goal is, really. And that's where we want to get to. All right, so just let me pop back over to here so we can continue on.
Yeah, since we're talking about Visual Studio, I'll take over for a second and
Sure.
just have a quick chat about some of the cool new features available in Visual Studio. So yeah, in Visual Studio 2013, they've added a lot of helpful things for us, and I thought I'd take just a couple of minutes and step through a few of them for you. So first up, if you're a C or a C# developer, you've probably seen this before, but just recently in 2013, they released the Just My Code for C++. JMC feature, as it's known as in the short form, is basically there to help the users focus on their code. So you're not seeing all the other library code and stuff like that when you set your breakpoints, which is very helpful. I've done it numerous times. I've stepped into a function, and suddenly I'm getting thrown into a Windows library, and I got to step out and then step back in, and that gets kind of tedious after a while. So this is a really good feature, especially when you're doing the late night coding and you're trying to figure out why that bug's there, and you're pulling your hair out, just want to figure it out. So yeah, it's a really cool feature, and it's really easy to use. That's the one thing that I really liked about it. Getting started, here we got a little basics sample for you. If you just went and created a new Windows 32 console application in Visual Studio and had JMC turned off, if you set a breakpoint right at the very beginning, you'd see your stack, your call stack right there, and as you can see, there's a lot in that call stack, and that's just setting a breakpoint on a default, Win32 console application. So that's a lot of things to step through. But if you were to turn on the JMC feature, you'll notice right there my call stack is shrunk down to one line. So that's really helpful in my eyes, for sure. And the Just My Code doesn't apply to just the call stack window. It also has some benefits for your thread windows. So as you can see down there at the bottom, if you've got it turned on, you get a really nice looking thread window. You don't have a bunch of threads open and have to step through all those. So yeah, it's a really neat feature. Again, turning it on and off is just a breeze. If you were in your external code window there, if you're in your call stack window and you right click, it'll pop up a context menu, and you'll see right there that you got show external code. If you click that, it'll allow you to have it. If you don't have it clicked, you're going to have all your code hidden. So yeah, that's a really cool feature. Definitely worth taking a look at. Again, yeah, if you got it turned off there, it'll show any stacks that aren't yours in gray. If it is yours, it'll pop up in dark black. So you still get to see that, right. So you're not missing it all, but it's not, your focal point, so to speak. If you want to turn it on and off completely, you can actually just go right into the Tools and Options settings. Scroll down there, and you'll find a setting that says Enable Just My Code. You click that, and it turns it on, and away you go.
Oh, I like this tool.
Yeah, this is a pretty good tool, especially for us mobile devs, right? You're
Yep.
building games on the tablets, and you want to make sure that you know how much energy you're sucking out of these tablets, right? You don't want someone to get to play your game for 5 minutes and suddenly, boom, they got to plug it in, right? So this tool's been a lot of help for us, doing development like that. Again, very easy to use. All you have to do is go in here and set it up. So you set up your app. You go into your diagnostic hub page. You look for the select energy consumption. When you click start, it'll launch your application, and it'll fire this up along with the profiling. Then you're just going to go back into your application. You're going to run through it, maybe play the game, play a few levels, stuff like that. Try to find the most intensive parts of your game, really, right? Because that's what you want to test.
So the gameplay, I got to play the gameplay over and over
and over again.
Okay,
yeah,
I can do
yeah,
that.
yeah.
I can do that.
That's the fun part of development, right?
That's
Right. So then, when you're done that, you can actually just go ahead and click stop. Once you click stop collection, you're going to see a profile window pop up here, and it'll actually show you a nice little report detailing, how much energy you've sucked out of the tablet or mobile device, whatever it might be.
Right.
So yeah, it's definitely a good way to tell, do I need to cut down on how many models I've got showing on the screen at once, or how many particle effects I've got running, whatever it might be. But yeah, it's definitely a fun tool to use for mobile development.
Stop using the flash as a particle effect on the phone.
Yes.
So don't want to do that.
Yeah, that'll drain a little bit of battery.
Okay.
Yeah. Another really good one, and this is something that a lot of you might be familiar with in its former name, the Team Foundation Service. So Visual Studio Online, which like I said was formerly known as Team Foundation Service, is the home for your project data in the cloud. So basically what this means is you can have your code stored up in the cloud and allow multiple users to work on it at the same time without having to set up an external program for that.
Right.
So for smaller teams, this is definitely a good way of going. Getting up and running is really, really quick with this. In fact, you basically just sign in and it sets you up automatically. You can configure a single server. The Visual Studio Online Basic is completely free for up to 5 users. So that's definitely a bonus. And it works with Git repos as well as other project tracking tools.
Right, and that's how we did this one.
Exactly, yeah. We used Git so that we could work back and forth with this. So yeah, we took advantage of this ourselves.
That's great.
So yeah, it's just a little bit about the new tools available for Visual Studio 2013. There's a lot more. Obviously I could have done a whole presentation on this alone, but yeah, definitely dig in there and check out some of those new tools. They'll save you some time and some headaches.
Yeah, we'll see a couple more when we get to shaders.
Yeah,
There's
exactly.
some neat ones that we can look at, and there's a model viewer, and that a lot of people don't realize that it's in there.
Mm-hmm.
So when you're doing game development, you can see a lot of those little extras just to be like, am I seeing what I think I'm seeing? Okay, yeah, the model's supposed to look like this, and that's what I see in game. So it helps to verify.
Welcome back, everyone. Hopefully everyone's enjoying our presentation so far. We had a nice little break there. So yeah, we're going to dive right in now and start talking about the specifics of DirectX. Before we went to break there, we showed you a little bit of a demo on a Windows phone emulator. But today we're actually going to take some time. We're going to be working with the Windows Store application as opposed to the Windows Phone. We saw a little bit in chat there that people were talking about the phone there. Just wanted to, clarify that for you and let you know that yes, today we're actually going to be working with the Windows Phone.
Windows Store.
Windows Store. Thanks for correcting me there. Yeah, Windows Store application. So
this module, it's going to be on the capabilities of DirectX 11 and what's new to DirectX 11. We're going to cover that. Then we'll break it down into the iFramework view and your app and what that class is. It's an interface that we're going to look at that runs all that stuff. And then we're going to move to the basic game loop and the update stage as well as the rendering stage. Now we've also put the source repository up on Mickey's Scruffy Fern GitHub account. Okay, so if you go to this link here, github.com/scruffyfern/sumodx, you should be able to get all of those resources that we're going to look at. Now that is in the completed state at the moment that we're going to arrive at the end of the day, and that's okay. We're going to be looking at discrete pieces of it as we go through these different topics and sections throughout the day. So it's all there. It should be runnable. Once you grab it all, you can mess around with it and play with it. Just pay attention as well. And I know it's addictive and fun, but hopefully we want to get to the point where you can make that and extend it and build your own. All right, so let's start off with the capabilities of DirectX 11. I know a lot of people were talking about what can we do with this and so on. It's basically a fully featured set of APIs enabling you to create high-end 2D and 3D graphics applications and games, and that's really what people most readily sort of attribute to DirectX when they hear about it. But it's actually a series of packages. There's Direct 2D and Direct 3D, which each handle their respective sides of those kinds of graphics. But within that, within the total DirectX API package, there's also Direct Write, which handles all of our text rendering features and other systems like that. There's DirectX Math, which provides us a ton of handy functions for doing all the math that you love to do sitting at home while eating a biscuit or whatever. It also goes into the X Input, which replaces the old Direct Input API that was around for quite a while. It helps you to provide console controller support, for example. And then we have the X Audio 2 package, which replaces the Direct Audio package, and it allows you to create high-performance audio engines while improving performance at the same time. So it has everything you need to do all the kinds of effects that you know and love, but it is really for the person who wants to get down into the low level, optimize it so that everything can run as smoothly and as cleanly as possible. So basically, if you want to make a game that's graphics or multimedia intensive and can use the features that many of the current graphics hardware devices provide, then you're going to want to use this DirectX API. You'll likely find it a bit more complicated than other systems that you may have dealt with in the past, but that's because, again, it's opening up all of that power that you can harness to really take it anywhere that you want. Especially if you have very little C++ experience or development on the Windows platform experience, then there's going to be a little bit more of a learning curve there. But there's still some good news, and that is effectively that this version of DirectX is the most cohesive and power-packed one and feature-rich example or rollout that they've done for the API package in the past 10 years that I've worked with. So there is a lot there. There is a lot to play with. It's a great little package that can, well, I shouldn't say little because it's actually quite massive, but it will really allow you to do all kinds of features that you've seen nowadays in the various games that are already out there. So DirectX 11 has added support for 3 new shader stages in the drawing pipeline, and this is, just as the hardware develops, new functionality is added into the hardware as well as the software keeps up with it. We have things like the hull shader and the tessellator and the domain shader stages. There's the little graphics pipeline down the right, and you can see those 3 have really been slotted right into the middle in between the vertex and the geometry shader. The geometry shader was something that came in last time around in DirectX 10, I believe, and pixel shaders and vertex shaders have been around for quite some time. So if you've done some DirectX programming before, then you may recognize this pipeline, and these 3 new stages do have quite new capabilities that we're not going to necessarily harness today, but they can allow you to do a wide range of things. The hull shader, for example, it operates once per patch, and a patch is just effectively a set of vertices that make up a triangle or quad within a larger mesh typically used for rendering an object. The hull shader itself can do a couple of basic things. It can transform the input control points into output control points within a patch, but more importantly, it can provide what are known as tessellation factors, which are effectively just numbers that indicate how much a certain path should be tessellated by the next stage. Now, what do I mean by tessellation or what that is? You may have seen some demos online over the last year or so of effectively what we call infinite tessellation. You'll see a model, a low poly stage, such as there in the picture, and effectively all the vertices and the lines that make up that mesh as the camera pans in grow more detail appears in the model, such as the face, and it just gets more and more detailed until you zoom right into the individual wrinkles. And that's effectively what we're talking about when we talk about infinite tessellation. So the tessellator is probably one of the most exciting features, really, or in terms of gamers and that is in DirectX 11. And we really want to grab that power, to harness it, and to use it in our newer games. A lot of games are starting to bring it in. It allows us to do seamless LOD. You might have, for example, in the original Halo and so on, you could open certain doorways and you'd see geometry that would look pretty blocky, and then it would pop and it'd be a little bit smoother, and then after a couple more seconds it would pop again, and now it's the final model. And that was usually because a lot of the game engines are set up to load models as fast as possible, but they only have a limited time to do so. So they load in a low-level detail, or effectively that's what LOD means, level of detail, a lower LOD version of the terrain or a model, and then once they have enough time to get the higher res one in, they'll just pop it out with the one that's there. Eventually we started realizing the popping doesn't look real nice, so we'll start trying to blend between the two once we have the secondary model loaded. That looked okay, but sometimes you get weird like facial deformations. Somebody's nose starts to come out of their head now that they actually have a nose, and things like that. And you could catch models at a weird angle where you see that, and that wasn't working really well. But now with processes like this, we're going to be able to literally give an infinite level of tessellation effectively, or geometry that we can blend seamlessly and let the graphics card sort of handle it for us without actually even having to make that high detailed model. We can make a lower detailed model, put on the normal bump maps and normal maps that you would see to give it some detail, being a low poly model, and then the graphics card can fill it in with a shader, all that extra detail as the camera approaches. So the tessellator is the one that really generates the new geometry or the new vertices and splits each individual triangle into two triangles or more depending on your approach to give that detail. That's what that tessellator stage does. Then we have the domain shader, which is the third piece of the puzzle that completes the infinite tessellation kind of effect. It's invoked once per vertex generated by the tessellator, and each invocation is identified by its coordinate on a generic domain. So the role of this domain shader, that's where it gets its name, is from this conversion to a coordinate in the generic domain, is to convert that coordinate into something tangible, like a 3D point in space, for use later on in the rest of the stages of the pipeline. So that's really all it does, is convert all the math that happened, splitting up all the faces into new positions, points, and vertices. It's going to take those points of data and actually build them out into real things that exist in your game effectively. So this could have a huge impact on games with large open environments, for example. Oops, sorry. I accidentally hit my mouse. It can have a huge impact on large open environments. You've probably noticed that distance object popping. It's starting to go away in a lot of games, and really they're finding better ways like this to switch between those LOD positions. So up until this point, we really didn't have a great solution for that, but that's something that DirectX 11 really makes available for all games and game developers to harness and pull in.
Well, it's nice too because it keeps that realism, right? It keeps you immersed. You don't feel like you're being, pulled out of the immersion of the world. So you feel like it's an endless world, right? Like you can continue to walk off into the distance, and you don't feel like you're constantly loading or buffering the level, right? So, yeah, that's definitely a plus. It's nice to have these new shaders, that's for sure. I love the Tessellation Shader, especially when you're doing development where your resources might be limited. You can definitely take advantage of the Tessellation Shader to kind of help balance that, right?
And that's exactly the idea, is that now you don't necessarily need 3 models of the same model, a low poly, a medium poly, and a high poly anymore. You don't need those. We started trying to figure out approaches that would let you create that extra art as quick as possible without actually having to have a guy rebuild it. So maybe he makes the high poly version of the model, and then there's certain other tools that you can use to sort of crush those into a lower poly and then crush it even smaller into basically your flat, almost 2D guy, and so on. But it's all computer automated there, and it doesn't necessarily give you exactly what you need, so then you got to have a guy go back in, hand touch every little vertice to make sure it looks as good as it can at that level of detail, and so on and so on. And with this now, you don't need those extra stages. You can do the one, and you do it through a 2D image, normal app or so, and then all that detail comes out and gives you that cinematic sort of quality. And actually, that's another big one. A lot of games now want to do those in-engine cinemas, right? You don't want to have to pre-render everything because you need to do localization for different voices, then your face effects will look off, and other things like that. You want to be able to really just run it in-game, no loading, seamless, just transitioned with this same model that the player's playing with, but now get him into that cinema doing his talking role. And this sort of helps with that because you can kick up that quality for those close-up shots with the camera trucks right in on his face or something to see, the important stare down or whatever he's doing. But it'll be at a nice high quality mesh because of this dynamic sort of LOD system. So it's a neat feature. Hopefully, it's going to really get in there and we'll take it in some new directions and see what else we can do. The other part in terms of major changes that has happened here is there's a loosely coupled secondary pipeline, all right? And it supports, so effectively DirectX 11 now supports two separate pipelines, the draw pipeline, which we just covered, and that's your basic one that goes through and builds all the geometry, draws it out, does any color effects and so on, and then what is known as the dispatch pipeline or the compute shader pipeline as it's more commonly known. These two pipelines are said to be loosely coupled because you can't have the same sub-resource bound for writing in both of the pipelines simultaneously. You are dealing with your external graphics card or graphics device, whatever it is, and it only has a limited amount of memory. You're accessing it now from two different effective systems, setting them up to do two different things, but the card itself still uses that same memory pool. So they are loosely coupled in that sense that they share a similar place where you can write and read to. So the compute shaders themselves, they allow the GPU to be viewed as effectively a generic grid of data parallel processors without any graphics impediments from the draw pipeline. So the compute shader has explicit access to fast shared memory to facilitate communication between the groups of shader invocations. So the compute shader, it also has the ability to do scattered read and writes. If you've done any deeper DirectX stuff before, you pretty much can only go with a read. You can't necessarily just jump around and read and write as fast as you want because that interrupts the pipeline and the way the graphics card works. And setting those things, you want to try to do it as seldom as possible. The compute shader is sort of built for a little bit more of the random access, a little bit more of the data manipulation back and forth between the two systems. And the reason why we do that is effectively we're going to be using the compute shaders and that pipeline to offload any CPU heavy intensive tasks to the GPU if we're bottlenecked on the CPU. Now, a lot of people are, especially on the PC, that are going to be pulling down these Windows Store games, probably have quad cores, and all that kind of stuff. So if things are written properly, you can make use of all those different threads and all those different cores, but we still get CPU bound on various other platforms and on the computer if you push it hard enough. So this is there to allow developers just to give that ability and flex. If you're not really rendering a lot right now for some reason, push some CPU intensive operations over to the GPU, let it grind it out as blazingly fast as it can, and then pass it back for you to move forward. Examples would be AI and pathing. You can offload those. AI is typically, how do we call it, very easy to parallelize in certain senses. So we can grab all that data, put it onto the GPU in a compute shader, have it grind out our answer and bring it back to us much faster. We've got faster memory to access usually on the graphics card because you're at GDDR5 memory and so on. And we can do a lot of that load balancing, and that's really what the compute shader is sort of all about, and what we're going to be, not today, but what you would typically want to harness it for as a developer going forward. All right, so that's enough about really what we can do with the DirectX 11, what the fancy new features are, or the most exciting ones for game developers in terms of programming are. So now we're going to get into actually getting our Windows Store app up and running. Now, the starting point effectively for most DirectX App Store things is you're going to need this iFramework View class. And it's the main interface. That's why there's an I in front of the class name. It stands for interface. that allows us to really communicate with the underlying Windows Store system. So it controls the main event processing of the application and the main loop, and it maintains an overall state of the game. So it's going to know really what we're doing at any point in time. So the DirectX App Class in the demo, if you have the source code already, you can take a peek at it. We'll sort of go through all this in the actual game in a little bit, but I'm just going to give an overview of all these different pieces right now. The DirectX App Class is our class that extends that interface for us. So you can see here the reference class for DirectX App. Okay, it's going to extend our core iframe view, or iframe work view, and this is really where your app code would go. Whatever you want it to do, whether it's just say hi or hello world and then exit, or do some kind of crazy game logic. But unfortunately, before we can do that, we need a class that creates this view. So that brings us over here. Our Direct App Source class, which extends the iFramework view source interface. So again, they're very closely named. So something to make sure you don't accidentally hook up the wrong one to the wrong class when you're doing this initial setup. But really, all this class is going to do for us, our DirectX App Source class, is it's responsible for creating that view. So there is a virtual function that we're going to overload, and hopefully most of you have done enough C++ that you understand what a virtual function is. If not, we'll do a brief little overview as we go through the code, just point it out. But basically, this function is now overloaded and overwritten so that when the Windows system calls create view on this DirectX App Source class, it's now going to create that other class that is really our actual application. And of course, being in C++, we can't actually do anything unless we have a main function. So here you can see the create view. It just creates that new DirectX app. But we need a main function to really fire off that part, our source part. And so we've built one here. It'll look something like this. We've specified our platform is going to be an MTA thread. That's just sort of a signifier that we need to use. You may also notice that there's these carets being used right here. And those effectively are signifying a new type of pointer that they've built into the C++ system. It doesn't replace any of the other ones. It's just another managed pointer that is now in there. So it's customary for our C++ programs to be kicked off by a function named main. So we've added that. It returns an integer, which is just going to be 0 in this case. And we have it build our app source our class, and we tell the core application static class to run that app source, which then would cascade back. It would create our view, and from there would cascade back and actually get our main app up and running, doing whatever it is that we told it to do in the main thread. So that's really how you launch your application. Those are all the little bits and pieces that we need to really just get things up and running. And you can see that in our application. We'll take a look at it. It's pretty much bare bones. It's going to look like that in all of them. And then your actual view class is where we're going to build out all of the actual functionality for the application. But this main function can be as simple as that. And then the source view that creates the view will be as simple as that. And that's really all there is to setting up the initial pieces to get moving forward with. So, there we go. What does the DirectX App Class do itself? Really, it's going to drive and it's going to maintain the state machine for our game. So it's going to create and maintain 3 other important references as well. They are the 3 objects that are used the most in the game, or really make our game exist. One is the move look controller. It's going to handle all of our input. And then we also have our Sumo DX class, which is going to handle the game's logic and physics. And then we have the game renderer class, which is really just going to be doing all of the rendering for our game. Now, what states can I say that the DirectX class is going to be a state machine for our game, and it's going to have states? What does all that entail? We're going to take a look at that in a later module. But for now, it's simple states such as loading the game, whether or not we're currently playing the game or if we're waiting for the user to press a button to continue playing the game. So earlier you might have seen that little pop-up window that came up. That's effectively the waiting for press stage, and it won't do anything until the user taps the screen or hits start on the controller or clicks the mouse on that little window to continue on. There's also the dynamic state, which is effectively going to be when we represent the game being active, people playing it, things like that are happening. And then we also need to listen for certain states that can occur from the Windows system itself. For example, what happens if the window is too small to actually represent our game and see what's going on? We can listen for that sort of signifier from the Windows core and then respond to it with a state in our game. So it's going to do those kinds of things. Same with being suspended or deactivated. If you were to, for example, make a Windows phone app and you got a call, it could get suspended and so on. So all those states are going to be built into this class, and that's really what it's going to handle. It's going to move through and react to in some way. So that's pretty much all there is for the DirectX class in terms of what it's supposed to do. It also registers all of the necessary Windows Store app events to maintain just sort of the flow of how the application is running. And again, we're going to take a look at that. But right now, let's take a look at really what the basic game loop needs to be for a game. And I've written it out in pseudocode here so that we don't, have to go through all of the code because it looks a little more wordy when you put it in code. But this pseudocode is effectively breaking it down as simple as possible. This is the pseudocode specifically for our game, but it is a generic sort of basic game loop that you will see. So while the window is active, okay, if it's not active, then we probably should be doing something else. But while the window is active, we check if the window is visible. And if it is visible, if the game can't function due to size or a pop-up or it's simply paused, then we wait for a new event to change the state of the app. So that's just sort of our, hold steady. We've notified the user he accidentally unplugged his keyboard or his controller or something like that, and we'd like his input. So that's just where it sort of hovers and waits. Beyond that, we can move down. If there are none of those pop-ups or anything in our way, we go into our else condition where we do the normal processing of any incoming messages, whether it's other input or now we need to suspend the game and so on. And after that passes through, once we've registered all those, we update the state of the game, carry out all the actual logic, the rendering, whatever it needs to be doing at this point in time. Then we get an updated rendering to the current screen. So we push that up to the actual device and flip the buffers, which we'll talk about all those things later on in another module. So that's effectively the game loop itself. It's just going to keep processing. Usually the game's active. Usually the window is visible. Otherwise, it's going to be hard to play the game. So most of the time, it's really going to spend its bulk of its time in that else condition, just doing the normal processing of the game input, messages, updating the state of the world, render. Get messages, update, render. And that's really your basic game loop system. Of course, if the window isn't visible, we still need to catch any possible events that make the window visible. So we have that else case in there as well. And then finally at the end, we exit due to the window closing or whatever other signifiers you want for closing your game. But make sure to save the game state so that they can come back and play again and pick up where they left off. Especially if you're doing a mobile device, that's very important for the mobile developers because they get interrupted with all kinds of messages and phone calls and so on. And so we want that state to be preserved for the game. So we're going to just take a quick little walkthrough of actually seeing all that now in the game itself. So I'm just going to pop out here. Bear with me as I shift these things around. Okay, so jumping up to the DirectX App Class to start, we can see that these are those engine states that I talked about, and we've just made a simple enumeration. So it's a little bit easier for humans to read. The machine doesn't necessarily care if we use 0, 1, 2, 3, 4, 5 for our states, but humans tend to want to know what's going on a little bit cleaner than that. So I've written them in a plain, easy to read format using an enumeration. And also we have our press result state. So when we are waiting for press, if they click on the screen and we were loading the game, we're going to do something different than if we were playing or continuing. And we'll see all that again coming up. So the DirectX app itself, again, we see here, it's our main class, and it extends from the iFramework View class, which is that one that we expect to run everything in our game more or less. So we've got all kinds of different functions on here. You can see here's our event handlers for worrying about when we get suspended, when we've been told we can resume, and so on. Those ones we're not going to spend much time on looking at right now. But there's the other ones such as the window being changed, the size being changed in case they scroll it. We want to respond to those events, and we'll see how we do that again later on. So if I go down here, here's our main update function that we're gonna look at right now. But just before we jump to that, here are those three main objects that this application requires to really run the game and keep everything moving. So we have our MoveLook controller, our game renderer, and the Sumo DX class, which handles all the physics and the actual game logic itself. So this application now is going to create these. It's going to be responsible for really telling these three things what to do and when to do them, and communicate between them all. So it's sort of the bridge or the overall class that allows us to handle those things. So I'm just going to jump over here for a second and then scroll back up. All right, so the constructor itself, the main function that we were talking about earlier, there it is in the CPP file. Again, it's just going to create a reference of this app source class. And really all that app source class does, if I jump over to it, is it really just implements that create view function, which if we go to that, I know this is a lot of jumping, but it's just that simple. It creates our DirectX app class, which was the one we were just looking at. Here you can see we're right back below the main again. Okay, so it's just ping-ponging around, setting everything up, and then if I create that, here we are at our DirectX app. It's going to set a bunch of default flags for us for the app and let us go off on whatever our process is after that. So that's really all there is to it. These three little main function, our other source view class, and our actual app class, they all extend from those different iframe renderer classes, and that's really the basics you need to get your Windows App Store up and running. The process by which we walk through that and we manipulate that in the phone, we'll see in a bit, but that's really the code that you're looking for to get everything up and running.
So basically it's the foundation, right? That's
right.
What we need to get up and get going. It's what stores our necessary game objects for whatever implementation we might be doing.
Exactly.
So yeah, this is basically I like to refer to it as the foundation of the house,
sure.
Right? You need to build this before you can actually start putting up walls.
And it's rock solid because it's that simple.
Yes, exactly,
there's no questions in there. You're basically going to rename things to whatever you want, but you just fill in the blanks, and then you're at that stage where we can progress forward. Now, getting something to render in your screen in DirectX so you can see what you're doing, it's going to take a little bit more work, but effectively you have that basis to actually get something to kick off through the Windows Store app process and get you in and running. Okay, so now I'm going to flip back over here. And we're going to be doing this process of bouncing back and forth between code and our PowerPoint quite a bit. So we've got our main game loop set up and ready to go. The application's going to kick off. It's going to get us in there. And again, those two important things that we've said it's going to be doing is effectively just going to sit in that one chunk of the loop and keep going back, updating the game, rendering the game, updating the game, rendering the game. So the update stage is really the bulk of everything that's going to happen in your application. And we've made an update function, and that's where we've put all that data. So inside that game loop, it's going to call that update function. We're going to handle initial loading and intro sequences as our game boots up. Mm-hmm. That's an important part of it. We only do that once, but it's still got to be in there, right? So we do update. and those things happen. Once they're done, we can also do transitions between levels or in-game menus or other situations that interrupt sort of the flow of the game, such as pop-up messages when errors happen. So the update stage is responsible for that as well. And then it will also be responsible for updating the controller, which listens for the player's input from all of the different devices that he might be plugged into his Windows Store app effectively, and then bringing that information together, that input together, and then handing it back out to the rest of the systems for use. So most importantly, what the update stage is going to be doing is it's responsible for updating the state of that game world and all of the objects in it. That's usually what people think of when you say, oh, I'm updating my game, like in terms of the internal process, that's the part. But all these secondary things, the loading screens, the transitions between states and all that, it does that stuff as well, and it keeps that in check and sort of making sure that we're not running off into the middle of nowhere by accident. All right, so let's just take a look at the direct Windows or our DirectX apps update function and see just sort of that internal process. Oh. Boop. There we go. One extra tab more than I thought. Okay, so. Oh. Sorry, I forgot to actually hit escape. There we go. Transitioning over. Alrighty. Okay, so I'm just going to jump to the update function. Oops. And I hit the wrong button. That's going to take way too long. Back to the header.
There's a lot of updates in there.
There are a lot of updates, yeah. Unfortunately, that's a pretty commonly used word there. All right, so here we have our DirectX update function. And right away, we signal the controller class to update and check for any user input. We're gonna spend some time looking at all of that later on, but we can just pretend, you're pushing up or W or something like that to make the little sumo wrestler run around. That's the kind of stuff that the controller update function is going to be responsible for, is congregating all that data together and figuring out what the user is trying to tell the game. From there, we check our internal update state. What are we doing? Are we waiting for resources because the game is just starting and we're loading things? Or have all the resources finished loading and we now need to transition to either playing the game or continuing on from wherever they were, or some other step like that, in which we just simply show an info overlay so the user knows what's going on. Please push A to do this, or show them their game stats because they just won a level or something like that. And again, the next state we could be in is waiting for a press, which really comes from this state. Okay, there you can see we're setting ourselves into waiting for press. So now we're waiting for press. We check, has the user actually done something? Again, we talk to the controller for that. Has he pushed A or pushed start? Has he clicked the mouse button? Has he touched the screen in the right area? The controller will say yes or no every time, so we just keep sitting here checking until we see yes, and then we check again what is the result of that. Should we now load the game, play the game, and continue on the game from there? So all of these stages, these states, there's a lot of code there. They're actually much simpler, and we're going to explore that in a whole entire module just on its own, just to see all that state information. For now, I'm just going to gloss over it and sort of still keep going with what's in these update functions. Now this one, the dynamic state, is really the bulk, again, of our game. In comparison, you can see it's a much longer state, okay, and it's actually the last one that's in here. But really all we're going to do in it is first check if the game is paused. So again, we talk to the controller, or for example, has he requested that it's going to be paused? And if the user has pushed it, then we pause the game. We set up some states. We wait for a press again. When they click the button, we unpause and we continue on. If they have not requested for a pause, the game continues on as normal. So we tell the game, go ahead, run the game, and just update everything in the world. So that run state is going to be returned, and we're going to check, has he lost yet, or has he won? Maybe he beat the level. Transition to some other state. If he's lost, transition to some other state, say, sorry, game over, would you like to try again, and then come back in. So this update function effectively in the DirectX app, it's all that higher level state controlling stuff that I was talking about, that's really what its responsibility is. It calls the functions that are actually going to do the updating of the individual game logic, the individual components, the player pieces. It also does check if things are paused, and so on and so on. So it does all of those high-level functions, just sort of keeping everything in structure, everything in order, and moves through from there as we go. The individual what happens we'll see in those individual classes in a moment. All right, so popping back over. So a little bit of work.
Yeah,
right?
yeah. There's a little bit there. Yes, definitely.
There is a little bit to get through that stuff. The update stage after that, the main game loop goes to the render stage. Similar kind of process. It's a state in our DirectX app that's going to be an overview. It's going to do what we want it to do. It's going to render all the new positions of all the objects. But again, it's driven in a way that the DirectX apps just basically instructs, could you please do this? Could you do this? What state are we in? Fall back out, go back and do some other things. The rendering stage itself can be broken up into various parts depending on the complexity of the visuals that are required by the game. So some systems, for example, require multiple passes. For advanced effects like dynamic shadows, or maybe some of the X-ray visions through the walls, or heat scopes techniques, thermal vision, and so on, it might have to render multiple times the same scene to get all of that detail layered in the proper way, and so on. So some of the render stages in games can be quite complex and have a lot of mini stages effectively inside it. Now, luckily in our game, it's going to be pretty basic. We're going to keep to the minimum so that we can allow things to continue moving forward at a reasonably decent pace. Some systems also require that every other visit, for example, to the rendering system alternates between two slightly different camera positions. And that would be how you set up things like stereoscopic gaming if you wanted 3D.
Which is 3D, yes.
Yeah, it's 3D through whatever kind of device, whether it's something you're wearing or a 3D display or whatever. You would set it up in that manner, and every time you'd go through that render stage, you would either render it from this point of view, next time around, render it from this point of view, and oscillate between those two setups. So that's really what the render stage is all about. We're going to now we're going to talk a little bit more in depth. The steps of the basic game rendering stages is pretty much as basic as you can crush it down to. So you can think of this as pseudocode for what we want to do. Effectively, first off, you want to set up where and what it is that you're rendering to. So it could be the back buffer, it could be a texture. You've probably seen games where they've rendered a movie onto a wall while you're doing something else, or a trick for doing rear view mirrors, for example, is actually to put a camera where the mirror is and just film what's behind you and then put that on the mirror as a texture. Okay, that's rendering to a texture. Rendering to the back buffer is your typical approach. You prepare what you want to show and then you flip and actually show it once you're done drawing. If you don't use a back buffer like that, you can get that screen tearing effect you might have seen in games. Some people attribute it to a frames per second lag or something like that, but it's usually because if you don't have a double buffering system set up, you will be showing an image to the monitor before you're actually finished drawing what's in there. It can be a VSync issue if you're not have your game set up to actually sync vertically to your monitor. You might actually be showing half an image while the monitor is halfway done updating as well. Depending on your hardware and your software, you can get that same kind of effect happening there. So that's the back buffer that we write to. We write the whole game's image to that, and then we want to present it. So that's what we're setting up in the first part, is just what is it we are rendering to. Then we clear the screen typically if it's required. Sometimes it's not. You want those like flashbang effects where you sort of have that haze image of what was already there, or you want a weird shadowing behind an object as it moves. Just don't clear the back buffer. You'll have the image you had last time, and then you're just going to draw where the guy's hand is now, and so you'll get like the 3 or 4 hands in a row. Sometimes you don't want to, but typically we will want to clear the screen, so that's where we would do that. Then we go into rendering all of our 3D geometry, our objects, the players, the enemies, and so on. Over top of that, once that's done, we render our HUDs and any 2D graphics that you want to sort of sit in front. And then finally, which I don't want to say Yeah, basically, some developers will forget that we need certain things to always be on front, because if you don't have this here, you'll fail TCRs, technical certification requirements, or whichever way the company is that you're dealing with says it. But basically, some pop-ups are more important than others, so we actually add a little bit of a step in there for those kinds of pop-ups, so they'll always be on top of any pause menu or anything else that is a 2D graphic that you've already put up, without needing to really worry about ordering. You know, if you're going to draw these pop-up messages, that they're always being drawn last, so they're always on top of anything else that you're drawn effectively.
Yeah, it's something to keep like in mind when you're doing 3D and 2D at the same time, what order you're putting
right.
things on the
It's
screen,
that same
right?
kind of thing, only now there's a third layer that
yeah.
you're going to want just for these kinds of warnings and pop-ups. So once we have all of those layers of all those things drawn into our back buffer, onto our texture, we present it to whatever's going to be displaying it, whether that's the screen or the geometry. So that's sort of your basic render stage step through. And in the demo, we've created a class called GameRenderer for that, to handle all of that for our DirectX app via its render function. So let's just pop over and take a look at that. We'll step through that class and just see that that render loop that I just talked about is actually going to be there. I just got to grab the right class here. So if you go in under rendering folder, okay, and you jump down, we have GameRenderer and GameRenderer.h. I'm just going to open both those up. There we go. I'll just pin them so I don't lose them for now. Okay, so there's also a bunch of comments in here in case you forget what this class is for. Okay, there's a wall of text. And actually, this is coming from another project that we're going to mention later on. There's a first-person shooter that you can see online that was also done by Microsoft. And this code, some of this code is brought from that, so that this can be sort of your basic, your first step, and then you can move on and start working into that project later on. So here you can see the game render. It derives from, it's going to derive from the DirectX base class, and it's responsible for all of our DirectX or D3D11 and D2D objects that we're going to generate, whether they be HUDs or models or whatever. And there's a bunch of information in here. I'm not going to go through all that now. You can read it at your own leisure if you need to. But if we get down to our actual class here, there you can see it's extending from DirectX base. We have two reference classes, one to our Sumo DX, which is our game class that has all of the physics and the geometry and where everything is. So we're obviously going to need to know that so that we can render these things where they are, as well as the HUD itself so that we can draw to that. And the classes and functions, or sorry, the functions and methods that we have in here, basically everything you would need to do different things, from setting the dots per inch on certain devices, loading levels and resources asynchronously, topics that we're not going to necessarily worry about today at all, but the framework is there, and same with the first-person shooter one. As you expand to that one, the framework is there to get more and more complicated and get more things done and spread your knowledge across all of these different features. But really, the render function, that's the one that we really want to look at and deal with right now. So I'm just going to jump over to that one. And here it is. The first step of our basic rendering loop, we said we needed to set up the rendering pass to be completed. What is it we're drawing to? So here you can see that we are setting our render target, okay? And I've already built a target view buffer effectively, and I need to get the address of that buffer to draw to. Same with a depth stencil view, and that's effectively for making sure that objects that are in front of each other draw properly in front of each other, and so on. That's really what that one's going to be for. As we go through, we're going to want to clear that depth buffer to start, so we don't have any old geometry laying in there thinking that we should be drawing behind it or in front of it. We've got to make sure that we clear that out. And also we have a direct 2D context, which we're going to set to a target bitmap. So we're actually going to render to a bitmap first for our HUD, and then render it on top of our rest of our scene. So that's what I'm setting up here. So that's basically both the things I mentioned, one setting up to render to our back buffer and one setting up to render to something else. And that's what's in there. We need to make sure we clear our actual scene as well. Again, if you don't want to, for some reason, to do some cool effect, then you're going to put an if statement in here and say only if I'm not stunned or flashbanged or something like that.
Staring into two mirrors
Or
behind you or
sure,
something.
Something like that. That's where you would put that. But right now we're just going to clear the whole screen to this color, which is effectively a really dark color, just as a basis to start. Not pure black, but dark. So next we check first, are we running the game? Should we be rendering any 3D elements, okay, that have been loaded? So we just verify that we do have a game pointer to our game class, all right, and some bit flags or Boolean flags just to check if the game is loaded and the level resources we need are loaded. That's typical. You don't want to be trying to render stuff that doesn't exist. You'll just crash and so on. So that's in there for those reasons. From there, this section really is only used after the game state has been initialized. All the device resources are needed for the game. They've been created and associated appropriately with game objects. So things like textures have been loaded, and we know what game object needs that texture. All of that needs to be done once we get into here. So we can update variables on the graphics card in different ways. Sometimes we change things each frame. Sometimes you have to change things each vertex. Okay, which you obviously don't want to just put everything into the vertex changing buffer and update that every vertex, because that's a huge amount of memory that you're updating thousands of times a second, or trying to. You're not going to be able to. You're going to try to, and it'll just slow everything down. So we have different buffers for different time frames. That's how we've ordered the data that we're going to give to the graphics card. In that way, it gives us, one, more control, and two, better frame rate. That's really the purpose of it. So we're logically not necessarily dividing things based on what it is I'm trying to draw. Instead, we're logically dividing things by how often you need to update those resources on your graphics device. So in this case, this is the constant buffer that changes every frame. Okay, so things that change every frame are things like the camera position. Right? We were talking about if I was doing stereoscopic vision, I need to do the right eye, then the left eye to get the two images to get the 3D. So that's something that only changes once. We change the camera's position once per frame and then render everything in the scene. So that's something that goes into this constant buffer, for example. And you can see that actually happening here. We are setting up the constant buffer that changes every frame. We're altering or grabbing the view for that, which is effectively a 4x4 matrix that has that camera view in it for us. And that only updates once every frame. So once we've done that and we've updated those buffers, we come down here and there is a bit of a graphics pipeline that we have to deal with. Here's all those constant buffers we were talking about. Here you can see buffer that never changes. Okay, something I've put all the buffers in here because you may have a reason for them, but to explain logically and to show you the different stages you may have. So something that you only set once per gameplay. For example, could be the resolution. Okay? It really never changes, generally speaking. Or change on resize. So these are the values that do update when the user grabs his window and does that. Maybe they want to split frame, play the game while they're, I don't know, Skyping somebody or something like that.
Following through the walkthrough, right?
Sure, yeah, that's right. Yeah, sorry, yeah. Looking for where all the hidden secrets are so they can complete the game like they knew where everything was. Exactly. However you do it. So those kinds of change on resize, that's what goes in that buffer. Then we have changes every frame and changes every primitive, which I've shortened to prim effectively. So every like vertex positions and things like that, color maybe, and so on, that might change on each object. So those are those buffers that we set up, and you can see that it says VS, that's for the vertex shader. So all this information is to deal with the vertices, the geometry, and where things are. That'll go into the vertex shader, which we'll discuss and look at a little bit more in detail later on. And then we also have pixel shader buffers as well. So these are, pixel shaders are used more for doing color overlays and other effects like that, where really everything has already been rendered into position. You know where it is, and now you want to just haze it, apply a fog, tune render it, maybe put a black outline around them, and those kinds of effects. Those are sort of the pixel shader effects. We'll look at those as well. But again, you have different data that you want to update to do that, so we have different buffers for those ones. All right, so after we've got those buffers set up, the last thing we actually have to do is, well, walk through and render each one of those objects. So I've set up a little for loop here, and it's literally just going to go find our objects array, which we're keeping track of just things in the world in that. You can see that it has a bunch of game objects. That's the base class that I've used to represent anything in the environment. And it's just going to step through. It's going to start at the first one, and as long as we're not at the end, keep incrementing through and effectively telling that object to render using whatever its render function is. So for example, we have a class that renders our cubes for our sumos. We have our class that renders the cylinder for the base, the mat that they're playing on. They each have their own render function so that it knows what it needs to do with its vertices to push them over to the graphics card, get everything running, and so on and so on. So we're just going through the array, or the array of elements, and telling each one, please render, please render, please render, and letting them then do whatever they need to do. So that's the process of doing that 3D chunk of our render stage, effectively. After that, we wanted to do our 2D stage. Okay, so we're going to begin drawing that. And to do that, when you're dealing with the 2D context in DirectX, for the process of drawing HUDs or any 2D elements, you have to start by calling effectively this begin draw, which of course if I try to jump to it, we're in the Windows code. You can see that it's in Direct2D header and so on. And we are basically telling it that we're going to start drawing on this render target. Draw calls can only be issued between a begin and end draw call. So we know we need to start one and we need to end one whenever we're going to do 2D drawing. So I just thought I'd point that out because that's a little bit different than the 3D one. We didn't have to do that, right? There was no up here. We didn't say, I'm going to start drawing the 3D context anywhere. Okay, but for the 2D context, you do preface it with, I'm going to start drawing now. Please pay attention, and here's what I'm going to do. All right, so to handle the swap chain being pre-rotated, effectively things aren't rotated and aligned the way we want them to. So we're going to set a default transformation that's going to rotate everything into that 2D space that we want so that it's set up properly to draw to the screen. And why we will see, you can look through the code to see how we do that or why we do that later on. It's not that important, but basically we just want our piece of paper laying in the right spot, and now we're going to draw onto that piece of paper. So again, we only attempt to render in-game HUD and elements once everything else is loaded, once the game is running. So we check again, is there an issue? Do we have all our resources, our textures we need? If so, we have a game HUD class that we tell to render. We pass it the information about the game so it knows, for example, how much life you have or how much ammo you have if you're doing a shooter. So basically it just has a reference to get that information. And we give it the 2D context that we want it to draw to. And then finally, the window bounds that it's going to be drawing those HUDs within. And certain platforms have window restrictions still, possibly because of CRT monitors and so on. Other systems do not, because we have standardized hardware such as the phones. So it's nice to have those window bounds in there so that you can give it that information a little bit easier. So I'm actually going to jump to this class, and we're just going to go through the game HUD render part just to see what it does. Basically right now, is if there's a show title flag set, we're just going to draw a bitmap. We give it its size and the width and the height, and we take into consideration any margin constraints that we need. The rectangle itself, as you can see there, takes a left and a top corner position as a float, and then the right and the bottom corner, and then it draws your rectangle of that size, and we're telling it what bitmap that we've loaded that we would like it to draw in that rectangle. So the image we want, where we want, and how big we want. And that'll just simply draw that bitmap into our context, and it's ready to go. Now, if we wanted to draw text, it's a little bit different. We can do a draw text layout. In this case, you can see that it requires an origin and then a couple of other interface setups and so on and options. So in terms of where we want it, we're gonna position it based, again, considering margins and so on and the logo size and everything. Put it in there and then draw whatever our header is with whatever brush we want and so on. So it's just some basic stuff. We'll see that what it looks like. Again, we got to make sure the game exists, and if the game does exist, for example, during the game, we're going to tell you how long it's taking you to shove the other sumo out of the wrestling ring. So we have a little round timer that we're going to print up in the corner of the screen that's going to keep track of what's going on. So we grab the time from the game, we combine that with the string saying round time, and we get that length and we turn it into a string, and we tell it to draw that text down here, telling it the length and of course the buffer containing all of that round time, whatever, however much time it is, in here. And we can get our text format from above, and we can draw it out in a rectangle wherever we position it again, top, left, right corner, using the same kind of setup that you would normally do with a rectangle, and so on. The only difference is that you're going to want to take into consideration things like the point size of the font, and again the margins and so on, and how that's all going to fit together in that rectangle when you build it. So you can see that really you can just change this string, it won't matter, and this sort of builds itself out to be whatever size it needs to fit that, and so on. Also, if the game is actively playing, we draw a rectangle for the touch input down in the bottom left. So this is just drawing a basic a line in a square, so you can see how that's done as too. And that's just to give the user the idea of where he can touch to control the game. That's really all it's for, but we only do that during active play. We don't bother when there's a pop-up, because then they might play around with the little corner of their screen and it doesn't need to be there. So we only draw that square in the bottom corner when they're actively playing the game. If a pop-up menu comes up, that's why that is active play flag check is there. It'll just ignore drawing that rectangle, but we'll still do all the other HUD elements. So if they pause the game, they still see the time that they're sitting at, and how much time has progressed, or if they're on track to beat their high score or low score, I guess, in that case, since you're trying to get them out as fast as possible, but without the little HUD display. So just showing you different ways to do some of those features. All right, so let's step back. That has now drawn the HUD. After we draw the HUD, we need to do that overlay of warning messages, pop-ups, letting them know the controller got them hooked because their brother was pulling on the cord, or whatever it is. So finally we want to draw all of those pop-ups on top of everything else. And so we check if the game is actively playing. We draw a rectangle for the touch input down in the bottom left. So this is just drawing a basic a line in a square, so you can see how that's done as too. And that's just to give the user the idea of where he can touch to control the game. That's really all it's for, but we only do that during active play. We don't bother when there's a pop-up, because then they might play around with the little corner of their screen and it doesn't need to be there. So we only draw that square in the bottom corner when they're actively playing the game. If a pop-up menu comes up, that's why that is active play flag check is there. It'll just ignore drawing that rectangle, but we'll still do all the other HUD elements. So if they pause the game, they still see the time that they're sitting at, and how much time has progressed, or if they're on track to beat their high score or low score, I guess, in that case, since you're trying to get them out as fast as possible, but without the little HUD display. So just showing you different ways to do some of those features. All right, so let's step back. That has now drawn the HUD. After we draw the HUD, we need to do that overlay of warning messages, pop-ups, letting them know the controller got them hooked because their brother was pulling on the cord, or whatever it is. So finally we want to draw all of those pop-ups on top of everything else. And so we check if any game info overlays are visible, and this is just a class that we're using to represent any of those pop-ups. And if it is, then we draw the bitmap that we've stored all of that information in. So remember I said we were rendering to a bitmap. That's effectively what we're going to be doing for the overlay as well, and we just say where we want to render it to. In this case, the rectangle is going to be at half your width and half your height, plus the constant for how big it is. So it basically just is going to center it for us in the middle of the screen, so it's a nice pop-up, it's readily visible. The player is usually looking at the center of their screen, and now it just explodes in their face, and they have to deal with that message. And that's really what you want with those kinds of messages and that. So finally, as we saw earlier, we have to end our draw call to the 2D context, okay, and that just sort of wraps everything up. Now we could get an error, and we might get an error such as the D2D error, recreate target here. That error just indicates the device is lost, and it should be handled on the next call to present so that we can deal with it. That's not a big deal. You probably won't lose your computer while you're playing on it, but you never know. But that's what that error is there for. I had it stubbed in from earlier. And finally, the last thing we have to do is actually present the finished image. We have drawn all our 3D models. We've drawn all of our 2D overlays and our HUDs on top of that. We now have a pretty picture we'd like to display to the user, and that's what that present function will do. It'll just, I shouldn't have peeked. Went to the wrong one. Sorry, go to definition, there we go. It's really just going to be calling this command, which if you've done DirectX before, that's the swap chain present. So you're now saying, please present this other image that I am now finished with, and I will begin drawing in the thing that you just took off screen effectively so you can present it next. So that's the sort of the final step in actually getting it onto the screen. And there are a couple other like gotchas that we want to pay attention to, such as is the window being stretched or squished for some reason at the moment, and if so, notify that that's happening so we re-render the screen even though we just finished doing that. So, but this is the important part, that finally we present it. The rest of it is just sort of for rubber bumpers to make everything nice and cuddly so nobody sees any weird situations. So that's pretty much all there is to the render stage. Just let me pop back here. Make sure I hit the right keys to get back in there. But that's really all there is. So the update stage does all the logic. The render stage handles all the drawing of everything that we've done after the logic. And that's it. Now, the update stage itself, actually, let's just dig into the game's update stage for a second. So I'm just going to go back to the code because there is something I forgot to show as we were going through that. I actually want to show you what it is that the game is going to do inside that Sumo DX class. So if you go inside Sumo DX CPP here, actually I'll also open the header. Again, there's some comments in here so you sort of know what's going on. The important things: move look controller, game renderer, a camera, also very important, and that list of things that we are rendering, that render objects list. So that's where it comes from. So I'm just going to pop down here. You can see that there's not too many states in this class. It's pretty simple. We do have our run game. That was the one I wanted to show you for a second. And if I go to that definition, so this is the one that gets called by the update stage before we do any rendering or anything like that, after the input has been detected. And it's just going to do simple things like update the timer so that we see, again, the render, how long it's taking you to push the sumo guy out of the ring. That's controlled by that timer. So we need to make sure we update that before we render. Keeping the camera facing the direction of whatever the user's input is. Letting the player actually move velocity-wise. We'll come back here and we'll look at this when we get to physics. This is where all of our physics is going to happen in this update dynamics function. And then after that, did he leave the mat or did the opponent leave the mat, in which case the game is complete or the player is lost, and vice versa. And we may want to save his high score, for example, if he achieved one. So that's really all that update function does within the game itself. Again, it's broken down into as small chunks as possible, so everything's nice and easy and tidy to manipulate, to find what you were looking for, and to work with. Okay.
So basically what's happening is we're checking for our input, right?
Yes.
Then we're going to pass that input along to our objects. We're going to let our objects take in that input. We're going to do the physics on those objects.
Yep.
And then finally we're going to step into our rendering and render where they've been moved to and after all the physics has been done.
Exactly. That's the general update stage that we do, and then we do the rendering stage after that. So that's your basic game loop. You don't have to write it out in classes like that, all segmented like that, but as your game grows and as things get bigger, that will be a big deal. It'll just help you find all the little bits and pieces that you need to pull everything together. And so that's why I've shown it that way, and it's set up that way, so you sort of can see where to grow your games if you're used to writing things in one class or smaller little setups. Okay, this is sort of your extrapolation and how to break it out into three major pieces: the renderer, your actual game that updates everything, and the controller for input, and then wrap it all together in one application class that steps through all those things.
Yeah. Yeah, well, we went through a lot there, that's for sure, right? And well, you know, we looked at the foundation or the framework of the game. You know, we looked at how do you update everything, and then finally we looked at how to render everything. So that was a really good overview of the basics for building the game, right? What the things that you definitely need to do. Yeah, so sounds like it would be a good time to take a break, and let everybody kind of stretch their legs, and you know.
We'll dig into it a little bit more discreetly and specifically on how to render certain things and get something showing now in your game now that you have that framework of how we're going to manipulate everything in the game itself.
Sounds good. So yeah, we'll take a 10-minute break, and when we come back, we'll dig into you know, creating, texturing, and moving some objects. Welcome back. We just had a few minutes there where we were doing our break, and I was reading through the chat, and I noticed that one of the questions that was popping up was, how come I can't get this to load? So I just wanted to take a couple seconds and just restate what you need to get this project up and running. First and foremost, you need a copy of Windows 8.1 or 8, preferably 8.1, because some of the code that we are doing might require 8.1.
Yep.
As well as you're going to need the Windows SDK 8. That's a good thing to download. If you got an Express, I think that's a must if you have Express. If you have Professional or Premium or Ultimate, I think that gives you the option to download it while you're installing. So that's a thing that you definitely need. And of course, you need Visual Studio 2013. That's what we're using to build it today. So those are just some of the things that you definitely need to get up and running. So if you're running into issues where the project won't load or it's saying, you know, unsupported version, this is probably the reason why.
Also, there were some questions about how much work would this take to backport it effectively to Windows 7 or DirectX 10, for example. It's a fair amount of work simply because we've built some of these systems to buy into the Windows Store specifically for Windows 8.1 and things like that. So you do the initial setup part of what, you know, classes you use to get your application running, that part would have to change and so on. But the theory of how to build those buffers, for example, of when things should change and what you should update on your graphics device, that would stay the same, and things like that. So pretty much the theory would stay all the same. You still want to set up render loops and your main game loop the same with the update stage and render stage and things like that. But it would just be the initial classes that you would use to actually build a desktop app. You wouldn't need the Windows Store integration part because it's a desktop app. It's not going to respond to any of those. For example, like the snapping, like you had said, and things like that. It won't be getting those calls as a desktop app, so you don't need the integration to the iframe view source and those kinds of classes. So if you wanted to make a traditional desktop app, or you're in Windows 7, you wanted to do that, you would do it in that way. But the theory and all the concepts that we're covering today, all the same ideas, same applications. You make a cube the same way, which we're going to see in a little bit, and so on. Shaders would stay the same. It's using the same shader language, HLSL. So that part won't change, but the initial, I guess, basically what we've just covered would be slightly different.
And the same thing goes for the backwards compatibility, right? The theory is the same, but the syntax is going to be a little bit different. So yeah, you can take everything that we're doing today and talking about and just basically extrapolate it and change the syntax up a little bit.
Much like somebody else was pointing out that we're not using raw C++. That's correct. We're using an enhanced version of it.
The managed C.
With managed pointers, the new pointers that I pointed out early on and stuff like that. It's the same idea, same theory. You would just backport to whatever version of C++ you wish to use and go from there. So the concepts are all the same, different syntax for those different abilities if that's what you want to do. All right, so let's move on. We're going to go through creating and texturing and moving objects. All right. Again, we're going to cover initially some things we should know about. For example, how DirectX goes about making a mesh, vertices, triangles, etc. And then we're going to actually see a different an approach to creating one of these meshes through code in case you don't have a modeler, that you can poke and be like, I need a character, make me one, please. Then we're going to manipulate that object and look at also how to finally get that mesh to render. And finally from there, create more of those meshes without all of the extra overhead. So we're going to look at a simple way, or I guess I should say a common way, in which games will be able to show you the same thing but in different places. We're just going to bend space and time so that we don't have all the overhead.
I love bending space and time.
It isn't, yeah. I mean, you get used to it after a while. It takes a little bit of skill. So the things we should know for this really is that DirectX games use polygons to represent objects and surfaces. Typically, they will be triangles. You can use quads in different rendering systems and other engines and that, but we're going to stick with triangles for today. 3 points are easier to manage than 4. And we'll go from that kind of perspective. Those meshes are then going to be passed to the shader pipeline during the rendering stage of the game loop to be processed and displayed. So most games store this mesh data for their objects in external files from a modeling program, for example. There's a bunch of them out there. There are free ones out there that you can get that you can bring in, make some kind of character and export it in a common format like a DAE file or what's that other one that we use commonly?
FBX.
FBX, there you go, thank you. That's the one I was thinking of specifically. And like I said, Visual Studios actually has a model viewer little mini program inside it. So you could open up, bring that asset in to the Visual Studio project itself for the game, double click on it and see that model, and you can even manipulate it in there as well if you need to make little changes to it. So that is a neat expansion that is going on in Visual Studio, and I just wanted to highlight that because a lot of people don't realize that that's actually there, but it is. So you can take a look at a model even if you don't have the modeling program because you're not an artist. Why would you have that software? Maybe you just have the code suite. Now you at least can visualize and see what it is you're supposed to see in the game and then verify that those two things sync up. So that's a great little addition. Now another approach is to store those simple meshes, or for simple objects like barrels, they're really just cylinders, crates, I mean they're cubes, and so on, little power-ups, all the iconography that is 2D that faces the camera, right? They're just quads and so on. We don't need a modeler to make us that model, export it in a file, and then pull it in to display it. We could just embed those vertices into an array within a class and then just say create me a cube, create me a cube, create me a cylinder, and put them wherever we want. So that's another way to do it for simpler models. There's no need for that external modeler to bulk it out and make you an actual file that you then have to worry about parsing. You have to bring it in the right form. If it's DAE versus FBX, things can be labeled differently or different shapes or different orders. You have to worry about all that stuff. We're coders, let's just code it right into a class and it'll be enough for today. We just need 2 cubes and a cylinder for the mat, so we're going to go with that approach for today. So the basic meshes can also be written right into the code like that, and that's what we're going to be concerned with today. Alright, so let's move on and actually look at creating a mesh itself. So in most games, the mesh for a game object is loaded from that file, and it contains specific vertex data. So the ordering of these vertices is app dependent effectively, but they're usually serialized in either strips, fans, or lists. Okay, and here's, for example, some images on what I'm talking about. That vertex data, it can come from any of the software sources, or it could be created manually internally, or you could have even just written it by hand in a text file. That would have been also suitable. But it's up to our game to really interpret that data in a way that our vertex shader later on can effectively process and render. So if we were to use something like strips, when the vertices are stored in strips, each vertice from the previous polygon, or rather 2 of them, are going to be used in the next polygon. So you can sort of think about it, you're going to do this, and then effectively you're going to do that, and then you need to flip it again, so that each 2 vertices in the previous thing in that order are in the new triangle. So you can see that there on our image. We have vertice 1, 2, 3. Then when we add vertice 4, it reuses 2 and 3 to complete the next triangle. And then when we add 5, it uses 3 and 4, and so on, and sort of unfolds it like that. It's like when you're folding up origami and then you like open it up, you get a creased piece of paper and it's all these triangles all over. Sort of looks like that. That's effectively the essence that what you're trying to do. Now that can be very difficult for certain things, such as if I wanted to make just a basic house with your cube with the slanted roof. Could you pick one of the corners and now tell me every corner after that to perfectly unfold that house made up of triangles, 2 for each side of the cube and 2 for each side of the roof, into one strip where they follow this pattern. All right? A lot of people have trouble unraveling things mentally or even on paper into that setup. So it can be hard to do it by hand in that manner. So that brings us down to lists. But the nice thing about triangle strips is it saves memory, because now I don't have all the duplicate data. Triangle 1 isn't made up of vertex 1, 2, and 3, and then triangle 2 is made up of, 3 new points again. As you see in the triangle list, that's exactly what happens. It easier for people to mentally break down, because now you just have to say, where's this triangle? Now where's the next triangle? Where's the triangle on this side of the roof? Where's the triangle on that side of the house? And so on, and just state all of those vertices. So it's much easier to work with in a triangle list, but now we have duplicate data, because every triangle should be probably sharing 2 points with another triangle, but you've written it twice. Okay, so the triangle list is sort of the most inefficient way to do this, but then again, at the same time, it's the easiest for people to work with mentally and to lay things out. Then we have triangle fans. It's another way to optimize triangles. It's great for doing things like people's eyes or large fanned out surfaces, obviously, because you basically just give it a center point or an origin fanning point, and then you just do all the points around the outside, and they all connect.
I believe that's how we did the mat in our demo, isn't it?
For the top of the cylinder, that is sort of how that is laid out, yeah. You'll see that the texture stretches in a funny way because we haven't bothered using our amazing art skills as programmers to make it all pretty. But yes, that's effectively what is sort of happening there. It's that kind of stretching system. So the fan form, it's similar to the list, or the strip, sorry, in the way it works. But again, it reuses now the origin point and only one of the last points in the array of vertices that you've listed to make that fan. So it's slightly different, but same idea. Now, because our demo game doesn't require any complex models, we won't be loading any external mesh data or files, but resources and tutorials on this topic can be found all over the web. Just Bing it and you'll find it. And if you want a more complex model, you'll have to import it, parse the file, and take a look at it. So now, creating the mesh itself, really the minimum data required per vertex is position in some kind of local space. All right, where is this vertex? So in that previous Windows Phone Direct 3D template that I had opened up there for a second, we had that little multicolored cube spinning around in Module 1 just to verify everything was running. And I'm going to refer to that one a couple times here just so we can see two different implementations, our game as well as their version of it, so you can get used to the way of doing things without just memorizing specifically how we coded it. So the minimum amount of data that we require for any given vertex is that vertex position in either 2D or 3D space, depending on what it is you're trying to draw. And a cube is made up of 8 vertices, right? So there's 4 corners at the top, 4 corners at the bottom. There's your 8 vertices, and they're all connected in a triangular fashion. So in the code here, you can see that they have laid out their simple cube vertex is just basically their wrapper class to talk about this location data. They've made an array of them called cube vertices, and it's basically just a vector or a float 3, however you want to refer to it. It's 3 points of data, once for your x, your y, and your z coordinate of that vertex. So what they've done is, if you take a look at the first list, there are 8 float 3s separated by another 8 float 3s on the right. We'll talk about what the right side data is in a minute, but the first row, or sorry, column, the first column of data is the vertex positioning for each of those vertices. And you can see that they've decided to do the top face first of the cube, so they've listed it at minus 0.5x, positive 0.5y, minus 0.5z, so that's our back left corner effectively. And then positive x, positive y, negative z, so we have the other corner. All of the y's are going to be positive because it's that top face of the cube. All right, so we're specifying everything up here, so they've raised it up half a unit above the origin. The origin in this case for the cube is that center position. So they've moved everything up, and then they've spread one out into each corner at the top, and the bottom half of that column are the 4 vertices at the bottom of the cube. Again, half a unit below the origin point, move it out to each corner half a unit in X and Z position. Now, all of that data gives us, that would have been the basic information we need. We didn't actually need that other column, but because they wanted to make it colorful and give us that cool technicolored look, what they've done is that other column is the color point they would like at that vertex. Okay, so they've, again, color can be split into red, blue, and green channels, RGB. All right, so if we said full on R, full on B, and full on G, so 1, 1, 1, which I believe you can see is the 3rd row there, that's our white color. So the corner that is white is that 3rd row, and that's the position 0.5, 0.5, 0.5 in this case. And that's how they've done it. And then they just change the colors as they go around the cube with that secondary column of data. And that's not uncommon to include color information into vertice information. And we do that for simple games, especially on mobile, where they do simple shading just using that vertex data. That's quite common. As you can see, the graphics card interprets that rather nicely. It takes the color data from one vertex and the next and blends from one color to the other nice and smoothly. So you can do some neat effects just by using that color vertex data that you might want to embed with your vertices. Now you can embed other information such as lighting. Okay, that can also go in there. You can do UV coordinates. Okay, so a UV coordinates, since positionally we call them X, Y, and Z for where this vertex is. If I wanted to tell you what part of a 2D texture to paint to that vertex, we need a 2D coordinate system. So we've called them U and V. And that's where a UV texture coordinate gets its name. So it's basically saying where in X and Y on my texture should I take that piece of color and stick it on this vertex. And so then you can blend from this vertex to this vertex across the texture using UV coordinates from this point to this point, but on my texture file. And that's how they map effectively a texture onto, wrapped around on a cube. Now you have to do it in a certain manner, obviously, because you are taking a 3D object that you've unwrapped into a bunch of triangles and then stuck it on your 2D image and then painted over it, and now you want all that data to come back. There is a specific way to do that, but that's known as UV texture coordinates and UV texturing. And we'll briefly take a look at that. We'll describe that as well, but that's something more that falls into the realm of a modeler. He's going to be worried with unwrapping the model, even if it's a complicated humanoid, laying out all the individual triangles or quads that make up that person, and then painting properly their face over it or whatever to get it to appear. We just have to interpret that data. Another type of data is a normal, known as a normal, and really it's just a vector coming up off of a surface. Okay, so you could think of it as if this was the top of the cube, and I put my other hand on it, the direction my thumb is pointing would be known as your normal for that face. In this case, though, it's the normal for the vertex. So vertexes represent really the corners of the cube, so we would want them coming off on a 45-degree angle in all directions, sort of off that corner of the cube. That kind of data can be put in there, and we use that for lighting. All right, so that will help us calculate ways shadows are casted, the way light reflects on a shiny surface and causes that sort of halo-y glow on a metallic surface. You get those hot spots, we call them. Okay, that's all done through normal data and interpolating between those normals. So that can also be embedded into your vertex data. Now, their case, in their little cube demo, if you look at the simple cube vertex, if you right-click on that structure and go look at it, they have specified just a point, X, Y, Z, and their color data, RGB. In our demo, we're going to take it a little bit further, and we're going to put something else in there. So how do we specify to DirectX that a vertex will have certain pieces of information over others? That's effectively what we need to look at. We now know that they want color data and they want positional data in there for that cube. So what they've done is the first step is to create sort of this input element description, and there's a D3D11 input element DSC structure flag that we can use, And we're going to set it as a const because it's not going to change once we tell it this is how our cube is set up, or how the information for each vertex in our cube is set up. That's never going to change over the course of our game, at least not in this game. You may have a reason for changing it later on. And so what we're going to do is we're going to have all of the cube's vertices stored in code, and then we're going to load them into memory. That's great. But in order to actually render them, we need to transfer and store those coordinates and colors on the GPU's memory. So we got to move all that data to the graphics card. And like I said earlier on in the first segment, or second segment, we can't constantly be accessing that data. It's going to cause some problems. We're going to lose frame rate. We don't want to do that. So we'd like to do as few things as possible. In this case, we'd like to push over the description so that it knows the format of all of these, and then never touch that again, because that format's going to stay the same. We just then later on say, could I have a buffer of these? And it goes, oh, okay, sure, I know what you're talking about now. Here's a buffer with enough of those vertice spaces. Go ahead and fill in that information with whatever you need. Now to get that vertex in there, we need to set up an input layout interface. And here's the code again from the sample. First, it creates that description. It states the name of each of the data elements, okay, which we will refer to in the shader at some point when we go to render this. So it's going to have position and color. So we've just named them as such, position and color, right in the description. The next element after that, in this case, we've put 0 for both, and that value is appended to that name in case you have, for example, 3 colors for some reason, or something that's named the same. That next element is just sort of appending, so you know this is position 0, position 1, position 2, because some complex shaders will distort the position of things, right? So you'll need to know the different stages of this guy morphing into, you know, some big crazy creature. So you might have to label them similarly, but that index lets you know which position we're dealing with at that point. So that's what that variable does. The next variable, or parameter rather, in there is our format for the data that the position or the color is. In this case, you'll notice that they both say the same format. And if you take a look at it and try to figure out what it's trying to tell us, it says R32, G32, B32 as floats. So basically we're saying we want 32-bit red value, a 32-bit green value, and a 32-bit blue value. But why would I need that for position? That makes sense for color, red, green, blue, great, I got a good range of colors, right? Why are we also using that format for position? Just so that we don't have a bunch of the same structures for 50 different things that effectively could be used with the same amount of memory, we need an X and a Y and a Z, RGB, 3 things, right? And then we need 32 bits again, because it's the same data range that we're going to use, which is a float. So we just say R32, B32, G32 as well. And it doesn't matter that it's positional or color data. They're both 3 valued floats, and that's it. So that's nothing to be confused over. It's not a mistake in the code. That is correct. They are both supposed to be the same, even though one looks like we're talking about color with position. And so that's what those values are for. There are other ones that allow you to do 2-dimensional colors, or just one float or whatever, depending on what kind of things you're passing in, such as an alpha value for RGBA and so on. The next one, 0, again for both, it specifies the input slot parameter. We're not going to talk about that. Just set it to 0, you'll be fine. It's more of an advanced thing that you might need later on to do fancy effects. And then next comes the aligned bit offset values. So that 0 and that 12 in those buffer descriptions. Basically what this is saying is, where is this data for this element in the overall buffer from the starting point? So position, it's the first thing I'm going to state. So it starts right at the beginning. So I say 0. 0 bits in, or bytes in, sorry. And then position takes up 3 bytes, 4 bytes, sorry, for red, 4 bytes for green, 4 bytes for blue, which are X, Y, and Z. So that's 12 bytes of information. So color can't start until 12 bytes later. So we say 12 for our parameter there for the offset, so it knows where the color element now starts. Now, we're labeling them logically in order that they happen anyways. So why do we need to put that number in? Well, it's just in case you don't label them in that, or you inject some code later. That's why it's there, just to give you the flexibility to do it in any order you want. But as we'll see in the code, there is actually a little shortcut defined that we can use in DirectX now that just says, I've put them in the right order. please calculate this for me, and it'll do so. So that's a nice new feature, again, that I've noticed that has come in over the later versions of DirectX that we can now use. So you don't have to do all the math in your head and type out the right number of bytes for each little piece of information as you're making this description. So after that is D3D11 input per vertex data. So that second last parameter it allows us to input what kind of class of data this is, so that the graphics card or graphics device knows how to handle it a bit better. We can obviously do certain optimizations for certain kinds of data, and this is going to allow us to sort of know what's going on. So we've said that it's an input per vertex data, so we're letting it know this is going to have to change for every vertex. The color and position are going to change every time I talk about a new vertex, more or less. So we've gone ahead and set that so it knows that this information is going to constantly shift. And then the last thing we can't use, the final parameter there, that 0, 0, can't be used because of the fact that we actually said input per vertex data, because what it's meant for is our instance data step rate. So we could say, use this same information for 4 primitives and then change it. So maybe they all have the same color, and you know that in your game these things all have the same color. You can use that to signify how many things to draw before changing the color value. But in this case, because we're saying it changes every time, every vertex, that value has to be 0 so that it always updates in sync as well. And it won't let us use anything else when we put input vertex data in there. All right, so, I did it again. There we go. Gotta stop hitting that scroll wheel. So finally, the next thing we want to do is we need to create the input layout on the D3D device. We've, again, just defined it on ours. We haven't actually gotten it over there. So that takes care of the description part. Now we can create the actual input layout on the graphics device itself. And we do this by doing something similar that is shown here. The D3D device, we tell it to create an input layout. We pass in our description, so in this case, the vertex description that we just created. We tell it the size of that thing, and we can just use array size to figure that out. So it'll get the array size of our vertex description and fill that in. And then the rest of these, file data is a pointer internally in the demo. That'll be different than yours. But basically, you have to hand it the data of those vertices and the length of that data into there, and it will hand you back your reference to your input layout that you're then going to refer to in the future. So that's that process. So that line of code, that's how you do it, but it's going to need to change each individual time you use it, and we'll see that in our game, how it slightly shifts to be able to actually do that. So at that point, we now need to create the buffer for all that data based upon that layout and then push it over. So that's the next stage. There is a lot of setup in DirectX just to go into getting something set up to render. But once you have it there, then you can manipulate it, and you realize the process stages, it becomes second nature. It's really make a description, create a layout with that description, create a buffer with that layout, push all my data into it. Those are the steps that we're going to keep doing for any object that we would create, whether it's a cube or a model or a cylinder, it doesn't matter. Those are the same kind of stages that we're going to step through, and that's why we're highlighting all this, so that you can see this is what you have to go through, the process you have to go through to get to this point of actually rendering something. So the vertex buffers, they contain that list of vertices for each polygon in the mesh. All right, the vertex shader runs on the GPU, and it reads from that buffer and interprets that data based on the input layout that we just finished specifying. So to actually create that buffer on the card itself, we need to set up effectively a D3D11 sub-resource data structure and the D3D11 buffer description structure for that vertice group that we want to create. So the D3D11 buffer description and the D3D11 sub-resource data structures, they're there to ensure that DirectX understands the physical memory layout of that buffer, including the size of each vertex element in that buffer and the maximum size of the vertex list itself. We can also control access to the buffer memory here and how it's traversed if we need to. In this case, we're not really going to need to. It's beyond the scope of the tutorial, so we're not going to cover any of that stuff. But after we've configured this buffer, we call the create buffer command, which you can see is the last line there, to actually go about manifesting that buffer on the graphics device. All right, so if we had more than one object, we'd have to go through a similar process to create a buffer for each unique model that we wanted so that the models would exist, and then we can start the process of trying to draw them. All right, so this information here, the sub-resource data, those p-system mems and systmem pitch and systmem slice pitch, those are all those things that allow us to manipulate how it's going to be traversed, and we don't need to worry about any of that. It's going to be nice, straightforward, just read it as it is in our buffer. We're not doing any crazy optimizations for right now because we don't need to push the hardware to the limit just to draw two cubes. Hopefully not. So we're just going to leave all that set up as such, and we're going to build that buffer description by passing that information in and then create the buffer with that line of code.
It seems like a lot, but after you do this a little bit, it starts to become, like you said, second nature.
It does, and you're going to make a function that's going to help you do these kinds of things occasionally, and classes that hold my cube. So now I can literally just say new sumo cube, and there's another sumo player running around in the environment, right?
Yeah, this goes back to you need that solid foundation,
Yes.
and once you got your foundation in place, you can start putting your walls up, so to speak.
Exactly. The foundation is the most important, and since this is, from the ground up, the beginner kind of entry point, that's what we're going over. So again, you're going to probably take most of this code right out of that other project, that the Sumo project that you have now, and start adding your own classes that do the exact same process to make a sphere, for example. Sphere is going to be a little more complex than a cube, obviously, because you got a lot more vertices to deal with, okay, and so on. So maybe you want to start with a trapezoid or some other shape or a diamond or something like that that's just a manipulation of the cube layout before you get into that approach. But all of these steps are going to be the same. Creating a buffer, make sure that buffer gets over there before we can go on to actually getting it up on screen. So the vertices aren't the only thing that we need, okay? Here's a bunch of random dots. What did you draw today, Mickey? It's not that useful, right? Just having the dots, and that's all we've told the graphics card about so far.
Yeah.
Here's a list of points in space with colors. Wow, that's pretty, right? Right now, it's a collection of colored stars in the environment. That's it. That's all it sees is stars. So we need to give it a little bit more information than that. So a mesh isn't created out of vertices, it's created out of a bunch of polygons that we haven't really told the graphics device about, right? It goes back to our triangle strips or triangle lists, triangle fans, those things, the connections. We haven't told it anything about the connections. It just has 8 dots. So we need to envision each vertex as having sort of an ID, so we know, or name, right? An identification number that's assigned to it that represents its position in that buffer that we made. There's 8 vertices sitting in that buffer, and we'll just label them 0, 1, 2, 3, 4, 5 as we go through. Now we need to create a list of triplets that represent each triangle in that cube using those ID numbers. Okay, so this approach is called indexing. Okay, so we've named the array that holds the indexes appropriately, cube indices there. That might be a little small, unfortunately, sorry about that. And it's just going to be I've just made it an unsigned short array because it just needs a positive number from 0 to whatever. And I've grouped them by the triangles of the faces, and I've color-coded it just to make it easier for people to see there. It's not color-coded in the code, obviously, if you go look at their example again. But this is the line of code that sets up the indices for the multicolored cube in that little template that we set up. So it specifies the 0, 2, 1. So index 0, 2, and 1. So we got 3 vertices out of our buffer. That's going to make our first triangle. Now it's half of a square of the face of a cube. So we need the other triangle, and again it's going to share 2 of those. So the other one is 1, 2, and 3, and that's your other triangle. Now it's important that you get the order of these indices correct, because if you don't have it right, by default you won't see anything if you're looking at it, because it's actually flipped around. And you're going to be looking at the back. It doesn't by default render the back of anything. Why would we need to render the inside of a dice? There's nobody inside the dice. What good would that possibly serve? Why waste time? So by default, it only renders one side of any polygon.
And that's referred to as backface culling.
And that's what backface culling is exactly in this case. And you can do front face culling. It just means don't look at the front, look at the back only, right? And you'd see nothing, except when you looked at the cube, instead of seeing nothing, you'd see nothing from this side, but you'd see the inside of the other side. So you do see something, but it looks like this weird pushed-in box that you see. And that's a common stumbling step for some people, is that they have the wrong backface culling mode set because it's in your shader, right? So they might be borrowing somebody else's shader, not realizing that for whatever reason the guy used the right-hand rule versus the left-hand rule. And what I mean by that is if you specify the vertices, and in this case 0, 2, 1, so if I put my hand at wherever 0 was, and then I wrap my fingers towards 2 and then towards 1, okay, the direction your thumb points is the front of that triangle. Okay, so again, if it was up here and I put my palm at 0 and then I wrap towards 2 and then 1, so now it's pointing at you. So I should see this as the front face of my triangle. But that's with my left hand. Some people do it with the right hand, right? So they want front face this way. But the triangle, if I do the same thing from 0, 1, 2, and 0, 1, 2, my thumbs are pointing in different directions, so you see nothing versus seeing something, depending on what kind of culling you're doing. So something to be aware of, the order of these indices is important for specifying the vertices of each polygon in this setup. So that's how we set up effectively that list, and this it saves us sort of some of the other craziness that might have to go on to make the cube. We effectively now have our 8 vertices, which lists 12 triangles, okay, which creates our entire cube. If we didn't do it in this manner, you'd have to make 36 vertices to do your 12 triangles to do your cube, right? Because instead, all that duplicate data, we use the same corner point for one triangle, two triangle, the top triangle, the other top triangle, the other back triangle, the other. You use it for 6 different triangles, right?
Yeah.
So
it would work, but it would take a lot more memory.
It would work. It would just take more memory because you'd have to duplicate now 36 vertices to specify each for each triangle in the triangle list. So this is using an indexed list of vertices to create less triangles. So now, even though we are going to use the triangle list approach, we're saving some memory because we haven't listed all that duplicate data. Instead, we've just listed the indices of the triangle and set them up in that manner. So that's why we have done it in this fashion, or rather, that's why the demonstration did it in this fashion. We're going to do a similar approach in ours. So at this point, we have now successfully moved all of the data that makes up the cube's mesh over to the graphics device. However, to render it to the screen, we still need a few more pieces of the puzzle, like a view and a projection matrix that represents our camera and our Windows settings. And by window, I mean the screen view. So a vertex shader then interprets the polygons and so on, and which we're also missing, so we're going to have to get to that. So rather than go into all of those things, let's take a look at the difference and similarities between the samples code and what we just went over in the sumo wrestling demo code. We're going to take a look at the vertices in the demo game. They contain position, okay, NUV, and normal data, whereas the sample from the template just has color and position. So I've dropped color in the demo, and I've added in UV and normal data so we can do some lighting and some texturing as well. All right, so that provides all that support we need for textures and lights, just using that extra 2D and 3D vector effectively that we're going to store in there. The code to set up the D3D device to handle these vertices and the extra data, it's still very similar to the sample project's code. The difference is that I've moved it into some other more logical places so that when we build a larger game, it makes a little more sense. It's a little bit easier to locate each of it for each different object. Okay, in theirs it's pretty straightforward. They pretty much just all put it in the same class. Here's all the buffer description. Here's pushing it all out. Here's laying out all the vertices and rams it all out. It's great for looking at exactly what you need to do. Okay, and it's nice laid out point by point by point in that one. That's why I wanted to show you that template. But now we're going to see how I've taken that and effectively moved the code and integrated it into other pieces of the system. So I've created a mesh object class, first of all, and that's going to just be the game's base mesh class. So a mesh, we know, needs a list of vertices, for example. Okay, so, and a list of indices. so we don't have to duplicate that vertex data. That's what's going to be really in the mesh object. Just those arrays declared, that's it. It doesn't actually make anything, okay? It's just that's what's in that base class. From there, I've extended that to have a cylinder mesh class and a sumo mesh class. The cylinder mesh class makes cylinder. The sumo mesh makes our little 8-bit sumo wrestler mesh, or cube. And that's pretty much all there is to it. So we're going to look at the sumo mesh and that mesh object now. I'm just going to pop over to that. So just bear with me here. All right, so if you take a look at this code here, so first off, meshes folder, like I said, I broke things up. We have a mesh object class, okay, and if you look at the header, it just has the render function. That's that part that we saw earlier. We were going through our array of objects. It's saying render, render, render on each one. So as the base thing, that's what this is going to be called. And it does nothing. If we go to it right now, it would just be blank. But that's going to need to be extended. That's why it's marked as virtual, so that we can override it with a proper render for whatever mesh object class this thing is. This class is also marked as abstract, so you can't make any that way, and so on in your code by accident. So the other things we said we needed, a vertex buffer and an index buffer, and the vertex count and the index count for those buffers. So how many points do we need for this object, and then how many indices do we need to make all of the polygons using those vertices to make that object. And then the buffers is where that data is actually going to be stored. And you can see these are generic ID3D11 buffers, and that's why we need to do that description and that buffer layout, is because we don't know what the data is going to be. It's just a generic buffer. You're just asking the graphics device, can I have some memory? I'm going to put some stuff here. So it doesn't know that format. That's why we have to set up that description. That's why we have to, build out that whole buffer chunk first to let it know how the data is arranged, because we're just using generic buffers. So I'll just pop over to the CPP, and the constructor, because again, this is just going to be an abstract class, doesn't really do anything. It doesn't have anything in it itself. The render function does have some codes written in, and it's basically showing you that we'd like to use our vertex buffer. Okay, so we tell the 3D context that got passed in here, so the rendering device we're dealing with, I would like you to please set up the vertex buffers using this description that we pass the address to, and basically we have to give it a stride and an offset, which is the length of the vertex system. All right, so let me just zoom in a bit. This is probably a little bit too small to read. Oh, come on, there we go. There we go. Center that. I've also put up the line numbering, because somebody was asking for that earlier, so now they can easily locate where it is that we are in the code. So the mesh render, as I said, the stride, it's basically how long is the data we need per vertex in this case for this buffer. So I hand it the size of our PTN vertex. What does PTN vertex stand for? Well, really it's a vertex that has our position, our normal, and our texture coordinate data. And I'm going to keep losing, sorry about that, I'm going to keep losing the zoom level every time I switch files here. I want to let me zoom in this time. All right, so it's just a 3 float and 2 3 floats and a 2 float, because we need our position data, which has X, Y, and Z, our normal data, which has X, Y, and Z, and our texture coordinate, which just has a U and a V. So I'll jump back. There we go, back to full size. So now that we've told the graphics device about our vertex buffer, we also want to tell it about our index buffer. Okay, that's our next line there. And you can see that we just need to pass in where it is. So we say mindex_buffer.get, and that gives us the memory address of where it starts, gets passed in. We tell it the format of the index buffer, and before these formats, it's similar to the ones we were using where we were saying RGB 32s. Only in this case, it's just a simple number. So we're just going to pass it in as what effectively that means is a red 16 unsigned integer. So it's just a single number that gives us that many bits of precision. That's all we're going to need. We're not going to have 50 billion indices, hopefully, because that's not the point. So we can pass it in as that. Now it knows that buffer, how big it is, how big the stride is, and it can now use those. And we get to then specify which one of those three topologies we wish to use. Do we want to hand it as a triangle list, or a triangle strip, or the fan?
Yeah.
Okay, in this case, just to keep things simple and how we label everything, we're using the triangle list. It's inefficient, but it still works for our purposes. So we've passed in that primitive topology as a triangle list, and it now knows that every set of 3 indices describes a new triangle, and it doesn't relate to any of the other triangles as far as it's concerned for saving data. So then it just asks for the next one, and the next one, and the next one, and just lays them out all independently. Finally, at that point, we can say draw indexed, which basically just instructs the graphics card to go through a certain number of indices in the array and draw all of those primitive shapes. So we tell it how many we have, and it'll run through the whole thing, the whole array, draw every one of those little pieces of our cube, or our mesh object in this case, since it's not actually a cube. So that's what the base class really just does for us. If I go over to the Sumo Mesh class, I might as well start at the header. There's really not much there.
No.
Okay, again, it's just going and basically setting up that we are a mesh object. That's it. All right, so the CBP, on the other hand, goes through. It needs to know about the graphics device that we're going to be dealing with. All right, we're going to set up a buffer description and our sub-resource data, which we saw the demo sample, the sample doing. We're gonna have to build those. We need to tell it all about the vertices we're going to use. This column here is the positional data for each of the 8 vertices. You can see we have 8 rows, and again, it's exactly the same as the demo or the sample. It's centered around 0, 0, and they're all a half unit in each direction to get all of our points. That's the way I've laid it out, just to keep it consistent for you. And then this next column, though, is no longer color. All right, this is our normal data. So in which way that surface of, if I put my hand down and I put my hand on it and I point my thumb upwards, that's the direction that the normal data is, and that allows us to do lighting calculations. In this case, we want it coming off of the corner of the cube as if projecting into infinity away from the origin. So all I've done is just used a simple 1 or -1 value of the way that point of that cube is pointing in 3D space. So the front right corner, top corner, would be pointing up and over to the right and forward off the cube. So it's 1, 1, 1. The next point over is pointing down, or below it actually is pointing down, so it's pointing still forward, still to the right, but down. So it's -1 for that one. And I've just gone through and done every combination of them. That matches, you can see that the symbols actually match up with the symbols of our positional data. That's an easy way to figure it out in this case for a cube. So our positive point is all positive for the normal. The one that has positive x and y but negative z is positive x and y and negative z for the normal. And that's going to give you the proper layout for the normals of those corners in a cube so that our lighting works no problem. So it's the most basic example that I could think of. That's why we went with 8-bit sumo wrestlers, and there it is. Now the last part is UV texture data. This part, again, it's a little bit different because you're translating a 2D point from a texture to where you want that to land on the cube. Now, what I've done here is I've used the data points, and you can see there is if you want to take a look at the texture file, I'm going to show you this for a second. Resources here. So again, Visual Studios has a nice built-in texture viewer. There you go. This is the texture for the sumo. Now, you might remember not seeing any red lines whatsoever on the sumo. That's because actually what I've done is, because of the index triangle layout, I can't actually use this texture, which is from a game that we'll be doing in tomorrow's MVA. But what I've done is I wanted the top part for the hair on the top of his head so we knew which way was up on the cube. And so I've actually given the coordinates, which are coming right down here and right across the top. Those are the coordinates I've used for all of the triangles so that we get that top head hair piece on top of our cube, and then the rest is just below that by 1 pixel and to the left by 1 pixel, so that everything else on the cube is skin color. And I'm not actually using 3/4 of this image. And that's the sort of neat thing about the ability of the UV textures, is that you don't have to use a whole texture for any given object. So you can end up doing, if you've done 2D games before and done texture atlasing or sprite sheets, it's the same kind of idea but applied to maybe multiple 3D objects or an animated 3D object. You can tell the vertices what part of the texture they should be showing at any given time, and then you could move through the texture or change what they see on that texture itself, or on the model itself from that texture. So that's what these values here are telling us. Okay, now the top left corner in UV is 0, 0, right? The far right is 1, and the bottom is 1, so that it's a little bit different than maybe the coordinate system you would expect. 0, 0 is top left corner, and 1, 1 is bottom right. All right, so not to get confused there. And all those numbers punched in here give us that shape that we want. Now from there, that's great. We have all of our vertices lined up with all of the lighting data, with the texture data we need. We now need to go into actually making the polygons using those vertices. So again, we have our little triangle list in groups of 3s saying which indice, or which vertex rather, so which one of these 8 rows do we use to make this triangle. So 0, 1, 2, so we're using this guy, then this guy, then this guy to make that first triangle of the negative x face. And then we need to use 1, 3, and 2, so these 3 here, to make the next triangle, and so on through the system. So each one of these is a triangle on its own using the vertices from that list, exactly as the demo sort of did. My ordering is slightly different for what I was doing, also partly because of how I do the texture UV mapping. After that, again, we have to fill in our vertex count. There's 8 of them. We have to fill in our index count, which we can just calculate by getting the array size of the indices. And now we have that data. We can start building our buffer description. Okay. Some of the flags that we set before aren't in this one that compared to the ones in the sample. And there might be a new one too, just because of different settings that I needed. But these are pretty much going to be your basic settings. You're going to tell it to use it as default. There are some advanced buffers, descriptions and usages that you can set up, but we just need a basic buffer. The size of it is going to be, well, however many vertices I have, multiplied by however big one vertex is in terms of my PNT data, my position, normal, and texture data. All right, so I've just taken the size of that structure, multiplied it by the number of vertices that you have, and that is your byte width for this buffer. Again, we let it know that it is a vertex buffer, and that's what we would like to bind this to in the graphics graphics systems hardware. We'd like to bind this to a nice vertex buffer so it can utilize it as fast as possible. We don't need the CPU to read or write to this data anymore, so we're going to set the flags to 0. Again, that's an advanced feature. The system memory that we should be pointing at is wherever we've stored our sumo vertices in our system memory in the game, so we give it that reference to the array. Of course, we try to create the buffer, and it's always nice to see if it failed, just in case your graphics card doesn't support whatever you're trying to do, or the hardware you're working on doesn't. So that's what this sort of a helper class does, is just see if an error occurred and then present it to you in a nice manner. But otherwise, we're just creating the buffer like we saw in the sample code, pass in our buffer description, the initial data, and that vertex buffer itself, and that will create our buffer for us. Again, we have to make a buffer for our index system as well. And so again, how many indices do we have? In this case, it's an unsigned int, or unsigned short in size, so that's word. So size of word, get that, multiply that. We get our size of the bit width for that buffer. We tell it it's an index buffer now, so it uses it in a different way. Again, no special CPU flags or anything like that. We point it to our system memory that has those indices, and we create that buffer as well. So really just this part is the only difference between the two create buffer commands, because we've effectively just overwritten our previous buffer description variable or structure with the new information that we're going to use to create that buffer. So that would create our sumo mesh on and push all that data that it needs to know to the graphics device for us to sort of see what's going on and render it at some point later on. All right, so I'm going to step back out of this. I'll go back to the slides for a bit. There we go. Perfect. So we've taken a look at that sumo mesh, setting it up, getting all the vertices in there, getting all the connecting lines for your polygons, for the triangles to lay that all out. Now, in order to manipulate that and to even see it, we're going to need 3 4x4 matrices, okay, that are going to represent the position of that object and its rotation and tumble and anything else, its scale. Okay, that's one of the matrices. Then we're going to need another one for our view, which is effectively our camera. And then we're going to need another one for projecting that information into a 2D space to show on the screen. So in order to do all this manipulation, all that, we do need these 3 matrices that we're going to effectively apply and multiply to each of those vertices when the system goes to render them. So the 4x4 matrix, it's basically is just your basic transformation matrix. If you've done linear algebra or some complicated math like that and had some fun in that class, I'm sure you've seen how a 4x4 matrix is laid out with the identity matrix, for example, is 1 all the way down the column and everything else is 0. The first 3 along that major axis control your scale, and rotations are all done in different ways, and transposition or translations are usually, depending on if you're row or column major, at the bottom or at the far side. Those are those matrices that we're going to use here with all of that data plugged in to manipulate that vertex to wherever it should be, and then to manipulate it according to the camera, and then finally to your screen to present to the user. Now, do we have to do all that crazy math all the time for every single vertex? No, obviously
Thankfully,
your system is going to handle that for you. You're just going to set it up. The graphics card is going to grind it out way faster than you can, and then it's going to get it up on screen for you. So typically, that first matrix that converts the model's coordinates into world space, like where it should be, is known as the world matrix because it takes you through that process. Mm-hmm. Now, that's not to say that there is one of them. There isn't. There's effectively one of them for every object to get that object into world space. Mm-hmm. All right. So when we built our cube, for example, it was all centered around 0, 0, 0, and we built it out as if in local position to that origin. But that doesn't mean every cube exists in the center of your game world, no. Right? Even though that's what that is. So the world matrix is going to take that local space 0 to 1 or 1 to -1 position or whatever you did to model your indices and vertexes, translate them into where it actually is in the environment, what size it is, and so on. So that's the principal point of this world matrix and what it does or how it helps us out. Now, typically, we have the next one is known as the view matrix. It converts that world space coordinates into camera space. So again, it's going to do same kind of math, only it's from the point of view of where the camera is. So now we're taking that into perspective, and we're figuring out where is the camera looking at this scene. Oh, he's actually looking at the left of the cube. So I shouldn't be rendering it just as if the cube is facing the camera. Now I got to render it sideways. So it's going to do those translations to get everything from the point of view of your camera looking into the world now that everything's in the world position. And so that's what that one does. And then finally, the projection matrix converts the coordinates from camera space into screen space to actually get the pixels, the right pixels, which gives you, we call it a projection matrix. There's also, sometimes this is called a orthographic matrix because sometimes, such as in 2D games, you don't actually care about depth, like how far an object is away. And in a projection matrix or a perspective matrix, that we can use as a projection matrix, it does matter. One hand in front of the other, one looks smaller than the other from the point of view of the camera. So the projection matrix can sort of shift between orthographic or perspective mode, whichever one you want. If you want depth or you don't want depth, you can bend your FOV, your field of view, okay, in many shooter games. For example, you have control of that to like widen it so you can sort of get more peripheral vision if you've got a widescreen monitor or whatever. Or you can give yourself a fisheye lens so everything's all, like bubbly as if you're underwater and zipping by you at weird angles. That's all controlled in the projection matrix. That's what we're going to be dealing with in there. So again, because that model matrix changes before we render each object, the game is going to store that one separately from our other two. Right? Every model needs its own world matrix. So we're going to put it in one of those different buffers that we talked about earlier because it gets updated more often. The view one maybe gets updated once per frame. So that's going to go in that once per frame buffer that we talked about. And we saw that. We saw the camera get view. They were pulling that view matrix out. That's exactly what it was doing. It was requesting this 4x4 matrice. So that's where that's going to go. So projection and view matrices are separate and usually stored in a different area. The world matrix is stored per object to represent everything that object has, and it gets passed in every time we render a new object. So there is a little bit of difference in how we handle those and where we store them. Now, one other thing to note is DirectX Math does use row major matrices. Okay, so it can be used directly with HLSL, the high-level shader language matrices that are defined with row major as a keyword. So that they're just like the back face calling, front face calling, you have to look at your shader and which way is it dealing with. Well, in this case, you have to look at the shader and go, is it trying to do it in row major form or column major form? And depending on what is set, it'll either work perfectly with DirectX Math, or you'll have to do a transposition of the matrix to effectively flip it and invert it so that it will work in column major form or vice versa. All right, so you'll see in our demo actually that we do transpose these matrices every time we go to use them, and that's to get, because of the shaders, the order it expects is different than the default DirectX setup. So just something to keep in note. If you see things moving in the wrong direction or not manipulating right, it might be simply because of that, and you'll want to take a look at that. So we're going to inspect the camera class, which is where I've put the view matrice, for example. It's in the camera class. It makes sense for it. That's where you would expect to find it, since it effectively is the camera itself. Oh, I forgot to exit. There we go. And shift over. All right. So let me grab the camera class here, which if you go under game objects, that's where the camera class is. So we have both the header again and the CPP. And if we take a glance at the header, and let me blow this up for you so it's a bit easier to read. There we go. Again, it really is just about defining the position, the orientation, and the viewing frustum of a camera looking into the 3D world. So it's going to generate both our view matrix and our projection matrix. So we're going to need helper functions for that, so that other functionality, such as when somebody crushes the screen, it can set the projection parameters for our field of view, or our aspect ratio, more notably, would be the one that would get changed if you manipulated the screen size of the game, and so on. So all of those things go in here. For example, for the view projection, it's a camera, so we need to know where it is. That's known as the eye position. So again, it's just a float 3. Where is it? And then we have, where is it looking? So what is it looking at? And finally, which way is up for the camera? Because you can look at something, but you can hold the camera upside down if you wish. And that's useful for if you're doing a flight game and you want to do a barrel roll from the cockpit point of view. You just manipulate this up vector to constantly point from up to right to down to left and back to up. And he did one full revolution around the rolling axis. So that's a nice way for us to control what our camera is going to be viewing, and it changes our view projection. And the projection parameters, like I said, field of view, aspect ratio, the near and far clipping plane. Near and far clipping plane, that's near plane is how close can something be to the front of the camera before it doesn't render. And this sort of simulates, I'm sure you've seen this in news footage, somebody be carrying a camera and eventually the guy walks right into the camera. But he got too close. He hit the near plane. That's that near plane there. When they bang up against the camera, they got too close, they hit that near plane. Now, we don't physically have a camera, so you'll just see through the object as it passes through that near plane. You've probably seen that in other games, most notably, third person driving around smashing up action games. You can zoom in to try to get a closer view of your guy, or you ram him into a corner and the camera punches in. It'll go inside his head, and you'll sort of see the cutout, and you'll see the eyeballs floating around, right? That's that back face culling, but also our near clipping plane is removing the geometry right where the camera is so that we can see at least that far forward. And that's what you're seeing there. The far plane is how far away can we still see something, right? So we want to specify how close for that front of the camera is and how far away it is, and that's really what we're doing there. So those are just some basic camera stuff that you can manipulate. And again, we have our helper functions for changing just the look or just the eye position of the camera. And then we have all of our matrices and all of our float vector forms functions. So could I please have the position of the camera? And it hands it back as a float 3. Could I get the projection matrix? Could I get the view matrix of the camera? It'll hand them back as XM matrices, and so on and so on. If you needed to know what the near clip plane or the far clip plane was, you can ask for that, and so on and so on. And here we are storing our actual 4x4 matrices that hold that view matrix and that projection matrix data. We also have an inverse view just for usability purposes, so we don't have to calculate it on all the time. We can just grab it internally there and store it and use it maybe a couple extra times per frame before we have to recalculate it. Then we have the eye position, look position, up position, and so on, all the internal settings for the view angle, the near plane, and all of that. So it's as basic as you can really make a camera system, but still have the functionality you're going to need for a 3D game. That's what I've really trimmed it down to for all of you to use. Now, in the camera class itself, when we create a camera, it just sets that view parameters up to some basic defaults. So the default position is going to be the origin of the world. The default look is down Z, because typically in 3D games we consider Z being positive Z being into the screen. Sometimes it's positive Z is out of the screen, but in this case I've set it to into the screen. So the camera starts set up looking in that default presentation that we would expect, and of course up is Y, so we say 0, 1, 0 for the default up vector. And then we just set the projection parameters, so the near clipping plane is going to be 1 unit away, the farthest we can see is 1,000 units, and then things just stop rendering beyond that, and the FOV is going to be 1/4 pi in this case to start. So going through these functions, the most important ones really are just the ones that are going to give us that view and that projection matrix, and they're just going to hand it back as is from internally. There's also a world one, but that's just where the camera is inversed. It's not exactly, we're never going to render the camera, so we don't need to worry about that. In some games actually they do when they have multiple cameras. Sometimes you see like a camera icon where the other camera is and so on, but not in this case. The rest of these are all just helper functions that just give you the specific data you ask for, and that's it for the camera. So the camera really just, the most important thing is that it holds this view and projection matrix for us to use when rendering everything else in the game. That's really what the camera class is all about. All right, so popping back here now. So now we know where we're going to store that data. And now that we've seen where those matrices live and how they're stored and we've talked about what they're used for, we're going to need to alter that world matrix right before we render an object to the actual rendering device. We basically have to transport that part or that version of the world matrix to the graphics card so it renders all of that vertice data properly for that mesh. So the alterations need to be stored somewhere. So we've abstracted the fact that there's only one world matrix at a time on the graphics card, and we've instead created a world matrix in each game object. At that point, most games are going to create a class called game object, so I have done so as well, or they just call it object or whatever, base piece or something like that. And that's going to be our base class for all objects in the game, and since all objects in the game have a position, generally speaking, and a rotation and a scale, that the major thing that this class is going to store is simply that world matrix for any object that extends from that class. That's all that's going to be in there data-wise. So that's where we store it. So we got our view and our projection in our camera class, and we're going to have an individual world matrix, effectively, data in each game object that we create. So our two sumo wrestlers are going to have their own world matrix in their game object classes, and our cylinder for the base, for the ground, also has its own world matrix that we render in that fashion. Now, once we have all of those in position, we need to create a series of constant buffers that we've talked about before. The never changes buffer. All right, we got the change on resize buffer, the changes every frame buffer, and the change every primitive buffer. So to declare those, again, they're just default buffers. Okay, just like the vertex buffer was a default buffer, the index buffer was a D3D11 buffer, they're all just basic buffers. And that's why we need to hand descriptions along with the data so that the graphics card knows how to interpret it. So each one of these, again, are just basic buffers. So we've declared them with a COM pointer pointing to those interface structures that are going to be our basic buffer. So we start by creating the buffer description. So D3D11 buffer description again. Then we use md3d device create buffer with that description to get it over onto the device. And finally, you fill in the data via your original COM pointer that we've declared right here for that buffer whenever it changes. So if I wanted to change the window size because they've resized it, I would talk to the m constant buffer change on resize dot projection matrix and change the field of view or the aspect ratio or whatever in there because it's going to be in that buffer. So these pointers now are what we're going to manipulate whenever we need to effectively manipulate the data that's on the device itself. Okay, because now we've told it to look at this memory and constantly send that over whenever required. Okay, so inspecting the game object and the children. I'm just going to do this quickly again, pop out here for a second. We're just going to, now that we have that game object class, I just want to point you at them and sort of show you what is in there. So here is the game objects header. Again, it's pretty basic. It's going to have a render function, which really is just going to call the game object's mesh. Okay, the game object is going to be made up effectively of the mesh of the object. So in this case, in the future when we make our sumo block, which you can see right here, a sumo block class, it's going to extend game object, but a sumo block needs a mesh and where and what it is positionally. So there's the mesh object pointer, and we're going to have our model matrix, I've called it in this case, but because it's currently just for this model, which is what's going to become the world matrix when we go to render this model. Mm-hmm. All right, so that's just sort of the labeling difference. So when you want the model matrix so that you can take it and effectively convert it into the world matrix, that's the thing you're going to be after. And of course, we can just change the position or the velocity as needed. And there's this update position because all of these game objects are going to need their position to be updated. So I've made that virtual function for you to override for any new game objects you make. And let's just jump over the sumo block here. Oh, sorry. Go to the header for the sumo block. And again, this might be a little small, so let's just zoom in there a bit. There we go. So the sumo block extends from our game object class. Okay, it needs to take in its position. And in this case, a sumo, we're going to give it a target, the other guy, right? This is a guy you should be like facing, you should be charging at, you should be pushing. So the constructor takes a position and that target. And same thing, we could change the target in case you want to put a multiplayer mode in later, or like a holdout mode where there's 20 sumos all at once and they're all trying to push each other out as your own expansion to the game, then that's fine. So I just provided you a function to allow you to change the target on the fly.
I kind of want to see this 20 sumo mode.
could be entertaining. I don't know how easy it would be. You might get beat quite often, but it'd be cool. So what we've added here is that the sumo also needs a rotation matrix. So I've given it one. It needs to know about that target. And finally, it's going to have an angle that represents the rotation that we've put in that matrix. So these are something that the base game object didn't have. Mm-hmm. And so I've just expanded and put them in here. So the target controlling part and storing that information, that's all built upon the game object, which does still have our model matrix, which becomes our world matrix, and so on, and our render function. So if we jump over to the CPP, and I actually have to open this so I can zoom it up again. There we go. If I just scroll down here to our update position function on line 40, we check if we have a target. If we do have a target, then we want to always make that sumo wrestler face the enemy. I mean, you don't, running sideways at him or backwards. You don't see that in sumo wrestling. It's all like facing the guy, pushing as hard as you can, that kind of stuff. So we're going to do that for our little cubes, we're going to make him rotate to always face the position of the enemy. And to do that, we basically just take our target's position, which we have a reference to him. So we ask for his position in vector form. Okay, that's all that this function does, as opposed to the position in float3 form. Mm-hmm. So we're grabbing it in vector form because in DirectX, you can subtract two vectors and it'll return you a vector. The minus sign is overloaded to do that, whereas a float3, it wouldn't work out. So we've kept it in vector form, and our position I've asked for in vector form, and that's why there's nothing in front of this. So this is just our position, our target position. If we subtract our position from the target position, that gives me a vector facing my target. I can then normalize that so it's just a direction. And then what I'm going to do is I'm going to calculate the angle between two normals, in this case our direction, and the forward-facing direction of the model, which I've decided is x, positive x. All right, it's going to measure the distance, or the degrees rather, between this, or radians actually is what it'll probably be in, between our facing and the current direction we need to face to get looking at our enemy. So that answer comes back. We save it as our angle internally. We're then going to see if we're in the upper arc of the map. So because of the way the system returns it, it's going to give us a 0 to 180 because it's going to be the closest angle to get to that. Mm-hmm. So if I have to do too much of a spin around one way or the other, it's going to give me the short angle, and I'm not going to turn in the right direction. So you'll only be facing your target half the time. Otherwise, you'll start to rotate the other way around to face him again when he's the other way. So I've just put this little check in to verify basically if the Z component of our direction is positive, then I know we're on one side of the arena map. And if it's negative, I'm facing the other side of the arena map, and I'm just going to invert the angle into the negative version of it. And that's going to allow us to do full 360-degree spins in either direction to face our target automatically. Again, we're not controlling this. The code is just going to be doing this, rotating the cube to always face the other cube. So then what we have to do is we have to build our new model matrix, that world matrix, to render them. And we do that by taking any scaling we wish to do to the sumo. In this case, I've made the cube the size I want. So I need no scaling in X, Y, or Z. So I just say 1, 1, and 1 for each X, Y, and Z component. And say, could you please, DirectX, give me a scaling matrix, which will be effectively a 4x4 matrix. It'll hand that back using this scale of 1, 1, 1. And I'm going to multiply that matrix by our rotation matrix around the angle we need to rotate. He only rotates around the y-axis, which points straight up in the air. So I can make a matrix rotation y using that angle. Again, these functions, these XM matrix rotations and things like XM vector set, those are all part of that DirectX API, and it is different than DirectX 10. That's why, and previous versions. Some people were asking, you know, what are the differences? This would be one of those things you would have to change. Okay, you would have to change any of this math to do it the old way in whichever way you were doing in whatever version of DirectX that you're rolling back to. So that is one of those differences that somebody was asking about earlier on in the chat. But all of these are from our XM Math API. And finally, after we've rotated, we've scaled, we've rotated, now we actually have to move him to wherever he is currently standing. So we just make a translation matrix using his position of X, Y, and Z. And that finally combines together into our full 4x4 model matrix.
It's probably a good thing to point out too that the order of which you do these operations is very important.
It is important. You can't just throw them in any order. Yeah. Especially when you're dealing with, for example, two angles. Okay, rotation around Y or X, or just Z and X. The order does matter. You may have to play with it a little bit. When you get into something complex like that, actually look up how to build a world matrix out of those things. There's also an orbit rotation.
I was going to say, I remember it by ISROT, right?
Yes,
the identity,
ISROT.
Scaling, rotation, orbit, translation.
Perfect, exactly. For those that you don't know, he was a student of mine at one point, so I'm glad to see that he can quote that.
It's stuck.
That's good, it's stuck. So yeah, ISROT is one way to actually remember that kind of information, and the order in which you should be doing these things. So again, you can look that up whenever you need to do something more complex. You'll get all that information, and you'll be able to lay it out as such. Okay, so that is how we build, for example, our Sumo's Worlds Matrix. at any point in time, and allows us then to pass that to the graphics card as well as our view and our projection from the camera class. We now almost have everything we need to finally render something to the screen. Again, there is a lot of setup, but once you have it all, it does work quite nicely. It fits together relatively easy, and expanding on that to do other objects, and I hit the wrong button, isn't that difficult to do. Sorry, I just got to jump through a bunch of slides to get us back to where we were. I forgot the shift button. Whee! All right, so where were we here? Manipulating an object. Perfect. All right. So now we're on to rendering the mesh. We have the mesh. We have everything we need to see the mesh. We have the ability to translate the mesh around and move it in 3D space. The next step on our path is rendering that mesh to create a basic vertex and pixel shader using the high-level shader language, HLSL. Both can be written in a single file if you choose. You don't have to write a vertex shader or pixel shader in their own. And most people will write them in separate files just so that it's easy to manipulate and jump between them. Okay, so the vertex shader, there's a vertex shader HLSL file and a pixel shader HLSL file that you can find in the project there. There's actually two other ones also in there that are flat shaders. Basically, they strip out lighting.
Yeah.
Okay, that kind of thing. Or they do it in a different manner. So we're also going to create a separate file just for those buffers to help manage them. It's easier to find them that way. Some people will stick them in with their shaders, but then when you need to change the layout of your vertices, for example, now maybe you want color data instead of texture data because you're shifting to a mobile platform and you don't need all that detail. You'd have to go and find whatever random shader file has the buffers in them, and they could be in more than one place. Right? They might have, so it's easier, I find, to set up a separate file. In this case, we've just labeled it as a .hlsli file, okay, for that information purposes, and we've called it constant buffer. So that's what's in the constant buffer HLSLI file. Is just going to be that data layout. Now, what do vertex shaders do? I've mentioned them previously, as an introductory sort of overview. It's a process. The process in which we take a mesh's vertices and we can perform things like transformations, skinning, or lighting on it, and then hand it off to the pixel shader to do some more overlays or something like that. So you can do it for facial features. You can have them scrunch up their face and so on, like this character here smiling and frowning and doing all that, just by manipulating the vertices with a vertex shader. All right, so we're not actually changing the model in terms of in the code, but the shader is doing that in some manner. They always operate on just a single input vertex, and they produce a single output vertex. So it's a one-to-one. It doesn't create anything, not like the tessellation system and the geometry shaders that I briefly mentioned and that. They make more vertices, okay, or more geometry. Vertex shaders can only manipulate already existing ones. That's what they do. So this stage of the rendering pipeline has to always be active, or we'd see nothing. So that's just sort of, I just pointed it out because it has to be there. And then pixel shaders lets you do crazy effects like this, where it's not about rendering the thing, it's about changing what you have rendered now into some stylized approach. So pixel shaders are also sometimes known as fragment shaders because they're now dealing with a piece of your overall picture. Okay, so they can compute color and other attributes per pixel or fragment. And they can alter the depth of the fragment, for example. We do this for Z buffering purposes, and it's a way to remove geometry we don't need to see and so on. We can use different techniques like that. And we can also create a bunch of two-dimensional post-processing effects like blurring or mosaicing it, sepia tones, swirls, embossing, whatever you want, colorizing, so you can make it green fog like those penguins in the top right, or monochroming it by removing all the color like the penguins in the middle. You can do all of those kinds of post-processy like effects now that the image is rendered. That's what the pixel shaders really deal with. So we're just going to jump in and take a brief look at those shaders. We're not going to spend too much time on them. I've provided them with you. They will work seamlessly, basically, hopefully for you. Bringing in textures, you can and manipulate those and see what they look like. You could also go back to look at that original sample with the multicolored cube, look at its pixel shader and its vertex shader, which are even more simplified because they don't have the lighting data or the texture data. They just have the vertex position and color information. So if you just want simple toon colored objects, you can go use those. Just bring them in, load them in, see where we're loading these HLSL files. Just do a search through the code, you'll find it. HLSL doesn't come up very much, especially .HLSL. So you'll find the two spots where we're loading it. You can swap in those other files and then refer to them similarly, but you will have to change the vertex buffer data because of the layout of the vertices is going to be different and so on, because you'll need that color data. Not so much to remove the normal or the other, the texture coordinate. It doesn't matter if there's extra data, but you need those two that it actually expects. So I'm just going to pop over here to the code. I'll take a quick little gander at that. Right, so here we are in the code base. And if I go down to shaders, I open this up, you can see there's 5 files in here, one of which is our constant buffer file, index file, basically, that has all the information in it. And let me zoom this up a bit. There we go. So what do we store in the buffer that never changes? Well, the lighting position, actually, in this game. I don't move the lights. The lights don't move anywhere. They don't change colors, so they never, ever change, no matter what. So we put that in that buffer. We now never have to update the graphics card again with that information. Once it has it, it'll be happy. Our change on resize, just the projection matrix, because that changes our aspect ratio. So that is something the projection matrix controls, so we need that. Things that change every frame happen to be our view matrix, the camera. Where is the camera? That changes every frame. Then the constant buffer changes every primitive. That's our world matrix, our mesh color, diffuse specular color, which is our lighting colors that we're going to be using, how the lights affect the object, and so on. Those change every primitive. And then finally, also the vertex shader input. This is where we tell it you're going to get a position, you're going to get a normal, and you're going to get a texture UV, which will match the buffer description elements. If we go and look at those, you'll see that unlike the sample, which only had position and color, I now have position, normal, and text coord 0. Okay, that's what those refer to, that same setup that we did with the buffer descriptions, but now we're going to have 3 elements instead of 2 elements with similar settings as before. All right, so that's what that looks like. Now, we're going to look at the pixel shader. Actually, no, I'll go to the vertex shader first. Since it does happen in that order, vertex shader does happen first. You'll see that the code more or less, looks like C++ still, but it is written in HLSL. So one thing we expect is the vertex shader manipulates a single vertex and exports a single vertex out. So we bring one in using that vertex shader input structure that we just saw a second ago, and we're going to make a pixel shader input structure. We're going to call it output because that's the output of the vertex shader. And right now we're just going to set it to 0 or null as that class. And we now start manipulating the vertex. In this case, we're going to change the vertex position by taking the input position. So that'll be in local coordinates. So it'll be, for example, the top left or front left corner of the cube is 0.5, 0.5, 0.5. That's going to be multiplied by our world matrix for wherever the sumo is. And that could translate it to 50, 25, 10. Then we take that, we multiply it by how the camera is viewing this object in that world, and that'll change its coordinates again. And then finally we multiply it by the projection matrix as well to get it into screen space. So that vertex now has gone from local coordinates to world coordinates to the camera's view coordinates to the finally where it should be on screen coordinate. All right, now you see that we have to use this mul for multiply function to actually do this work. Okay, we can't use the multiply symbol. You can't use a star for that in HLSL for what we're trying to do with this vertex and these matrices. So we use the multiply command or function effectively and pass in the information to do that. Now the texture coordinate, nothing's going to change in this shader. We just pass it along. We're not going to manipulate it at all. We then have to compute our normal. Remember, we had those little normals pointing off all the corners. Well, they need to be translated into the world view and then the camera view and so on, so that we get it from the right direction to calculate lighting properly. When you look at a shiny surface from a different angle, you're going to see glare. For example, there's a light here beside me. I can see glare coming off my hand, and as I tilt my hand, I get a different glare. And that's because that normal on my hand is moving around as well, according to where I put it in the world and how my eyes are viewing it. So those two things have to be multiplied together and combined on that normal, and that's what that line of code there is doing. It's outputting the new position and coordinates of that normal for that vertex. Then next, the next line of code here, vertex position and view space. So we're going to normalize it for the pixel shader's sort of range of values. So we're setting the vertex to eye position by taking the input position again, multiply it by the world, multiply it by the view, but then we're going to invert the x, y, and z values afterwards. So that's the direction from that vertex in space to our eyeball or our camera position. Okay, that's just useful for certain lighting effects, so we're just pre-calculating that now while we're in here. And then finally, we need to know where all of our vertices, or all of our lights are. So we take our light position arrays, which we haven't looked at, but we've basically just hard-coded in 4 lights, and you can just right-click on this and say go to declaration. It'll show you where it is. And we've just set them up in the world. You could change those if you want, you change their colors and so on. But we're just taking that position again, multiplying it by where the camera is, and then we're using the vertex to eye direction that we just calculated, adding that on to that normalized direction for the light, and that sort of gives us our skewed perspective of that light from our camera point of view, and so on. That's going to be interacted with that vertex, and that's going to be used by the pixel shader, which if I jump over to right here. Now this is going to get into lighting topics and so on. We're not going to really do anything there. And I'll blow this up again. There we go. So we're not going to spend much time in this. We could go over the different ways to do lighting and different types of lighting and so on, backlighting and so on. Of them, yes. And there are lots of them, directional light, specular lighting and so on. So really this is just taking that output, but now we rename it input, but it's still that pixel shader input structure, and it's now using all of the vertex to light 0, those things we just calculated, and manipulating them, doing dot products and all this to calculate the lighting in different ways, to do our specular lighting and so on. We multiply our color by the amount of light being reflected in that direction to you and add that in, and then we sample the UV coordinate for this vertex from our diffuse texture, okay? And we take that, we're going to multiply it by the diffuse color, which is from our lighting component and so on, and the diffuse luminance, and then add on our specular hotspot kind of reflective shiny surface light to that. So it's going to get the color from the texture at this point. That's what this this function does here. So diffuse texture is our reference to that texture, whatever it is that we're using. We're going to sample it at this position, okay, and we're going to multiply that by any color tinting from lighting that we have and pump it out. And that's really what this shader does. Obviously there's a little bit of complicated math and doing all the geometry behind that to figure that out. Don't worry about that. The point is to show you, these are the kinds of things we can do with a shader. They're pretty basic. In the end, a vertex shader manipulates vertices. A pixel shader manipulates the actual color of that point on screen and so on. All right, so let's pop back now, and we'll continue on. We're almost done this section. There's just 2 more slides to go effectively, and then we'll take a little break. So make sure I hit the right key combination so I don't have to scroll through everything. All right, so we've looked at the shaders, and now after the shaders, we have everything we need to render an object. Okay, that is a lot of setup. That is a lot of work, but the reason why we did a little bit of that extra work is to make it easier later on. Building those mesh object classes, okay, and those other classes like the game object and so on, and the ones that extend from it, just allow us to manipulate that data much easier. You saw how simple a lot of those classes were. There weren't a lot of functions to them. It was mostly variables being stored, some helper functions to get the values in different formats, and that's it. And really that's what you want. Nice, simple, easy to manipulate code, easy to bring to your next game and continue on, so on and so on. And that's really what we wanted to do.
Well, you're building an engine is what you're doing right
yes.
now. You're literally building an engine that you can use later on in many games, right?
Exactly. So. It's about building that foundation again, right? Yeah. Just like you said, building a foundation for a 3D project that you can then bring out and do multiple things with. Now, with that in mind, instancing and referencing, this is a way, now that we have the separation of data in terms of where is the object, how is it rotated, from the physical piece of the game, which is the vertices and the individual points and so on. What we're going to do is that sumo mesh, we're going to bend space and time so that we can use the same mesh, the same chunk of memory, but to draw multiple sumo objects all over the screen wherever we want it to. Okay, so that instancing, I'm going to make an instance of something, so it creates an object from the same base template as another object as before. But referencing is, could you please refer to this guy when talking to whoever? So what we're going to do is we saw that mesh reference was in the GameObject class, so we only need one sumo block mesh, and we need multiple sumos that then refer to that same mesh. So let's just pop into the code, and I'll show that last bit before we wrap this section up. Oh, and I forgot to exit. There we go. Boop. Okay, so again, what we're going to do here is if we look at sumo block, actually we'll just look at the header. So the sumo block has the game information. It extends from game object. Okay, so it can be you, and then I'm the other sumo. All right, we're different people, but in this game they're going to look exactly the same. So we don't need two different bodies. We just need to be in two different places at once, and so that's what we're going to do. So the sumo block doesn't have any of that information. It has where each of us are rotated and who our enemy is. And if I go to the game object and pump that up, the game object again has the mesh information down here, and it has the model matrix where you are, where I am. So the game object as a whole has where it is and what you should be, but then it simply references, okay, via this pointer, this managed pointer, a mesh. And it's going to be the exact same mesh, both of which are going to use the sumo mesh right here, which again has all of our, I'll go to the header, doesn't really have anything except for our actual pixel layout, our vertex and our index layout for a cube. We're both cubes. But there's no positional data here. So where we both are at the same time doesn't matter. So if we jump over, and I know this is a lot of jumping around, if I jump over to the game class down here, sumo dx cpp, and we look at where we set up the game to start, all right, that would be in the initialize right here. There it is here. Starting at line 53, we can see that we create a sumo block instance, all right, for the player. We give them a position, and we push that into the render array. Then we create an enemy sumo block, which AI sumo block just extends from sumo block, so it has an AI and the player can't control it. And we go ahead and we push that one in. But neither one of those knows anything about the mesh yet. We haven't created a mesh for those things. We've just created that class. Nowhere up here do we create the actual instance of those meshes. So both of their meshes effectively don't exist at this point. If we go down here just a little bit further, we create a cylinder mesh, or a cylinder game object for the floor. We create our camera, and we continue on. What will happen is later on we're going to actually build that instance of the block itself, which I'll just jump to here, sumo mesh. Oh, and I'm not even in the right file, so I'll just do that. Because I've forgotten what line of code this is on. There it is there. Thank you. There. Get out of there. All right, so in the game renderer, it's probably a little bit too big. There we go. In the game renderer is where we're actually creating the sumo mesh during its initialization. All right, and we're letting the sumo mesh know about the device. And all we're going to do is we're going to go through every object, and we saw that we were pushing both the player and the enemy sumo into that render object array. So we're grabbing the render object array from the game, and now during the initialization of the game renderer, we're checking what kind of object he is. Oh, he's an enemy sumo. You know what? Your mesh is this mesh that we've made. And if I just scroll down to here to the player, sumo block, he uses the same sumo mesh. I haven't created two instances of the mesh object. It's the same mesh object, and it doesn't matter. But both those both those player and enemy now will draw based on the same object. So that's just a way of referencing one model. Even though we have multiple instances of the sumos, we have one model. We don't have the extra overhead for 3 different models or anything like that. And that's a common practice, setting up things in this way where we have the separation of the data for that character versus his actual physical look and feel and textures and so on. And that allows us to make many, many different crates that you can crack and break all independently, power-ups laid all over the environment, enemies that all look the same. Now, you usually don't want that, but...
Lots of trees.
Yeah, lots of trees, exactly. That's a great one. Trees everywhere, but you don't want to load 5,000 vertices for every tree times 5,000 trees. That forest would be massive and unrenderable, basically, at this point in the game. So this allows us to have all that stuff. Okay, so that's a big overview. It is a huge chunk to get something rendering, to see something on screen, and all of that.
Welcome back. It was a nice little meal break there. I got a little bit of refreshment into me. And I'm feeling ready to do some more C++ and DirectX.
It's good.
Yeah. So what are we taking a look at now?
Well, we're going to look at state management is the next section that we're going to be previewing. And we've seen a little bit about the state management already. We've seen how the update state, for example, goes through a couple of different states and progresses the game through. We're just going to talk about what a state is, what a state machine is, and how we develop a game to sort of use those things. So what are states and state machines? That's the first thing we're going to cover. Then we're going to look at how to implement them into a DirectX game or really any program in general. And then we're going to look at, of course, the demo's implementation of it in the Sumo game. So what are states? Most games and entities can be thought of as progressing through multiple modes or states. That's effectively what we're talking about. So modeling states and state changes can help to manage the complexity of games and objects. All the states can be entered by some way, but you can't necessarily leave all states that exist. For example, if an enemy character guarding something in a stealth, action game or whatever, one of the more popular ones, he could be just hanging out with his weapon, whatever, sitting there, minding his own business, and a little box bumps into him or scratches along the floor a little bit too loudly and goes into that, exclamation mark interactive state, starts looking around, wondering. He's now transitioned from one state to another, and he's interested in the world. Just sees a box, maybe the box is still moving, gets upset at the box because boxes shouldn't move, and starts filling it full of lead or something like that. That's a state. Each one of those is a state, and we transition from each one. And of course, if you didn't notice the box was moving because the player stopped in time, he might go back into his idle state again and just hum and haw and stare at the birds. So there's always ways to go in and out of states, but not all states can be exited from. For example, when our little snake in the box, for example, maybe comes up behind him and gets him finally, once he gets close enough, he's going to go into his death state, he's going to play a death animation, fall and groan and roll around on the ground, and that's it. He's never getting out of that state again, he's done. So not all states can necessarily be exited. And you can only be really in one state at a time. Generally speaking, we don't allow you to be in more than one state. So that's really what a state is. It's just a series of code that we're going to run over and over and over again, or process until something triggers us to leave and go somewhere else. So that brings us to what effectively is known as a finite state machine, or FSM, or state machine, however you want to say it. And they're used to design programs, games, logic circuits even run on finite state machines. And really it's just a simple mathematical model of computation used to design some kind of flow and step-like process in a sequential logical order. For example, usually we design them as an abstract machine that doesn't exist, but at the same time they could be something like a bank ATM. It runs on a state machine. You could come up to the bank machine. That's effectively your entry point. Usually the bank machine is not being used at the moment, so it's idle. Okay, it's sitting there, and that's you, the black dot, walking over to the idle state machine. And you put in your stuff, you type some things around, you do something, in this case put in your access card. It now moves to the active state where, oh, you're now a user, I'm verifying that, looks great, and it may do a whole bunch of other things in a mini state machine example. At some point, you're done, you hit done, it goes back to idle, you walk away. Somebody else comes over, they put it in, and the machine's out of money, so it goes into service mode, says, sorry, this machine's out of service. It goes back into idle, the person leaves because they're not going to get any money. So it's a state machine. That's each one, we can draw them out like this, where we have individual states which we label to make sense to the person you're describing it to. And then we also usually label all the transitions in and out. Now the neat thing about state machines is, for example, that active state again is probably going to be doing its own mini internal state machine. Right? So inside that diagram now I could make a diagram just for the active state, which is our active state machine diagram, and it would do things like ask for your PIN code. Once you entered that, it would verify it, then it would go into another state and ask you, what transaction would you like to do? Would you like to take out money, deposit money, just check on the status, and so on. The user would give it more input. It would now move to the state that represents that thing that they chose to do, try to do that, do some more states, and so on and so on. And we could draw that all out as another state machine. So we can have state machines within state machines within state machines and draw them out in nice, simple little diagrams to describe an entire game.
State machine inception.
That's right, stateception. So you could do that, and that would be a nice, easy way to describe a lot of the interactions in your game. For example, you could do it for the player. Everything the player could do, what he could interact with. You could make each a little state machine graph. Or you could make one all-encompassing state machine diagram if you chose, where every state that the game could do, all the enemies could do, are all there and showing you moving in and out of each other. And that would be effectively a way to write out your entire program in a graphical, easy to understand method for other people that are maybe not coders or not developers yet. You need to say to the designers, for example, tell me what your main character is going to do when he gets into this boss fight. Just draw. You could show them how to draw a state machine. They can handle that. They'd be like, oh yeah, okay, so we got a boss, goes into the start mode, he comes out, he gets all angry, plays these cool animations. Then he moves into the throw cans at the player. Then when the player gets too close, he goes into jump up and down and stamp my angry, giant ape monkey feet or something, right? And try to crush the player. And if he gets farther away, start throwing bananas at him, whatever. They could draw all that out, and now you know the exact flow you need to do with the code, writing that all into the AI for that boss fight. So that's really what we can apply these to, and not just characters, but an entire program, which we saw some of the states already for the main loop, and so on, and we're going to look at those. But that's really why we have state machines and what they're useful for. So how do we implement them? Well, one way is you can look up what is known as their software design patterns, like the factory and delegates and so on, and state is one of those software design patterns. You may have, if you've done some university computer science courses and that, they've probably talked about some of these, one of which was known as a state, where you would create classes that really represent each state. Now, generally speaking, people use object-oriented programming practices where a class is an object and so on, but a state is also suitably represented by a class. So we then usually create a manager that knows about each of the states and keeps track of which current state you are in. So we'll have classes for states and a class for our state manager. That's quite common. A more basic and beginner way to sort of approach this is to simply use an enumeration, where you then use a switch case inside your function that just checks what this variable is currently set to, and that's the state I'm in. There's a little bit less overhead in terms of writing object-oriented programming techniques and so on. So that's the approach that we've done here today for this demo. As you've seen, there's a couple of enumerations that tell us the different states of the different state machines that we have in our game. So we're going to use that. It's a little bit more straightforward for beginners, and it still uses all the basic coding techniques to pull it off without any real high-end terminology and abstraction. So that's what we're going to do. The problem with that is it can get rather bulky rather fast. So as the system grows or your game grows, you're going to have large functions like your update or your render function could literally be pages of code at that point, because you've got a switch doing each case of every state in your game, and you might have 50 states, and each one of those figure out what state to call, or have internal states because they have others. It can get very bulky. That's why typically we don't do it this way in the larger AAA games, but it's perfectly suitable for the demonstration purposes, so we'll just break it down as a switch case for now. All right, so our demo implementation, I'm just going to run over the different state machines that we have in this game, and then the different states that they have. So the game's main state machine, we saw this one already, uses that update engine state enumeration to control what the game is doing at any given point. So we have our waiting for resources state, and it's really just lets us know that the game has requested a game object and the rendering object to load resources asynchronously, get everything ready to go. That's really what that one does, and we just know to wait till we're not waiting anymore. The next one is the resources loaded state, and again, the asynchronous loading of resources happens during this, but when it's completed, that's when this state gets triggered. We enter this state. It's effectively just a transient state, which does some cleanup things like maybe displays a loading screen or splash screen and takes you to the next stage of the overall game and state machine. The waiting for press state actually has 3 internal states that use the press result state enumeration, which has load game, play, and continue. So those are the 3 states that we expect from any of our pop-ups, effectively, is what we're doing. So whenever we need to wait for user input because we've shown him a message, we show those 3, or those would be the 3 states that we get thrown into after they've clicked on that pop-up or done whatever to try to continue on. So to either go to load game, play, or continue. The slight differences between them is load game represents the player's ready to start a new game and has acknowledged the status information provided about whatever the previous state was. Play, oops, I hit a button, there we go. Play just tells us that we're now ready to enter an actual level or set up and start playing the game. Pretty self-explanatory by its name. And finally, continue is because you've paused it and you now want to get back to the action. And that's all that state does. So it won't do things like reset the enemy or reset the character, which is what the play function will do. It'll put you sort of into those kinds of startup state modes. From there, the last 4, dynamics is the big one. That's the state that represents when the game is active and currently in play. The other 3 are more responding to something that has happened to the device or to the machine that you're running the game on. So either the window is now too small to represent your playable area because they turned the phone maybe and you can't do that format, or you're on your Windows Store app that's running on their desktop, they've crushed the window or done the snap to like 4 panels, and now they just don't have enough room on whatever resolution of the screen they're running on. We can listen for those and we can react with that too small sort of state. And then suspended and deactivated are, again, because of some interruption or a thread paused it from something else externally, or they've actually closed the window and told it to shut down, that kind of stuff. So those are the main states that the main state machine exists in at any one point in time. Now obviously dynamics, the dynamic state is the one it's going to spend the majority of its time in, because that's where all the gameplay happens. So after that, we also have that overlay system, those pop-up messages. Okay, we've actually built a little state system for them. We want the same background, we want the same positioning, we want the same screen space each time, but the messages that we're going to show are slightly different. What we're going to do after they click out of that is going to be slightly different. Maybe we're going back to the game, or the game is over and now we're going back to a new game or something like that. So we've built a state machine to handle all those differences nice and simply. So we can just say, hey, show the loading overlay. Overlay system, could you please now show my game stats overlay, because they've won the game. We would like to show them his high score. In fact, this game, after you have a high score, when you boot it up the next time, if it was sitting in its nice default fresh restart state, it'll show you the state or your score that you previously had first and then let you start a new game. So it'll just pop up that extra little state step. So that's what this overlay system controls. And again, we have loading, we have game stats, we have a game over, you lost, we have a game over, you won. It says just 2 different things basically. But also they try to save your high score or not. If you lost, there's nothing to save. You lost. So we don't do that. So they are different states. They're not just congratulations, move on. So we do need a difference there. And then starting the game fresh the first time, we have a little greeting. Maybe you want to show how to play the game, something like that. Something I could have included, I just didn't at this moment. Put a simple message in there for the key controls, for example. And then, of course, pausing is your other most common one. So that's all of those ones. Now, after that, we have two other ones. We have the game's input controller, so listening to you doing something on a controller or the keyboard or touchscreen. It has, excuse me, it has three simple states, either none, wait for input, or active. Active, it's actively doing something. And it'll grab all the input, it'll assemble all that together, and push it out. The none state, the controller is just not active, or we're ignoring the player's input for some reason, such as we're loading the game. We don't want him to skip the loading message and try to play when the game's not done yet. So we ignore all input from him until we've finished loading everything, and then we continue on. And then wait for input. The controller is just waiting for the player to acknowledge one of those messages, for example. So he has limited input, not full control. He can't move the character around, but he can click on the screen, push the start button, or push P if you're in the pause mode to get out, that kind of stuff. So that's sort of our limited input one. And that's what I've done with that wait for input, which I just realized I spelt wrong in the slides there. Input. All right, so waiting for input. Then the AI sumo wrestler, which we haven't looked at yet, but he moves around on his own, and he actually is going to have different moves. When we get to the AI section later on today, you'll see the kind of maneuvers and things that he can pull off. He's also going to maybe have some behaviors and get upset at you. So he's going to just keep track of what maneuver he's trying to do across multiple frames of iteration. So he consistently does that move, and then when he finishes, he'll go into some other move that he's allowed to transition into. And this is quite common for most, not only AI systems, but also the player itself, because the player maybe has a sword out, but he's not allowed to go right to a gun shooting mode because he has a sword out. So he's got to put the sword away, which is another state, then he has to draw out whatever gun he wants, and then he goes into shooting mode and aiming mode after that point. So this typical state machine system also exists in characters. So our AI, we're going to have a walk and a dodge and a push state, and we'll look more at that later on. Okay, so those are all the state machines we have in this project. Let's take a look at them and see how the code just sort of transitions through each one, where these are stored again, and that kind of setup. So we've already seen the enumeration for the engine one, but I'll go back to that as well. So here we go. And again, I don't need to show much on the screen at a time. So simple enumeration, okay? Gave it the proper name and wrote them all out. And then down here, here's our press result state one. So load, play, and continue. Same idea there. Here's our game overlay info state system and its states. So loading, stats, lost one, start and pause, and so on. If I were to jump over to the AI just for a second as well, we're going to see the same kind of setup. And I went to the wrong folder. Game objects. There we go. block.h. Oh, actually, that's not where I put it. Game constants. There we go. So game constants. So there we have a maneuver state. So walk, dodge, or push. We'll talk about these behavior ones later on when we get a little bit more fun, fancy things in with the AI. We're going to make it do a couple of extra things there. All right, so that's where they're defined, just enumerations in the classes where we expect to use them. Now, if we go back to starting with the update, all right, we are switching. So we're doing that switch case setup for our state machine in our DirectX app. And we're just checking what state it is, which uses the update engine state. So again, we can either be waiting for resources, the resources are loading, and so on. And that's all there is to it. This update is going to keep being called by the main game loop over and over again, and keeping us in one of these states doing whatever we're doing each time. The controller is going to have its same kind of thing in its update, except for the fact that during its update, we pretty much always want to grab all the inputs. So there's no, you'll see there's no actual switch case in here. instead, internally in the functions, and I'll zoom in a bit, internally in the functions that grab input in our move look controller is where those states are going to be used. So for example, if I just scroll up here, here's setting our active state, so whether or not we are active, well, first we just check if we are and we return true, otherwise we return false. So all of our helper functions are going to be the thing that uses the states to determine what it should say in this class. So it's a little bit different than this setup for how the update system worked. So I just wanted to highlight that. Here again, we're driving off that active flag, but now this is also in the active, we're setting the active, so then it checks if we are active, then we go ahead and we set some things and we turn off the mouse cursor, for example, because we're in that state. So the person is trying to play. They shouldn't see the mouse cursor on screen. So we can null it out by pointing it to a null pointer. And of course, if they're not in that state, if we're not active, then they probably need to click on our little pop-up window. So we should show the cursor again. So we go ahead and we create a basic arrow type cursor from the core cursor class and reassign that back to the Windows pointer cursor. So it's different ways to drive off those states, okay, and configuring what we do with each one. So that class is set up a little bit different than the other one for that. If I go down here, AI sumo block, there we go. We can see this one is a little bit more traditional to the update method. It has a switch case and it just says, hey, what are you trying to do? Are you trying to dodge at the moment? Oh, you are? Okay, here's how you dodge. Are you trying to push? Okay, you are. Here's how you push harder. And otherwise, you're just trying to walk. Go wander around. All right, so that's all we're doing. Nice, simple little switch statement that drives off these cases. And you can see that sometimes, right here, if enough time has gone by, we've decided, you know what, let's get a different maneuver. Let's try something else. This might not be working. The player might be getting wise to what we're trying to do. Let's change our maneuver state. So in this case, I've just simply randomly selected a state and moved on from there. Oh, and again, this is probably a little too small to see. Ah, and it won't let me zoom in. All right, well, we're done with that anyway, so we'll move out.
We'll be coming back to it when we do the AI.
That one we'll come back to in the AI in a minute. So really, that's all there is to the state machine system. And it's pretty basic. They allow you basically just to split up your code into logical chunks, logical components, move from one to the next in sort of a controlled manner and an easy way. And again, allows us to make great diagrams that we can show to people, and we can detail out what we want to happen where. If you need to change code, it's easy for other people that you're working with to go and find that state and go fix the AI. Maybe they don't like how the dodge works, and you guys have a meeting, you work out, instead of dodging this way or that way, he's going to do a little hop and then run and continue to dodge. They can look up the case, they can find where that dodge case is, they search for it in the code where it's being used, and you fill it out. So it allows us to do a lot more of that kind of setup.
Yeah. Well, they're definitely a fundamental of game development, right? You definitely want to leverage state machines in pretty much any game you make, right? Even if it's a very basic game, you still want your playing, your game over, your pause states.
Right.
So it is truly a fundamental of game design.
And that's why building a basic engine like that main game loop again, with those basic game states that you see in every game. They're always going to be loading stuff, and you're going to have to wait for that. You're always maybe going to have an intro sequence. You could make that a state. Right? Every game you pretty much play on a console has all of the intros of every company that touched it and so on and so on. You can make that a state that just plays those movies through until it moves now to the actual, awake state where you're sitting at the menu. That can be a state. You could then go from the state to the gameplay. That's another state, and so on. So if you can break these things down logically, you can build a finite state machine out that allows you to do that. Just every state needs to have a trigger that goes to one or more other states, and that transition needs to be taken care of, and now you're in that state again, and you continue on. But everything should be able to be broken down into these basic state blocks. You should be able to, arrange them out, draw them out logically, and move on. It works for the programs, it works for applications, works for games, works for individual characters in the games, even works for just tracking the status of a gun. A lot of shooter games, for example, will keep track of the ammo clip and so on, but then when you're reloading, it goes into the reloading state that you can't get out of until you're finished, and so on and so on. And then other guns, maybe like a shotgun that's pump loading, you can bail out of the reload state mid-reload and just use whatever's left in it. That can all be driven through a nice little state machine with different transition triggers that let you get in and out of that. But they're basically the same. So you're reusing a lot of the system that you're setting up. You're just changing what allows you to switch states, or what, if you can even switch a state in certain cases.
Yeah. Well, that's a really good overview of what state machines are and why we'd want to use them. And I think we should... welcome back. So yeah, we've covered a lot today. We've talked about getting everything set up and going through all the process of getting all your classes ready for rendering and that. And we've now got some objects showing up on the screen. So it's kind of come to that point where we should probably start letting the user interact with the game, right?
That'd be a good idea. So yeah, what we're going to do is we're going to start with capturing user input for this module. And what we want to do is we want to aggregate input from multiple sources. So I'm going to show you a way to handle and set up a class that can listen for input from your mouse, your keyboard, touch device, the controller, and bring it all together so that the game only responds really to a proper range of input at one point, and not multiple at the same time, because two people are using two different devices for fun, pushing forward to see if they can run twice as fast. And that sounds funny, but I've actually done it in multiple games before, just gone in there and be like, oh, it supports controller and keyboard, what happens if I hold forward on both? You'd be surprised by how many games you can actually do twice as fast movement or do more jumps.
Yeah, some fun inputs by that. Yeah.
So we're going to look at aggregating that all together into one, so that you only get one input at a time coming through, and it ignores other inputs and so on and so on. But still supporting all the different devices that we could be doing. So we'll look at capturing that input and then how to apply that input into the game after that step. All right, so aggregating input from multiple sources. For this demo, we wanted to support all of the available input devices commonly used to play games on Windows 8.1. So that means we have 4 different sources at this point to deal with. So we're going to create a single class that's going to aggregate the input from all of those sources into one meaningful place, which means that we can grab and react to that input from anywhere else in the code much more quickly and efficiently, because it's all being handled by the same class itself. So to further simplify things, we can also have that base class interpret the input data and return it through specialized getters to other classes in that game in different forms if we need to, and that way everything is centralized and still easily accessible. So we wanted to support keyboard input, mouse input, gamepad input, touch input. Those are the 4 that we were going to look at, and of course the first step is creating that single class. So input is delivered in the form of events, basically. So if you've done any other programming in other languages, there's usually event listeners, we call them sometimes, and that kind of stuff. Basically, somebody else is raising an event, you need to listen for it, capture it, and now do something about it. So all device input is passed to your application through events from the Windows core system. All we have to do is register event handlers within our class to listen for and then respond to each of those expected event types that we want to know about in an individual class. So of the 4 input sources that we want to support, the keyboard is the easiest one to work with in the beginning, because really it only has 2 events that we want to listen to: key up, key down, and that's it. 2 basic events. So we're going to take a look first at that and how to grab that input, respond to that input. That's going to be our example, and then from there you can extrapolate how to do the other ones, which are going to be very similar, except for the controller, which we're going to look at separately using X input. So first, during our initialization of the class, you will want to create an event handler, and you can see by the code here on the slide. To do that, in the move look controller initialize, I've pretty much just crushed this function down from what it is in the actual code source into just this part that we care about. It takes in the core window that is dealing with this app, and then it's just going to tell it with the plus equals operator, which has been overwritten, so that we can set up an event handler using that and tell it what we want to listen to. So in this case, we want to listen to the key down and the key up events. and we want to tell it what function we would like it to call within our code base when those events take place. So at the end of this line of code here, you can see that we go along and type event handler. We're going to need to listen to who sent us this message, and we're going to need to know what it is they're trying to tell us. All right, and then we're going to say, okay, on this class that we're in, I would like you to call the onKeyDown function that we haven't written yet, but we will, and the onKeyUp function of this class again whenever you hear these two events coming from that window. And that's it. That's the basic setup for that kind of system. Now you can also unsubscribe from an event by using minus equals instead of the plus equals here. You can use minus equals to unsubscribe from an event later on at any point in time. There are certain cases where you want to do that. For example, maybe you only want to listen to I don't know, mouse input when they're in their submenus or something like that. Other than that, we don't need the mouse, so we don't bother listening to it. You don't want to waste time, listening to mouse events if the person hits the mouse or knocks it, like I've done today already a couple times, because they might change slides on you, and you don't want that to happen. So you could tell the system to stop listening to that input because he's busy talking about this slide, and then go back to it later. So just something I wanted to point out so that people know how to manage which events you're listening to and from at any point in time. You can turn them on, turn them off using plus equals and minus equals in a similar fashion. So you'll probably see that in other setups as well. Now, typically when we're dealing with those event handlers, just remember that you will want to unsubscribe at the end. Now, because we are doing a game, and in this case it's a simple game, we pretty much want to listen the whole time that the game's running, and we never want to stop listening for any of those inputs. So in this case, you won't find anywhere in the code where I've unsubscribed from the events, simply because we never need to in this case, but you may need to in your own setup or game. So now that we're listening for that event or those two events, what does the receiving function need to look like in order to handle the event? Well, all of those event handler functions, for example, in this case, our onKeyDown function that we've created, need to, again, accept who is sending this message, so the core window in this case, a pointer to that, and a pointer to the arguments list or structure, depending on the kind of event that we're dealing with. Now in this case, it's a key event argument structure, but with the mouse it'll be something different, and so on and so on. And touch, for example, or cursor, I believe it's called, those events will have a slightly different structure there. So that one name there as the second parameter, this piece will change depending on what kind of event we are dealing with. So in this case it's a key event, so we're good. And you can see that I'm going to want to know what key we are dealing with. So I've made a variable called key, which is of type virtual key from the Windows System library, or namespace rather. And then now I'm going to grab out of the arguments parameter that got passed in the key that they're telling me about, this event is about. Now it might be a key I care about. It might also be a key I don't care about. Maybe he dropped his Coke on the keyboard and it's rolling across the keyboard punching a bunch of random letters. We don't want to know about that. We only care if they push WASD or P in this game, P for pause and WASD for moving your guy around. So we figure out that the command from the keyboard, we want to see that key if it equals W in this case. And if it does equal W, we're going to set a flag to true that you're moving forward. Okay, and that's it. Now obviously if you look at the code base, this has been expanded so that you can do W, A, S, D, and P for pausing and so on and so on, but that's effectively all that's going to happen on key down. Oh, you've touched this. I'm going to internally in this class set an appropriate flag to true or carry out some other action. In this case, we're only setting something to true. We don't want to actually respond to, oh, W, move the guy. We don't want to do that yet. We want to make sure that we get all of the input from all of the devices and then decide what to do going forward.
Well, that'll stop what you were talking about earlier, right?
It'll help with two things that do the same thing. If I was holding up on the controller and pushing W, you sort of want to be able to mitigate one or the other or both and then move on from there. So for now, it's just setting a flag that will let us know later on when we actually update the controller, and we saw where that was happening previously. In the update loop, it says, controller.update, and that's when it will be, oh, it says I should be moving forward. is true. Now I'll respond with a velocity of a certain amount or something. So the basic process for capturing the player input is to register an event handler and an associated callback. Okay, this is just a recap of the basic process. Then we write the callback to accept the sender and argument parameters and determine what actual key or button or movement or event took place and update our internal state of our movement controller accordingly. And that's really all there is to it. Now, to write that callback function again, we have to accept the core window pointer as the sender and so on. And that's because of the Windows Store integration and then how we're building everything in to the Windows 8.1 environment. So again, that would be one of those things that would be slightly different if you were to do this for Windows 7 and backport to another version to support that and so on that people were asking about earlier. So we've demonstrated the key down process. The key up process is going to be pretty much the same thing. When we let go of a key, it's going to raise another event called the key up event. It's going to now call our on key up event function because we're listening for that event. And then it's going to do something like set that variable, the forward variable, if he was letting go of W, to false, so we know we're not moving forward again anymore. Those kinds of things. And that's really all there is to it. So it's the exact same process we just did for on key down, but now for on key up. And that's pretty much all there is to it. Now, dealing with pointer event arguments and mouse event arguments, pointer being your touch input and cursor sort of finger going around on thing that they called a pointer event argument. Slightly different, but again, it's still the same process. We register to listen for a mouse click or a mouse move, and then we specify what function we'd like them to call when that happens, and handle a specific kind of argument, do whatever we want, done. So it's the same still process, but what's in those event arguments is going to be a little bit different. Now, obviously, there's not going to be key names of what key they pressed because they're moving the mouse or clicking one of the buttons or something like that. It's going to be slightly different where they're touching on the screen and so on. So we're going to have to handle that in a slightly different manner. Now, for controller input, it's a completely different system. So we've covered how to capture 3 of the 4 sources. Let's look at the gamepads as our next one. It's handled in a completely different way. We use a polling system to check for input. So we constantly ask sort of this internal state system of the gamepad, what's your current state? And then we evaluate what we want to do about that. Oh, I notice the A button is held down. I'll do this. Oh, I know you're moving the move stick forward. Let's do that. So we're constantly grabbing from the gamepad an input state to see what we want to do there. So it doesn't use event handlers or callback functions in this case. The other 3 do, this one does not. All right. Instead, we're going to be polling that system, checking for any changes each frame, and then to the end, we're going to basically use that, apply that logic, integrate it in with the rest of those internal states due to events, and then compile it all together and hand out some kind of useful input. So we use the X input API for access to that, to any controllers really attached to the system at any given time, even a dance pad. Okay, if you want to control these sumos with dance pads, you could plug them in, give it a shot.
I think that'd be kind of fun, actually.
Yeah, I can't verify that it will work. I don't own a dance pad, unfortunately, and I couldn't test it. But the X input API will allow you to do all of those kinds of external device kind of setup, and that's really what it was meant for. So it's a neat thing. Maybe somebody wants to try that and let us know how it goes. Later on when you got it. So you can also get battery information, for example, from the device if it has batteries, because it's a wireless controller and they've got the power pack in. So you can warn the user, hey, your battery pack's getting low, and show a little indicator or whatever. All that kind of information is what's in DirectX 11's X input API. So it's a really nice compilation of systems for external gamepad and devices. Get all that control, get that extra input, and figure out what's really going on.
In the system that you kind of set up, even if, say, you wanted to plug in a Connect or something, right, you would be able to do this because you could just take, obviously you have to write the code to handle the Connect events.
Yep.
But you could take this into consideration when you're adding all these states to the end result, right?
Correct. It would be a similar process. You would want to get your data or get your input from it, and then again set internal flags and internal states to deal with whatever that input was, so that when we get to the update function of the controller, it would now evaluate, oh, he's leaning right, I should dodge right. He's leaning left, I should dodge right, whatever it is, you know, he's pushing forward, so let's move the sumo forward. You know, you could do whatever you want there. You'd have to interpret it again. And that's what's nice about this class setup, is that it doesn't matter what device you want to use. They all funnel into this nice same area. We then deal with all of the input together, and we hand out to the game the specific pieces of information it needs whenever it requests what the current velocity of the character is, for example, and so on, so that we know and we can properly render and then update the physics system with it.
Very cool.
Yeah, so that's how that works. So why not take a look at it? Okay, so we're going to take a look at how we go about grabbing these event handlers and the gamepad polling system. We'll take a look at that because, again, it is slightly different. So we're just going to take a look at where that's implemented in the code base so that you can find it easier from what we've been talking about and what we've been referencing. All right, so here is the move look controller's initialize function. And basically, I'm talking to the core window, and I'm saying, okay, when the pointer is pressed, you know, let me know about that by calling on pointer pressed, which is a function that's somewhere else in here that we've written. Okay, and same with pointer moved, pointer released, pointer exited, and so on, all the way down. Those are all of our touch input ones. There's our key down and our key up. Okay, and again, they're all linked now to some internal function in this class that we would like it to call whenever one of those events occur. So you can see there's no difference in listening for key down versus whether or not he's released the pointer or moved it. It's still just an event, and that just calls another function, and that's it. Now, there is a separate handler for mouse-only relative mouse movement events. For example, when the mouse is moved. Okay, so this part is separate from the pointer part. The clicking is still done through the pointer click events. Sorry. And then the mouse moved ones are separate events. So we do have to listen for that one separately because it is different than dragging your finger around on the screen, for example, and that on. So it has its own mouse moved event, which we are going to call on mouse moved function to handle just the mouse cursor being moved around. Of course, they can't see the mouse cursor because we've hidden it on them, so there's nothing distracting flying around on their screen. We've already taken care of that. They're just effectively feel like they're directing their sumo by waving the mouse back and forth and so on. Or in this case, actually, the mouse is bound to the camera.
I was going to say, yeah, it's the camera that's moving in this case. Yeah.
I just wanted to show something different, same kind of application, but being able to, you know, pivot your view around. And another reason why I wanted to put that in there is for, again, beginners. When you're building DirectX, sometimes you've made a mesh and you've hooked up all the buffers and you've got something rendering and you think it's great and you run it and then you can't see anything. Okay, you can't see anything because you accidentally put it behind the camera or the camera's just facing the wrong direction. So I left this controlled to the mouse so that you can move the camera around a little bit. I did constrain it so that you wouldn't accidentally spin the game around and not be able to see. So I did keep it within the, you know, cone of arc of that gameplay area. But you could go ahead and remove those constraints or rejig how the input happens so that you can look around in a full 360-degree, you know, sphere in any direction you want if you choose. But I just wanted to show you how that mouse input can use that camera so you can look around in case you start spawning new objects and you can't see where they are, just to maybe find them off screen or wherever. So that's important to have. I always recommend people have that early on, is to have some kind of camera movement ability, because sometimes it's just hidden off screen and you just don't know it. You think everything's broken, but you're still actually in running order. All right, so after that, this is just resetting the state of the controller, but has nothing to do with the input events itself. So that's initializing them and getting them all set up. And if we go down, I'm just going to scroll by all these. For example, there's one of our pointer pressed functions, and you can see that now it's taking in a pointer event arguments. Different than the keyboard one we talked about, which is also different than the mouse one, and so on. And things inside that, actually, there's things like the current point, so where the pointer is, and you can see that we're using that. We're also checking its ID and position and so on. And we can do a whole bunch of operations just on the touch pointer position and so on. And I've left in, there's also these if-defs that if you want to define move, look, controller, trace, just define it somewhere in your code, then it'll start debug tracing all of the stuff you're doing, your positioning of your finger and your mouse cursor and your button presses. You'll see all that printed out so that you can,
Yeah, when you're tracking bugs, it's always
Yes.
nice to have that kind of stuff.
Yeah,
Definitely.
so I've left that in so you can track what input you think you're sending, and then whether or not the sumo's running the wrong direction, that kind of stuff. So those are in here as well. And again, depending on what state we're in when we're moving the pointer around, we may want to actually move the position of things, and in other times we might want to do nothing. So it depends on these internal move, look, controller states again have come up. When we're waiting for input, we go ahead and we let them move the mouse around and so on. And of course, if we're actually playing the game, then we're more in pointer device touch mode as opposed to the mode up here where we're moving the mouse around. So the pointer is in the move control area, so you have to make sure your finger is in that bottom left corner, that square that we have, so that you are moving it around. If it is in there, then that effectively simulates a D-pad touch event is what I've decided to simulate, and so you are moving the guy around as long as your finger's in that box. However, if your finger is not in that box, then I treat it as if you are effectively playing around with the camera outside that box and so on. So you can also control the camera as well as the character, and just scrolling through all this stuff. That's basically what's going on there. There's our pointer moved. If I keep going down here, that's all the rotations and everything. We have on mouse moved. So this is the similar approach, but now for the mouse. And again, we can see it takes a mouse event arguments. And inside that, there's things like the change in the mouse's position in X and Y. Okay, it's known as mouse delta. Delta represents change. Also why we have delta time often in games, the amount of time that's changed on each frame. Okay, so we have our mouse delta, and we just take out the X and the Y position from that. We're just going to cast that into a float so we can use it a little more easily. We also have some rotation gain on there, which is just scaling the control for sensitivity purposes.
Yeah, so you just the camera just doesn't fly out of the screen.
Or so that you don't have to move your mouse entirely
so far,
across the table, to get it to work. And those are just defined so you can go ahead and change them to whatever you feel is right for your game, or rather even the scale of your game, because some games are larger and you need to manipulate where you're moving a bit more. So that's always nice to have in all games, that kind of mouse scaling ability. And again, we then update our orientation based on the command, so we might change our pitch and yaw of the camera and so on because they've moved their mouse around. We want to limit the pitch. That's where I'm limiting it right there in case anybody wants to remove those limits or play with them just to see that it does work. That's our max and min pitch that we're limiting. And then we're going to keep the longitude in the same range by wrapping it around so that it's within a certain value of pi plus or minus. That's all. Similar reason to why I was doing that for the sumo early on, to make sure he doesn't rotate in the wrong direction after a certain point. This is just to keep pi within a constrained number so it never looks like 5 million. And you're like, how many rotations is that? I don't know. Okay, so it just keeps it in a constrained value that's more human readable. But that's about it for that. On pointer released, I'm just going to skip by that one again. That's when you take your finger off. On pointer exited, and so on. There's our on key down, and here you can see, again, key event arguments, but now we have our W key check, our S, our A, our D, space, X as well, because you can actually fly the guy up and down. Just for trying to find him on the screen, it was in there. You can move the guy around. Of course, it's not great for the game because then he's flying off into space and you can't bump each other and so on.
It's a cheat code.
Yeah, it's like a cheat code effectively. But it's just to show you that, I mean, you can put in anything you want in here besides what we're actually using and then drive code off these variables to do whatever else you want. Okay, so and then there's our pause key, which is P. So on the keyboard we can pause by hitting that and so on, and that'll instruct everything. So key up, like we said, was going to be exactly the same, except now it's going to set everything to false. So again, still a key event args. When we get this, we grab what key we're dealing with, and we just unset the appropriate variable, except for a case in pause, we only actually want to do it on button down. So it's a toggle button, right? So they push it, and it turns on or off, depending on what the state it was. So we handle that one differently by just verifying was it on or off, and then effectively setting it to the opposite thing. But in this case, when we let up, we don't want to do anything. If we are paused, we set a flag saying that pause pressed is true and pause is false, and we can toggle in and out, and that way every 2 button clicks really does what we want as opposed to just letting go of it. Yeah, it wouldn't be a good pause button if you had to hold P on your keyboard and then try to go to the bathroom. That just doesn't work out very well. You have to let go of that button to be able to go anywhere else and do whatever you wanted to do when you pause the game. So we've set it up as a toggle to support that kind of setup. Okay, so that effectively is all of the code for capturing the input. Actually, sorry, I did forget one thing. Let me go to the controller part for this. So, actually, there we go. So we'll go through the update function. The update function gets called by the main update loop, goes in as part of that, and the very first thing we're going to do is check for that pad input because it is different than everything else we do. So if we jump over to that, all right. First, if the controller is not connected, then there isn't much point in doing anything. So we go ahead and we verify whether or not the device is connected, and we check for the controller connection by trying to get its capabilities. So we can use the X input get capabilities method, which will tell us whether or not this gamepad, in this case, does exist, and we did get something back. If we did, we can go ahead and say, yes, there is, in fact, a game controller connected, and we'd like to use it, and currently the start button is not in use, so we're just initializing that state. So if we go down here, of course, at that point, maybe perfectly right between when we detected it was in there, they yanked the cord, and it's now no longer in there. So again, we can check, and if it's not there, we can say, oh, darn, the device is no longer connected, and do something about that. Ask them to put it back.
I've kicked a few cables out in my day, so.
It always happens. You drop something, or somebody runs by the TV or whatever, and, not playing with a wireless controller, you can lose it. So we have that, just sort of that protection in there. Again, we deal with our states. If we're waiting for input, the only thing they can do on the controller is push the start button to make that pop-up window go away. All right, so start allows you to move through the menus. If there is one, it just allows you to accept the message and continue on. That's all we're listening for. So we only do that when we're in the wait for input stage. If we're in the active stage, you're playing the game, or active state, sorry, we're playing the game. Again, the start button is now going to be used to pause the game. So when we're in this state and they push that X input gamepad start, all right, if that is true in this button's bit flag, so we're using a binary operator here to verify that it's true. If it is true, we know he's pushing the start button and we can do something about it. Otherwise, we're going to say that the input start button is not in use and pause pressed is true. So it's the toggle, same idea to toggle the start button. So it's every time you push it, you don't have to push and hold it to pause. That wouldn't be very useful. And that's all that's handling there. From there, we get into how to deal with thumbsticks. And please always, whenever you're dealing with thumbsticks, any kind of analog device like that, always include a dead zone.
Yes, definitely.
Okay, there are games on a couple of other smaller platforms that are hobbyist platforms that I can't mention. I've noticed a lot of the games don't have a dead zone, yet they have a controller to play with. Mm-hmm. So when you do that, you move the guy and then you take your hand off the stick. The guy keeps running very slowly in one direction just because the stick is slightly leaning to the left.
Well, they wear out after use.
And right? There is that too, but it's something that more of the AAA developers understand. Always put a dead zone in, mm-hmm. But it's something that new programmers and people new to game creation might forget to do. So always please include a small dead zone, and I've defined a small dead zone here for it so that the stick has a little bit of toggle room to wear down and not really, if it gets loose, it won't actually make the guy move around. So it's just something I always like to point out to people because it can be easily overlooked. We got to do it in both X and Y direction. And now once we've done that, we go ahead and actually grab the input from the gamepad for that thumb, whether it's left or X or left Y. And we divide it by the full range of the value, which is this here, and that gives us sort of what we're going to do, and we can convert that into a movement command number in some way, depending on, again, what input is useful for you. In this case, just dividing it by X there of the absolute float value of it to get the value I want, subtracting it from whatever is currently in there, and that gives us what we want. And Y, similar setup. And that's all just for the left thumbstick. The right thumbstick, of course, we got to do the same exact thing, but this time it's going to control the pointer change. So we're going to actually manipulate the pointer delta as you move the right thumbstick around, and that'll effectively allow us to control the camera and other things like that. It's going to be a little bit of a different range of values that we're looking for, and that's why I'm doing it that way. Whereas the left stick, really I just want -1 to +1 for which direction we're moving our sumo wrestler and so on. So it's a little bit of a different of input, and again, this is all going to be your custom game, whatever you need.
Will this be something similar to like an acceleration for like a car
Sure.
or something like that?
Yeah, you could do something like that on the stick or whatever. It's just going to maybe give you a curve instead of a straight linear value or something like that. But really the way you get at that value is that part there. What you choose to do with it after that fact is up to you and specific to your game, but that's how you access it from the input state at the beginning that we grabbed. Okay, and that's the same for the majority of the gamepad's options, including that start button and so on as we go through. So all that data has come in. I'm now going to just customize that rotation into the pitch and yaw for the camera and other things like that. Limit it again, just like we did with the mouse. Limit it so that it's within the proper ranges. And that's pretty much it. So that's how we effectively listen for what we care for from the controller. And then that, of course, would jump back out. If I go back once more and continue on with the rest of the update function. So now we've set up all of the stuff according to whatever the gamepad is saying. Now, of course, we can do things like check for any mouse input. So if the mouse is being moved, then we should calculate that same pointer delta that we just saw a second ago from the right stick, but now in terms of because they're moving the mouse. So effectively, it's just going to overwrite whatever. If somebody's using the controller and the mouse, it's just going to overwrite what the controller input was now with the mouse input. And so effectively, only one of them is going to get through. Now, I don't know which one they intend to actually use. All I know is there are two things trying to tell me to move something in some way. So the order in which I've coded them is just the order I picked. But if you wanted to give preference, the thing you want to be the last authority say is the one you put last, right? So if I switch this call to the controller to the end, then it would have priority say.
Or you could do something like a case in here, like
sure,
like to check to see if there's a controller plugged in, take that input. If not, maybe just default to the mouse.
And we've already done that, because inside that we do check, is there a controller? If not, don't do anything.
Yeah, exactly.
But in the case where two are plugged in, I can't tell necessarily which one is the one that should win, unless we had some option to let them choose that. Yes, I would like to only do this. Well, then I would use an if statement and just disable all that. You're right.
Okay.
Exactly. But if you cared about order, you can put them in the order that you want, whereas the least useful one goes first, and the preferential one goes last.
So in our case, we're going to want to put the dance pad last?
That's right. The dance pad would go last. If you're going to put that in there, it might as well be the best one to use. Yeah. So again, we get all that information from the move. We continue on from the mouse, and you can see the mouse is also doing the move commands if we are in that mode versus the trying to click on a menu button and so on. And then here we can see where we're checking those simple Booleans. So if forward is true, well, it could be true because they're pushing W. Okay? If it is, well, then I'm going to overwrite again the move command to be move forward as fast as I can. All right, so now it wins over any of the other ones. So I can push as many of these as I want to make movement command Y all forward, but it won't matter because in the end the keyboard is going to be the one that wins, and that's it. So all those extra inputs just get overwritten each time you try it on a different device, and that's fine. And that just simplifies all the problems we need to worry about. We don't have to worry about any of those problems anymore. They're all gone. Okay? If you're ever pushing two of those same directions on two different input devices, we'll override it and only end up using one of them in the end. So just all those bools, just setting all those values, and then we're making sure that the 45-degree cases aren't faster. We don't want you to be able to say, I want to move forward and to the right, therefore going at 1.707 times your speed in that direction. And obviously you can see I've done that quite a bit because I know what that number is, running on that diagonal, which of course is just a squared plus b squared c squared square rooted, the usual Pythagorean theorem setup. So we're just going to check if any of these cases are beyond the tolerance of pushing in that direction, that we're going to go ahead and we're going to normalize the move command's direction as a vector in that, so that it will only be a length of 1 regardless of what direction. So it's effectively creating a circle of radius 1, and your move vector, your velocity effectively is constrained to 0 to 1 in any direction as a vector's magnitude. That's all that that's doing. So it removes that ability to go faster on a diagonal angle. And that's what that does. And then as we go through here, there's things like sensitivity adjustments, rotating the command to align with our direction. So depending on how you rotate the camera, pushing forward means something different. It's relative to the camera. And that's quite common in a lot of games. You know, shooters, you're looking in one direction with your stick, and then you move or strafe left and right with your other stick, right? It's the same thing I've set up here just to show you how that works, so you have all the math behind it. You can move the camera, and then if you push forward, you'll see the sumo guy no longer runs straight up the mat. He'll now move forward to the camera's rotation and so on, and that's all that that's doing right there. It's setting that up, and then we're doing the sensitivity adjustment for it, and finally at the end we can go ahead and clear the movement command because we've now set all those values into the velocity vector, which is what the game will be accessing from the move controller. It will simply ask, what is the velocity, please? And we will apply that to the player's cube to move in that direction. So in the end, that's all we need, is that m velocity value. All the inputs get crushed right down into that in terms of the player's input.
Very cool. So yeah, that's a good way of doing the input, and we're really getting close to having a game now. We've got everything rendering up on the screen. We're able to move them around. So I don't know, you want to take a 10-minute break? When we come back, we'll talk about how to add physics and handle some collisions.
Sounds good.
Welcome back again. So yeah, we finished with the last module with taking a look at how to handle some input. Now that we got some input, we're probably going to have some objects bumping into one another. So this would probably be a good time to talk about physics and collision.
That's right, physics and collision detection. There's a lot of different ways to do that. Now for this game, it shouldn't be too complex. I mean, there's only a cube and another cube and that cylinder we're standing on. So we'll take a look at how we're going to handle all that. So first up, we're going to plan what we need. That's an important approach. This module is basically broken down into how you should approach doing physics in any game, not just this game, okay? Just the mental process that you want to work through, much like we did in the first module where we approached what we need to build our game, what we want to look at and that kind of stuff. So we're going to plan what we need, then we're going to plan our approach for what we need, and then common pitfalls that people run into, as well as simplifying it down and implementing the actual physics after that. So getting underway, planning what we need. What needs physics in your game? That's the first thing. I mean, you can make a lot of games with no physics whatsoever. Okay, a lot of games don't need any kind of physics. A lot of more AAA mainstream games, though, however, include physics whenever possible because we love watching ragdolls fly all over the place when things explode. So we want them in there as much as possible. At that point, you have to decide, is it a mechanic or is it an effect? Does the physics matter to the player, or is it just for awe and hilarity? Those are the things that you really need to look at because they will determine really how much time you should spend on it, and two, if it's okay to cut that later on if you don't have time to do it, you plan to, you didn't get to it. So you'll want to lay out what needs physics, whether it's an effect or a mechanic, if it's important, and so on. For example, if it was canned, would anyone even notice? Okay.
So by canned, you mean something that, you know, if I hit an object, the object would move the same no matter where I hit it from.
Right, or you broke something and it fell apart in a certain way.
Yeah.
Does it matter if it looks exactly the same every time or something like that? If they only crack 2 crates in your entire game and it's 12 hours long, one's at the first hour in, one's at the last hour in, they're probably not going to notice that the crate broke exactly the same way. So it could just be a canned animation that just plays rather than trying to put physics on a thing that you smash that then interacts with each other and falls down. In fact, the animator can probably make it look better than real than that you're going to be able to implement with your physics, right? So you probably want to take that approach. And that there's a lot of cases where that's more important. Some people just, oh, I need physics on everything. No, you don't. You actually, it probably looks better if you don't have physics on certain things. And that kind of knowing when to do which one, it comes down to experience and what you're going to have time to implement. So it's something to assess and keep in mind while we're doing this. Are collisions part of the physics system or simply triggers that cause physical reactions? This is really just a mindset more than anything. Do we want collision detection to be part of our physics system, or is it just something activated when an event occurs? For example, in a lot of shooter games, when the player finally dies, he plays a ragdoll, falls down on the ground, or then takes the force of the last bullet to wherever it hit and reacts with a ragdoll physics in that way. That's more of a trigger causing a physical effect, as opposed to every time we're actually worried about bullets going through the environment, dropping due to gravity, hitting the guy here, causing some kind of special damage because of the arc and the aim and the angle and all that kind of stuff.
That'd be quite intensive too.
It is much more intensive, and it's a lot harder to do, and that's why we just don't see it in a lot of games right now. I mean, over time though, we're getting more games with bullet drop, but at the same time, bullet drop makes it harder to play. So we'll talk about that in a second, where physics starts to be a detriment to your game as opposed to a benefit. So does your collision system allow for trigger zones and soft bodies, or simply solid or rigid body physics, as we call it? Rigid bodies is something like a table, a desk, a physical object that nobody's ever going to be able to go through. It's not going to ever turn into jelly or anything like that. It's always there. It might get shoved around, but it's always the same shape, same static kind of thing. That's what we usually refer to as rigid body physics. It can't bend. Whereas something like fluid dynamics, pouring water on somebody, or a large gelatinous ball that you can push, or bubbles, right? Those are soft bodies. They morph and they shape and they flex, and that cloth is the large one that's called soft bodies. Most people think of cloth physics because we see that in quite a bit of games. Hair physics would also be sort of like soft body physics, and so on. Those are the two different things. And does our collision system allow for that, or can we only deal with rigid bodies? Or trigger zones. When cars drive on grass, we change the physics. It's sort of a trigger zone because they're in a grassy area versus on the pavement or on ice. We want to trigger a change in physics in those areas. So all of those kinds of things, different touching surfaces, touches, collisions, how an object can flex or form, those are all different pieces and categories of a physics system that you may have to evaluate on each individual basis for each object and figure out which ones you want to incorporate into your system. Obviously, the more you do, the more complex your physics system gets, the harder it is to do, the harder it is to debug, the harder it is to actually make the game react the way you want. So sometimes going overboard and putting all that physics in is actually a huge detriment to your system. So planning your approach is also important. How are we going to implement each object's physics? In some instances, we don't have one overarching physics system. It's not needed. We could get the job done for just worrying about the player's physics separately from the ring or the enemy and so on, and that's totally fine. Power-ups just floating around in the environment that can't be touched by anything other than the player really don't need physics then, because they're just there and they're just going to trigger when the player gets close to them. He looked like he touched them, but really you're just seeing if he was close enough, give it to him. It doesn't need to be a physical contact, okay? So certain things we can do in different ways. Do we want one system to rule them all? Or can we have individual actions combining everything into steering forces for those objects? For example, with bullets, you have gravity. You could include the Coriolis effect, which is the spinning of the earth causing the bullet to drift. Some games have that in extreme sniper shots and so on. But those are all forces acting on that bullet. The initial projection, okay, the spin of the bullet, counteracting any wind, trying to change its direction, plus gravity pulling it down, plus the Coriolis effect of the earth spinning, which really isn't a force on the object, but everything else is turning past your bullet, making it look like really your bullet is curving in a certain direction. Right? All of those forces could be summed together into its final trajectory as it goes, and that would be this sort of individual actions combining into a single steering force. That's another way to approach a lot of physics-like situations. So bringing in an outside physics package is one way to hit this nail on the head. You just pull in another package and bang, you bang it into your engine and everything's good. There's a lot of freeware ones out there that you can use. I don't know if I can mention them, but they are out there. And then there's also a lot of the AAA ones that you have to pay for that can do crazy amounts of things, from fluid dynamics and fire and everything else realistically and crazy like that. So again, should I even use those? Well, for this demo, we chose to write our own physics system, and we're going to see why. Once we had evaluated really what we needed in order to get the job done, there's no point in bringing in one of these external physics packages.
Yeah, the setup and everything that would take the time, it just doesn't benefit us.
Exactly.
Right?
It's going to take more time to integrate the physics package into your engine than it is to do the actual coding of getting two cubes in a cylinder to collide. And there's just no real point to that. So that's why we've decided in this case, I slapped my microphone there, I apologize people, that we decided to code our own just to simplify things rather than do that. Now, the common pitfalls, one, people tend to sometimes not understand physics, and we might overload something. For example, your physics system may just be too realistic. We talked about that. It makes it too hard for people to play. All of those bullet drops plus the Coriolis effect plus wind, works in certain games because those are really like simulators for bullet physics. And that's what we're doing. But in other spray and pray genres of some of the popular games that just came out recently, you don't want bullet drop, you don't want wind, you don't want any of that affecting a person's bullet because they already can't aim and they need to spray as much as possible. So there's too much realism sometimes for the player to understand to be able to use it as a mechanic. So we're going to simplify and abstract things out a lot to make it simpler, easier to understand. You know exactly where that bullet's going and you can get the job done. Sometimes physics systems, too much overhead. Literally, it's just going to take you too long to calculate all of those bullets flying through with all that gravity and so on. You just don't want to have to handle that. Too unpredictable for the player, like I mentioned. Overly complicated implementations. Do you want to have to go through all of those physics and all that just for a nice, bullet simulator? Maybe not. We sometimes use more dimensions than required. I can remember you made a certain toboggan game, correct?
Yes.
And what happened with that one? What was your physics approach for that?
Basically, we just said, you're going downhill. We pretended as if you were on a flat plane, basically, right? Because we found out pretty quick that if we actually tried to do all the physics in that, it was too realistic. We were having a lot of problems where you get launched up into the air constantly and things like that. So we basically, we decided that we should probably just think of it as being on a flat plane and just moving you forward, but then we tilted the camera to give it the appearance that you were going downhill.
So it's an appearance of I'm going down a hill, I'm having fun riding my little toboggan, but in actuality the game has flattened it out. We are only doing two-dimensional physics. You can move left and right, forward and backwards, and that's it. We remove Z completely, or Y in this case completely. We don't need it anymore. It now becomes a 2D game on a flat surface instead of a 3D game where you have to calculate all of those going down a hill at a 45-degree slope or 30-degree slope and so on, and it was just too much.
Yeah, it was too much, and it just, it was giving us undesirable results, really.
Exactly. So that's the example I'm saying here, using too many dimensions that really you only need 2D, not 3D to do that kind of thing. So those are the common pitfalls that people run into while setting up physics systems. So simplifying it down, keep it simple. Okay, the KISS system definitely comes into play here. Common physics practices revolve around keeping things as simple as possible unless your game is truly about realistic physics, like most simulator genre games, flight simulators and that kind of stuff. Otherwise, it can be try to abstract it as much as possible because the user is not going to be able to understand what's going on to use it to his advantage anyways. It can degrade your gameplay. So abiding by that KISS mentality will generally lead to much less headaches, more productive work periods, better game in the end because the user knows what's going on. He can pick up the nuances in the system much faster. For example, many brick-breaking games have unrealistic physics on their paddles. All right, so the angle coming in of the ball to the paddle and ricocheting off, it should be angle in equals angle out, and the ball should go off. But if you look at a lot of those brick breaker games, if I hit the edge, it comes off almost like at a much steeper angle than it should. And they put that in there specifically because if you're in a box and you start doing perfect angle in, angle out, you would end up getting stuck in the exact same pattern every time, and you can't get out.
We actually had that happen to us when we did one. Same thing that was happening. We did the proper calculation thinking, oh, this is a good idea, and then we quickly realized that you're getting stuck in that loop constantly. So
remember that?
Yeah.
What was the name of that one?
Rectangle Destroyer.
Rectangle
yeah,
Destroyer.
Had to dodge some copyrights.
So that's exactly that kind of situation that you're going to look for and be aware of. It can enhance your gameplay by actually having unrealistic physics. Bunny hopping, as my pictures are showing, rocket jumping, okay? Those are classics to some certain games I won't name that make them what they are. There's even classes of characters built around the fact that you can rocket jump, right? And so on and so on. Those are unrealistic physics things that went in, but then people started to exploit as a mechanic, and now they became so popular in the sequel to the game, they enhanced it and actually gave graphical effects to it, and so on, and built it out specifically for you to be able to do that. So those are those situations that, it can happen, but they're still fun, people still loved it. Even though it's an abstraction, it's not perfectly realistic. I don't expect to run around and rocket jump.
It's not a bug, it's a feature.
Yeah, that's right. It's not a bug, it's a feature, and that does happen quite a bit. So those are those kinds of things that can happen when you keep it simple, but at the same time, it's not detracting from your game. So don't feel awkward about reducing your physics down to really just what you need. You don't need to do fully realistic physics every time. In fact, you probably shouldn't the majority of the time. All right, so that brings us to implementing the physics. It takes place during our update stage of the game loop. We saw that I pointed at the update dynamics function when we saw it briefly the one time. That's exactly where it happens. Typically it happens right after the user input is determined. Okay, so it'll be in that stage of your update loop. Implementations also should be frame rate independent, meaning that we want to do our physics in a static stepping manner. Okay, we don't want to do it based on however many frames per second you're pumping. If we do that, when the graphics card lags or something else lags, the physics is going to miss collisions sometimes. You're going to end up going through walls, and you've probably seen that in games where there's those kinds of glitches during very hard framey moments when there's enough smoke grenades or something in the flame, and you end up going through or not getting shot or not hitting the guy you thought you did, and that's because the physics system may be starting to miss those collisions because there's too much time between updates. So this will help to prevent bugs in that system due to frame rate spikes, and we don't simply use the delta time, the change in time between each update. Instead, we're going to have a nice stepwise implementation where we take however long this frame took, maybe it's a second, that'd be a really laggy game, but still, we would then break that second down into smaller physics chunks where we do each step at 2 to 10 milliseconds each and do all of our physics updates, hoping to catch all of the collisions. Now there are other ways to do this, like continuous collision systems that don't fall to that same kind of situation because they check the whole distance it moved as array from all the points and so on. It can pick up different things in different ways, but that's what we're going to do in this, create a fixed loop so we can hopefully catch every single step regardless of your frame rate. So the basics for that are here. We create a fixed update loop for our physics system. In this case, the update dynamics function, if you want to take a look at it. I've effectively crushed it down just to show what we're talking about here again. And we need some kind of timer to know when we started and so on and how much time has elapsed. Once we have that time, we're just going to say, well, the time left is greater than 0. Take a chunk of time, do something with it. Do we have any more time? Do the physics again. Do we have any more time? Do the physics again. Excuse me. So here you can just see that's where effectively your code for all of your physics stuff is going to go down in here, operating based on however much time has gone by, which is our new delta time here, which is just a simple chunk effectively of our overall time that's left. And that's the kind of implementation you're going to look for these fixed update systems. So within that fixed time step, the loop will need to do something like the following. Start, obviously, the loop from the last slides, and then we update the player's position for physics. Might as well move him first. He's the most important, right? So we'll move him first based on any forces such as gravity or the player's input and so on. Then we're going to update all the AI and the NPCs and all those moving objects so that they're in their new position. And we need to include, again, any forces affecting them, such as gravity and so on, plus their own impulses because they're walking or rolling or running or whatever. And then we need to now check for every other object, see if it collides with the player. Okay, so that's going to be a lot of work, depending on your physics system and the number of things and objects you have in your game. So there is going to be a lot of processing happening here. And if a collision does occur, we've detected it in some manner, then we should push the objects apart based on whatever your laws of physics are. Maybe people are made of rubber and they bounce even farther apart than they were. Maybe you just don't allow them to go inside each other, so however much they're overlapping, you move them both back by a certain amount. Maybe the player can push everything around in your world. Okay, he can physically move everything else, but nothing moves him. So when he walks into something, it moves, but he continues to do whatever he wants, and that's fine. It just depends on your laws of physics and what you want to apply. But now you know a collision has happened between this object and the player. Do something about it. After that, we go to our loop where we check all of the other objects against all of the other objects, not the player. And that's even more work. But that way, if the player is pushing something, it might push something else and so on, and they'll spread out and move out of the way as he walks through a garbage heap or something like that. And again, maybe one of those objects can't move, and that should back everything back up because now they can't, and so on. And that's the overall process that you're going to be doing in your physics loop. After that, we can end it. Once we've done enough iterations due to the amount of time we needed, we leave and we continue on. So how do we implement collision detection, and what forces will we apply based on our game's needs? Well, we're going to do discrete collision detection. Okay, so in this method, we're going to check for collisions between the objects each step, and at a lower frame rate or if we have a small fast-moving object, it may end up teleporting past. If we had two spheres, it may end up moving farther in one single step than the width of whatever object it was supposed to run into. So it'll go right past it. We won't detect any kind of collision in that case. So that's what our smaller steps of physics we're trying to do. But at the same time, we have to keep in mind that if we're going to have fast-moving objects, this probably isn't the best way to do that kind of physics. So bullets and things like that are going to need to do raycast or some other approach that's a more of a continuous or a swept check, which is what they're called, to figure out if it hit anything else along the entire path. And that's what these little images are really describing. It's just during a single step, as long as the box can never move faster than half its width, we know it'll always collide with everything. So we can sort of enforce rules if we want to make sure that sumo wrestlers can never move faster than half their bulk in 0.2 milliseconds.
I think we might be okay though.
Okay, we're good. So as long as we can do that, we can ensure that this physics system will work all the time. So we won't ever have the problem where the sumo wrestler totally jumps right through the other sumo wrestler in less than 0.2 milliseconds or so. If you can guarantee me that, then you can do this kind of approach without any concerns, and you won't have any other problems. And that's really just what we're going to look at now. So detecting a cube-on-cube collision. That's what we have, right? That must be what we need. We have two cubes. They're going to collide with each other. How do we do that? Well, if they both happen to be axis-aligned cubes, meaning that all their three faces, their bottom, their right side, and their back side, line up with your x and y and z axis, it's very simple to do. You can do this check right here, which is a really long line of code, and I did have to crush it down to sort of fit it on the width of it. But basically, it just checks the one side's maximum x value versus the minimum x value of the other object, and then the first object's minimum x value versus the maximum, and so on of the other object for y and for z in all those directions. We know that the one object must be somehow inside the other or not. So it's actually very easy as long as they're always aligned to the axes. That's not going to happen in ours.
No, unfortunately not.
No. The sumo wrestlers are going to push each other, they're going to rotate to face each other and keep pushing each other. They're going to be rotating around Y in all different directions. So we can't use this approach. So we have to go a little bit more complex if we're going to do a cube-on-cube collision. Now, other than that little cheat code input stuff, they can't fly. Mm-hmm. So are they ever going to land on each other?
Preferably not.
No, exactly. They're not actually going to land on each other. So instead, we don't need to do a cube on cube. Really, they can have no height whatsoever. It doesn't matter. They're effectively just squares on a mat. Now we only have to do square on square collision. Makes things possibly a little bit simpler. So that's that part I was talking about earlier. Find out what you need to apply physics to stuff, but then simplify it as much as possible. We don't need to be doing cube checks when really the shadow of them on the ground is enough, because they never leave the ground. They can't go over top of each other, so why do we have to check the fact that he has height? Just check where their limits are as a square on the mat. That would be good enough banging into each other. So they're never going to leave the ground. We're not going to consider them as cubes anymore. A simple square projected onto the mat is going to work much better. So that brings us to how do we implement a non-axis aligned square on square collision. At that point, we think to ourselves, are we going to do a whole bunch of work that doesn't need to be done? Is there an even simpler way we could do this before we worry about doing all this? Because again, the calculation is actually pretty large to do this. Is there any other simpler ways?
I think we can come up with one.
Okay, you're right. We can. Because we have made the sumo wrestlers rotate to face each other. Okay? We actually don't even need to use squares. Because they're going to be rotating to face each other, really the distance from the center of them to their outwards edge at any point in time is the maximum distance they're ever going to be apart from each other. So effectively that's just a radius check in a circle, because they're always going to rotate to face each other to push each other away. So we never even really need to worry about the fact that they're squares. In essence, they're a circle, or even more abstract than that, they're a point in space that has a line that you must stay a certain distance away, and that is it. So we can do a simple sphere or distance check that would suffice. So basically to do that, we simply take the radius of the one inner circle, add it to the radius of the other guy's circle, in essence, which is that distance from the center point to their edge. Then we subtract the center point of one circle from the other. That gives us the vector between the two, which we can get the magnitude of and the resultant vector of that, compare that to the sum of the radius, and if one is less than the other, we know that they are within the circular radius of each other or not, based on their center points and that distance. So we just compare the two radii added together to the distance between the center points.
And like you said, it goes right back to you know what your game needs, right?
Yes.
And we were, quickly we figured out that we didn't need to go through all that extraneous calculations just to figure out, where two sumo wrestlers are and if they've collided.
Exactly. So in the end, our planning our 8-bit sumo wrestlers worked out in our favor. It simplifies everything we needed to do. Okay. Now, if you want more in-depth physics or you want to see how to do some of those more complicated stuff, we're going to point you to another demo, the first-person shooter demo that Microsoft has also made that has a lot more is this touching that of different shapes, such as a quad, a face, a cylinder, and a cube, and some other shapes like that for that demo purposes. So you can see how that works. But really, the physics step system will be exactly the same. They'll just be calculating whether or not these two objects are touching inside that pseudocode at the same spot and then dealing with it at that point. So how we set up the physics system is still exactly the same as it is here, but the actual checks that we need to do on whether or not two things are colliding become a little more complex. And so we've abstracted that out of this demo so we don't have to deal with that. We're just going to look at a simplified version of it. So let's jump into the code here now, and we will take a look at that exact setup. Alrighty, so going in here, again, that's not the right class, there we go, in our Sumo DX class, and I'll just zoom in a second as soon as I run down to where I want to be, there we go. All right, so update dynamics. All right, that is the function inside our run game which gets called by the default DirectX App Class that we built. Every frame update, it's going to call run game to let us do a little bit. We update the timer. We position the camera to be looking wherever the controller says we should be. We update the player's velocity based on what the input is from the controller. So again, we've done all that input stuff first. Now we go into physics. And that's this function here. So if I jump down to that, we need to know how much time has elapsed. So we get our delta time from our timer, all right, and when that's our time frame, and that's how much time is left that we want to calculate for physics. So we're starting with all of that time, and we're going to chew away at that each fixed physics update until we have no time left, and then we're going to move on. So while that time left is greater than 0, we're going to go ahead, grab a smidgen of time out of here, and subtract that from the time left, and now use that, whatever that frame length is that I set in the constants file, or class. So we have that set, I think it's 0.2 or something like that, milliseconds. 2 milliseconds, I think is what it is, sorry. And we then update the player's position. That's the first step we said. So we tell the player to change his position to be wherever he is currently, added to whatever the velocity is that we just got from our input controller, multiplied by however much time this physics step is done. Okay, so he may be moving at 5 kilometers an hour, or sorry, I should convert that, or 5 miles an hour, either way, it doesn't matter. And then delta time, we're only moving 2 milliseconds, so we only move a very small step. All right, but that gets added to his original or position, and he is now moved. So we have now moved the player, we've changed his position. Now we're going to do something like determine what the AI is going to do and where he's going to move. We'll look at that in the next module. So once it's decided where it's going and what it's trying to do to push the player out, we go down and we check for any player-enemy collision. Now, the setup to do that, like I said, the first thing we have to do is find the distance in x and z between their 2 center points. So we just quickly do a difference in z and a difference in x by subtracting the 2 from each other. We now know how far away they are in both those directions. And now we want to calculate an overlap of basically the magnitude of that vector. Now, because I've been grabbing it as floats, I just take one float, multiply it by the other, so that's squaring x, and then I add it to the square of z, and now I square root that whole thing. And because the sumos are 1 unit wide, the radius is 0.5 of each sumo to the edge of their face. So I've subtracted 1 because that's the adding the 2 radii together. Rather than write it in, this is effectively an optimization. Why make the computer do it? You probably want to make this a constant though in case you change the sizes or something like that. I've done a bad thing and I've hard-coded that value in, and I will slap myself for it. Oh, there you go. And in the future, I wouldn't do that, but this now is doing our radius versus our distance point difference, and this gives us back the amount those 2 sumos are overlapping. All we have to do now is separate them by that amount. To do that, though, we have to know in which direction they are facing each other. So again, we can just take the vector position of the enemy and subtract our position. That gives us a direction from the player to the enemy that we can now move each of them away in positive and negative direction along that vector by half this overlap. And that's what we do right here. So if overlap is less than 0, because a negative number means there has been a contact, I simply move the player and the enemy backwards or forwards based on our player to enemy direction, depending on who they are, by half the overlap value. Now they both separate by the same amount. So whenever they collide, in whichever order, it doesn't matter who hit who, but they both get shoved back slightly. Okay. I mean, you can think of sumos, they're a little squishy, okay? They ram into each other and they bounce back just a slight little bit every time. That's effectively what we've set up there. So that is really all we needed for our physics, and that's it. And that's the end of that function, in fact. The dynamics is done. What are we missing? What physics didn't we do? They banged into each other, but what about the platform?
Oh yeah, we haven't checked to see if we actually left the platform.
We haven't checked if we left the platform. In fact, there's no gravity. We're not even standing on the platform and so on. No, we don't need any of that part physics-wise. Mm-hmm. Because our platform is effectively a cylinder, it's a circle, it's another radius check. If the guy has gotten a certain distance away, you've left the surface. Why check if you're on the cylinder? I don't need that physics, that physicality. It's abstract. It's not required in this result. So why calculate any of that?
Yeah,
right.
Makes sense.
So instead, if I go back into the code here, we'll see that in our Sumo DX, sorry, I gotta scroll up here. Oh, actually I can jump right back. Whee! right down here in our update function, oh, it didn't jump back to where I thought it would. There it goes. Right there, did either one of them leave the mat? So it's not really a physics check, we're just checking how far away they are from the origin. So is their position, is the magnitude greater than 10? If it is, I know they've left my 10-meter mat. And that's it. So that's all we've done. Same with the enemy. I check if he's gone beyond 10 meters from the center of the origin of the world, which happens to be the center of the mat, because I've arranged all those things being tricky and knowing I don't want to have to do any physics for that. And that's it.
Yeah, a lot less work than having to apply gravity and seeing if they'd fallen a certain percentage or whatever it might be. Yeah.
Yep. But I mean, we might want to add that as a neat little effect. When they have triggered that they've gone too far, start moving them down as if they're actually falling off a giant tower or something like that.
But again, we don't really need to use gravity for that.
No, you just, when this trips, you say, oh, you now have a downwards velocity. We lock out the player input, and the guy just falls. And that's it. There's no real physics needed behind that.
So far today, we've bent times and space. We've created our own physics laws. I think we're doing pretty good here.
That's right. We're on the way. So that's pretty much all there is to it. I guess that's the end for this module. We're going to wrap it up with the next module.
Yeah, so we'll take a quick 10-minute break. We'll come back and we'll talk about AI and
I guess if you have any questions, maybe start thinking about them and forming them. And if we have some time at the end of the next module, we can do a little Q&A.
Yeah, sounds good.
Okay.
Today, we're coming up on our last module here.
Yep, this is it. The big show.
The big show, yeah. It's a fun module though. We're going to be adding some AI, and we're going to be talking about some other extras we can add to the game.
Yeah, we'll discuss them. We'll leave them to you to implement them. Like the 12 sumo wrestling that we talked about earlier. Still want to see that, or the Kinect. Whoever brought up that Kinect question. Now that you know you can, I expect to see those sumos moving around with the Kinect. We'll see how that works out. So yeah, we're going to break this one down into, again, assessing what we need in terms of artificial intelligence, in case you didn't know what AI stood for, and then some common pitfalls that can crop up when you're playing with AI or dealing with AI, the basics of an AI agent and what it is, and then a stepwise implementation in terms of how we set up the one that we did here, and to give you an idea of how maybe you want to build up the one that you're going to make or whatever you want to do for your games. And then tweaking it, and of course just wrapping up today and everything that we've done, give a little brief overview. All right, so assessing what you need, we really start by, again, picking out all of the parts of your game that could benefit from artificial intelligence. So enemies, and then you may have levels of enemies. You may have like bosses versus the normal everyday grunts running around. NPCs, squad mates, critters, civilians, right? There's multiple categories of that for AI. The game's narrator, for example, could even be a possible AI entity in your game. There's a couple of those that have come out recently that I can't mention. And then there's level and map generation. You can use an AI to build levels and build better maps, or respond to the player's way of playing and generate new content ahead. That's also possible. Chat systems can have AI. So certain games now respond to you when you type to the computer. It'll respond in case you forgot it was a computer, and it'll say, good game or whatever, GG. And matchmaking system, we use AI to figure out who you should be matched against sometimes. That can be built into the game to balance different players based on their profiles and their stats and get a team together that seems to play well, and then against another team that's going to give them an equal kind of competitive action that we want. You can do AI in so many different ways, auction systems, everything else. Now, of those, which one are critical? Which ones are nice to have? Which ones really aren't required, but if you have free time and, money, why not spend it putting it into the game? Sure, that'll be fun. For example, do goldfish in a fountain really need a flocking system to avoid the players that are trying to shoot them during a bomb plant? I've seen that in a game. Did it really need to be there? Nah, whatever, maybe not, but then again...
Programmer had some extra time.
Exactly, or, he was up late last night or something. Nobody else was around. Now rank those on how complex and how many states or actions you will need for each of those AI systems, starting, of course, with the ones that are most critical. How long do you think it's going to take you to write whatever complex behaviors you want for the first boss, the second boss, and so on? How many actions does that boss have? Are you building it as a state machine? in which case it's much easier to describe how many states and how many actions and AI shifts that the AI is going to consider to move in and out from different things. For example, Halo, my favorite one, is always explaining the grunts and the elites running around. If you scare a grunt as Master Chief, it'll freak out and run around and get all scared, and then when it finds an elite, it'll sort of nerve up and be like, oh, I'm going to get my butt kicked if I don't get back to fighting. So it'll come back after you and Master Chief. How many of those kinds of interactions, those states, those behaviors are you going to want? If you're building it as a finite state machine, you can easily detail them out so you know exactly how much work you have ahead of you to implement those things. So it's good to get all that stuff written down, get all that implemented, work it out into those steps so you have an idea of how long and how much work is involved. Or if you have multiple programmers that can do AI, how to split that across them to balance the load so everybody can get that job done on time.
Dibs on the goldfish.
Yeah, I knew you were going to take that one. So common pitfalls in AI, usually losing focus of what the point of AI is in a game. Okay, that is by far the most common. Many people will love the idea of being an artificial intelligence programmer. Oh, I want to work on AI. Pretty much everybody that tries to get into the AAA industry as a programmer is like, what would you like to work on? Oh, I'd like to work on AI. I think that'd be great. That's quite common, the job role people want to work, mostly because they've never done it before and they don't understand the horrible, horrible pain that it can cause upon you in late nights of coding. But not knowing that can also mean you have, that glowy eye, starlit look on you. You're going to get all this amazing stuff done, and that's just great. So, but you need to remember what the point of the AI is. The point of it is to be an opponent when we don't have one. Okay, I don't have somebody to play against. It should play against me. Or I don't have somebody to play with. It's my squad mate, my co-op buddy. Fill that role. It should be decent, in that role. When it's an enemy, it should put up a challenge, but not be so good that I'll never ever beat it. That just wouldn't be fun, right? It needs to present the proper amount of challenge to the player, but still be fallible. It needs to make mistakes to give the player an opportunity to capitalize on the AI's mistake, just like you would on a player. He takes a wrong turn, you've got him pinned, you cut him off, and you take him down. You want the AI to make those wrong turns occasionally. You don't want him to always make those wrong turns, then he just looks stupid. That's not good enough either. It's too easy, right? So you want that balance between believability but fallibility brought together, and that's the hard thing with AI, getting that balance. But a lot of people will lose focus on what the AI is. They'll make it too good. They'll make it cheat. They'll have more fun designing it, which is the next point, than anybody will playing it. It's great to love your work. It's great to be, this AI is going to be the most amazing thing ever, and you put all this work and effort into it. But really, you shouldn't have more fun designing it than everybody else in the world should have playing it. That's, it's great that you enjoyed making it, but it still needs to be a good playable thing in the end. Try not to make your AI do certain things that are perceived as cheating. It's okay if it cheats. That's fine. But you don't want it to be perceived as cheating. In some games, in fact, it's not cheating, and people will think it is. They'll be like, oh, he's just cheating. He always knows where I am, or whatever. No, he was just randomly wandering around, and you happen to stumble into him. But because there's enemies everywhere, it feels like they always know where you are, because everywhere you go, there's an enemy, and you're like, crap, he found me again. Crap, this guy found me. Crap, that guy found me. It might be perceived as cheating because of other nuances going on, like they say over the radio, looking for the blah, blah, I think he's over here, blah, blah, and then you run into him. It sounds like they knew where you were, even though they shouldn't have, or something like that, and then the player reads more into it, perceiving it as cheating. So sometimes it's too predictable as well. Humans are great at pattern recognition. That's why we're good with puzzles and we're good with that kind of stuff. Computers are not so good at pattern recognition necessarily. We're getting better at programming them to be, but we don't want them to be too predictable. At the same time, we don't want it to be too smart for its own good, because it will exploit your game. I guarantee you that if you allow it to have all the same player actions as the player, and you leave a bug or some kind of issue in there that allows the player to speed up in a certain way, running in a certain direction, your AI, if it has the capacity to, will realize that's the best way to do it, and he will do so. It will start to exploit all of your games in all of the different ways that a player could because you accidentally wrote those bugs in there or whatever, and the AI will start to do that. Now, that being said, sometimes the AI is the best tester you can hire. If you have a learning AI that actually learns how to play better and put it in, it can show you all of the amazing things that you don't want to happen in your game, and then you can remove them from your game. So AI can be used not only as a thing to play against, it can be used as a tool to help you make a better game, to build levels for you, and so on, to develop your game and roll it out. So there's lots of things that an AI can do, but you have to be careful which ones it's doing, when it's doing them, because that can be a problem as well. Now, one of the simplest forms of AI agents are known as a simple reflex agent. And what we mean by that is effectively each agent will always have one or more sensors to perceive the world. And a reflex agent basically just responds to that sensor immediately, and that's it. Then it looks again, responds, looks again, responds, and that's all it does. It doesn't track history, doesn't remember anything, okay? It doesn't consider the impact of its actions. It just does. It's like, yeah, certain evil villains in Cape Crusader kind of adventures. That's his line. I'm not the man with the plan. I just do. Right? That's this kind of AI agent. They just go out. They do stuff because they see something else happening. Monkey see, monkey do. That kind of situation. And that's going to work out perfectly fine for this game. In fact, it'll work out in many games for the majority of simple AI agents. I see a bomb, I pick it up and I throw it somewhere. I see the player, I chase him down and try to beat on him, and so on and so on. I don't see the player, I stand around. Simple reflexive actions, no depth to them, but for the majority of simple actions, that's all we need, and that's known as a reflex agent. So for our game, that simple reflex agent, going to be suitable enough, it'll work. Currently, the AI can't actually perceive the environment in any fashion. When we look at it, we're going to see that. But what it can sense is it knows where the player is at all times. Now, is that cheating? Well, no. I mean, in a sumo wrestling match, generally speaking, they know where each other are. They can hear you or see you. I mean, it's not that hard to miss a sumo wrestler on a big mat. So that's okay. We're not cheating, right? That shouldn't be perceived as cheating, that the fact that the AI knows where you are, your sumo wrestler is at all times. There's no fog of war in sumo wrestling. So that should work out just fine. So we're going to, it's going to respond to that. It's going to carry out actions based on that sense. Oh, I see you, I see you, I see you, and it's going to try to get you. That's what we want it to do. And that's about it for now. Later on, we're going to have it decide at the beginning of the match how it's feeling. Is it aggressive? Is it a little upset? Is it a little cautious? And we're going to do different strategies based on its emotion, but we'll do that at the end. For now, we just want to, see what where the player is, go for them, and push them out of bounds. So this is where I'm going to talk about the stepwise implementation of our AI. It's a great way to sort of build your AI up, to get it to the point where you want, and to try different things that you might want a sub-faction of your AI to do. Maybe you have, again, in Halo, you have grunts and elites and all that. They all pretty much have guns. They're all walking around. They're all shooting. But some like the grunts are a little weaker, a little shorter, a little faster, so they run around and do more of the flanking. The elites are a little bit bigger. They're not afraid to come up and pound on you and that. You got the guys with the shields that are always trying to take cover with that, but they'll come out in the open because they don't need the cover. They're all more or less the same, but they each have that little bit of different behavior to them just to make things work out that way. So in this case, that's what we're going to do. So stepwise implementation. The first maneuver that we want our sumo AI to do this. We're going to try to have them push the player out of the ring and win the game. And to do that, we've added that class called AI Sumo Block that inherits from the Sumo Block class, and then therefore gaining everything it had. So it has its mesh for where the mesh or where the sumo block should be in the environment, but the world matrix itself is in the Sumo Block class, and all that kind of setup is still there. We give it a new function called determine AI action, in which it calculates the vector towards the player and then takes a step. And that action was called during the update dynamics function. We saw it in there in the last module, and I said we were going to talk about it briefly in this module, and this is that time. So we're going to go look at that determine AI action step, and we're going to see what's going to happen there for this maneuver, the first maneuver being walk. So let's pop over to the code here. And I just got to get to the AI class. So if we jump into our game objects, we'll start with the header first. So in the header, and let me zoom this in there. Ooh, probably a little too far maybe. There we go. All right, so we have this sumo block class. Extends from the sumo block as we stated earlier. We don't worry about this behavior part now. We'll get to that at the end. But we want this determine AI action, and we need to know how much time went by in this update so that we can take the step appropriately based on the physics in the right direction. So it's going to have a maneuver state. Okay, we're going to save it in this choice variable, and that's just whatever maneuver we are going to do at the moment. And again, we're going to have walk, dodge, and push eventually. Right now, we're looking at the push state. So I'm just going to jump back there. And then we need a delay, and this delay is just going to be the amount of time we want to do this action before we decide upon doing something else. So if we jump down to our determine AI action here, oh, and why won't you, there we go. All right, so determine AI action. Again, we're bringing in the time. We're going to take that chunk of time away from our delay before we decide a new action. And as long as, if that delay happens to be less than 0, for example, we're going to make a new choice, decide something else to do. Now, right now, we're not going to worry about this. We're going to just pretend we only have one. So we're not going to worry about how we pick between all of them. And we're going to go down to the choice that we want, which in this case is going to be push. So we need to determine the direction, again, between the player and the sumo AI. So in this case, sumo AI just grabs his position as a vector, and we subtract it from his target's vector position, which is the player, and that gives us that vector facing again in the direction from the enemy to the player. So now that we have that, we really just want the vector. We're going to set it as we're going to get, can't talk now. We're going to get the y value out of that and put it in this direction vector. And what we're going to do is we're going to normalize that value, and we're going to multiply it by delta time. And you can ignore this behavior for now, but it's just going to make this delta time, if it's 2 milliseconds, we're going to take a 2 millisecond step in that direction added to his position. So he's just going to march towards that enemy player. Now, later on, this behavior you can see is going to modify how hard he's going to effectively run in that. We'll see how that works later on. But really, that's all we have to do. So you're pushing, he's going to just find the direction he needs to face and move in that direction. Okay, so, and that's all there is to that part of the AI. All right, so moving on, or sorry, that was the push. I'll flip them around and do the walk in a second. But it doesn't really matter. Right now, they're both just moving in the same direction. You'll see in a minute that the difference between push and walk is really just that variable of how hard to push. So in terms of the next maneuver, we want to choose a circle strafing sort of dodge mechanic. So he's going to try to step aside and try to get out of the player's path in order to turn the tables on him and then shove him out of bounds. So if the AI is getting backed up into a corner, for example, he's almost out of the ring, he can make a sudden movement to one side, try to flip around and push the player back out.
Very tricky.
Yeah, very tricky. So right now, if you were to play it with just the one behavior, he'd literally just run it straight at you and that's it, and you would just grind on each other till one of you knocked each other out and that's it. So this adds a lot more depth to the game right away, and that's why we're adding this behavior, just to get that extra feel and a little bit more difficulty of when that's going to happen. Now, we don't want him always dodging. He's just going to dance around in a circle all day long, and you'll never be able to push him out of bounds. So that's not going to be very useful if he's spinning around like that constantly. So we're going to need to constantly decide when to dodge versus when to push for that AI and go back and forth. And again, that's where that delay comes in with the delta time being tracked and chewed off it. We choose a new choice, which may be dodge or maybe push again, and then keep going every couple of seconds, for example. Now, since the AI can't actually perceive the mat at the moment, we've only told him where the player is, he's not going to be doing this dodge strategically as a way to defend himself because he's almost out of the ring. It's going to be completely random. Now, what do you think? Is that Good, bad? Does it even matter?
It really depends on the situation, but at this point, I think it's it's okay if he's deciding randomly what to do, right? With just these very simple behaviors.
Right. Okay. So right now, Mickey says it's not a problem. We'll go with that. We'll keep that. We'll see what comes of that in a minute. So again, we've added to the enumeration that dodge and so on, and we're just going to jump back into the code to see the second maneuver. Oh, I forgot to escape. There we go. All right, so the second maneuver, which I happen to do first in the switch case, is called dodge. It equates to a value of 1. That'll become important when we get to the behavior part. And again, we need to know the direction between the player and the sumo and the player. So we go ahead and take that. But what we're going to do is we're also going to cross that with the up vector. Okay, so we're going to use xm vector 3 cross for cross product. And when you cross two vectors, you get another vector that's perpendicular to the two. So if you were to just hold your hand in front of you basically and make your index finger and your thumb, okay, like that effectively, the cross product is going to be effectively a third vector giving you that other axis. So what we're dealing with is I'm looking at my opponent, up is this way, and when I do the cross product, I'll effectively get a vector that's perpendicular to my direction to him, and I'll be able to dodge left, or I could dodge right, depending on which way I cross the two vectors. And that's it. So that's how we're figuring out the direction that he should dodge. Probably the most simplest way you can figure that out. Just cross up, which we know is 0, 1, 0 in our world, and we know how to look at our target. So we cross those two, and bang, you can go right or left, no problem, by just using the negative version of that vector or the positive version, and that's it. So back in our code, we take that direction, of course, and we grab the value out, and we normalize it so that we don't end up going faster than we would want. So we normalize it so it's always a length of 1. We multiply it by delta time. We now took a 2 millisecond step in whatever direction that was. And again, behavior is tagged in here, and we'll see why at the end. But that is then summed to our original position. The opponent, or the sumo AI, has now stepped to the left or right to dodge the player. And when he's angry, we're going to do some extra steps down here at the bottom as well. But for now, that's it for dodge. So pretty simple. Nothing too crazy there. And I'm going to pop back over to the slides here for a second and just explain the next one. So the third maneuver in our stepwise implementation is going to be a harder push. I already went over push by accident, but effectively walk is the same as push. In essence, though, the maneuver is simply a copy and paste of that walk job, but we're now going to do 2 times the force, or a variable times the force that we'll see when we get to a behavior. So the side effect of adding this behavior, though, to the AI agent is that it's now less likely to choose dodge, right? Because now we have more behaviors and we're randomly choosing, so he could walk, he could push, he could dodge. So each one has an even 33% chance to happen. So we've effectively now decreased the likelihood that you will dodge, or the opponent will dodge, because we've added yet another behavior. Now that could be good, could be bad. You might want to add some other flexibility.
Well, it modifies the difficulty, right?
Right, it does change things up, and in fact that's going to be the idea of the behavior. We're going to see how we change that up even more. So here we are going to now have walk forward, dodge left and right, and push really hard, so faster than I normally could. That accidentally makes a secondary effect of when he's far away from me, he's pushing really hard, just lets him move twice as fast. So now he has really a move, he has a charge, he has a dodge, and he has push at a certain speed and push really harder. But I haven't given all those states, but to the user it looks like he has multiple states just from the context of what's happening when that guy moves. And that's sort of the neat thing about it, is that you don't necessarily have to build as many actions as the user perceives. You're basically a magician, you're creating illusions of intelligence, you're creating illusions of these actions, and you want the player to perceive what's going on in certain ways. You don't necessarily have to do it, much like the physics. It looks like we're doing cube checks, we're not. We're doing a simple circle check or a radius check, and that is all. It's a perception that is important in AI, not actually what is occurring, at least for games. If you're trying to make an AI to take over the world, then it probably maybe needs some real intelligence. So that's not what we're concerned with here. So the illusion of intelligence is all that we're after, and the player's perception of that AI and what it does is the important part of how smart it thinks it will be. So our third maneuver, jumping back into the code here. And we're just going to pop in, and it's simple enough because effectively we're just going to copy our walk, which I didn't cover, which is set as the default case, just so that if we accidentally roll a bad number or we do something silly, it's going to always do something, which is move forward. But push is effectively exactly the same as you can see here, line for line, word for word, except at the end I have m times behavior. And for what I said just a second ago, we wanted push to be 2 times, so really you would just make it that. And now we have a push that's twice as hard as the normal walk.
You're going to get slapped again for hard coding values.
I know. So we don't want that right now, or we won't want that in a second, so I'm just going to undo that so I don't have to change it again. But that's all there is to the push. So we now have our push, we have our walk, we have our dodge, and we have a decent AI that if we played at that point, he'd be reasonably good at the game. He also throws in enough randomness and a little bit of actions that he can catch the player off guard. There is no apparent pattern. So we can't analyze the AI. We can't decide what he's going to do next. There's no pattern. It's random. So even though it's so simple, that little bit of randomness is nice because it gives it feels like more depth, more intelligence. Now at the same time, the AI is fallible because he can't perceive the mat. He can't perceive that ring. So sometimes when you've got him on the edge, or when he's got you on the edge, he'll be like, I should dodge. And he'll swing out to the side and throw himself off the mat because you'll take advantage of it and keep shoving him to get him out in time. So he can make mistakes. He can, at the same time, he could reverse one on you when you're not paying attention. You run yourself right off the mat when he steps out of the way. So there's still mistakes to be made by the AI, which you can capitalize on. And at the same time, there are opportunities for you to make mistakes that it will capitalize on. And that's really what you're looking for in a good AI opponent. Not one that will always beat you, not one that you can always beat, but one that, has some feel to it, has some life to it, feels like you're playing some...
You've got to have balance.
Yeah, it's got to have some balance there. And that's effectively what we've set up. All right, so let's just pop back over here. For one last section, as we're getting close to the end here. So tweaking it, at this stage, the AI agent, it's a decent opponent for such a simple game. You could ship this. We're good. Balancing the time ranges for changing its maneuvers and the strength of that push become the main balancing factors, right? We have those settings for how hard you want them to push. So where I hard-coded that 2, you could change it to 3 or 4 or whatever to make it feel like he's really ramming the player hard, pushing him right off the mat, or a little bit weaker, or you could change that variably over time if you wanted to put levels in that would make it harder just by adding a little bit more to that value over time. That's a possibility, but those timing on how often it should switch from one maneuver to the next and back and forth, which we'll take a look at in a second, is important as well. What range of values do we want? It needs to stay in one behavior for a certain amount of time so the player knows what's happening. It can't just constantly be like half a second, switch to push, half a second, switch to dodge, half a second, switch to push. It's going to be too fast. The player's not even going to be able to react to what he sees happening to realize what the computer's doing before the computer's already changing what it's doing. And that starts to make it a little too difficult for the player. He feels a little confused. He doesn't know what's going on. You don't want that to happen. So we need the right amount of time, but not too long that it looks like the guy's just doing one thing and only one thing. All right, so the AI agent feels just a little bit shallow still if you play it a couple times through. It It just does those same 3 actions in some kind of random combination, and that's it. We want to give it a little bit more depth across multiple play sessions. Or to use the horribly coined word, we'd like to increase replayability of this game, which doesn't exist, but we'd like to do that by just giving you a different behavior each time you play for the AI to respond. So sometimes he'll do certain actions like dodge. Other times he won't dodge. Other times he won't push really hard. He'll just move a lot because he's angry and he's just determined and he's just going to constantly go for you, never dodge, just keep trying to shove you, slow turtle style and win the race. We're going to do that by giving it a behavior attribute, which is going to decide how we apply each of those maneuvers in each match. And that's why you saw that multiply by behavior and the if statement for the behavior. That's going to be that piece that does that. So let's jump in and we're going to take a look at that randomized behavior demo and the code that's going to control that. And I hit the wrong button. Out. There we go. All right. So again, we have M behavior in this state. We have M behavior in that state. And in the end, we don't have one for the default. So now how is this going to change things? Well, this behavior is just going to be a number. It's going to be a simple value, but it's also an enumeration so that we can read what we want it to do. And if I peek at it, oh, it didn't peek the way I wanted it to. Oh, that's why. I jumped on the wrong one. I'll just go to it. So we're going to have easy mode. You've got to have easy mode. And then we have angry, and we have smart. So smart is a value of 2, angry is a value of 1, easy is a value of 0. Now if we jump back to see what we were trying to do, if this was 0, 0 minus 1, just minus 1, so that's going to effectively change the direction he's dodging in. So he'll always dodge to the left in easy mode, for example. Now if this was smart mode, it would be a 2. 2 minus 1 is 1. So he's always going to dodge to the right. And of course, if this was 1, which is angry mode, 1 minus 1 is 0, so he's never ever going to dodge. In fact, when you do roll dodge, and he's supposed to be dodging, he's no longer going to move because 0 times anything times the direction is 0 added to his position. He stays exactly where he is. He never moves. Okay, so in angry mode, no dodging. That's what we have determined. And in easy mode, dodge to the left. In smart mode, dodge to the right. So each now behavior has its own flavor of dodge. Okay, and that's what we've done. Also, as long as we're not angry, then once we've done dodge, we're done. However, if we are angry, we skip the break. And if you've used switch cases before and you've done a lot of programming, you realize that when we don't break, we fall through into the next case and we do it. So now, instead of just sitting on his butt when he's angry, because that doesn't seem right, he's angry, when he rolls dodge, he's just going to fall through, do nothing, and then end up pushing anyways. And now push. And because behavior is in here in push, and he's angry, that's a value of 1. So he goes ahead and pushes just as hard as he would if he was just walking, and that multiply by 1 wasn't there. However, in smart mode, this behavior is a 2, so now he's pushing 2 times as much. And in easy mode, it's a 0, so now he sits on his butt, and he doesn't have a push maneuver. So he'll only have walk and dodge to the left in easy. In angry mode, he'll never dodge, and he'll pretty much just trudge along in your face all day long, regardless of whether or not he's pushing or walking at that same speed. And finally, in smart mode, he will push twice as hard as he does when he walks, and he will dodge always to the right. So we've now effectively multiplied the different kinds of setups that could happen. All we have to do now is decide which one of these behaviors he's in at the beginning of each match. So much like we decide, here's how we change maneuvers. So again, when this delay runs out, we're just going to say however many states there are in a maneuver, which happens to be 3. So I do a random number, mod it by 3, so it gives me a 0, 1, or 2 answer. That's what state I've decided he's now going to do. Delay, this is where we're changing that range of time before he decides when to choose again. In this case, a minimum of 1 second plus 0 to 2 seconds or 2 point whatever seconds more. Okay, so there's always going to be a minimum of 1 second that the AI is doing one of these actions before it ever changes its mind to try to dodge or try to push or walk after that. All right, so that should give the player that minimum enough time to recognize what it is the AI is doing before the AI decides to try to do something else. And if you don't feel that that's enough, go ahead and just increase that to 2 seconds or 1.5 seconds, something like that. And of course, go ahead and if you want longer actions, you would change that. And that's how we do that part of the random choices that we go about doing things. In terms of when do we set the behavior, we pretty much, by default, when we construct one, set his behavior to easy. But we also, if I grab that, jump through the code quickly, I should be setting it down here in the Sumo DX. There it is. All right. When we create the enemy also, I can hand in what I would like him to be as this third parameter, and I've chosen a random behavior from 0 to 2, so 0, 1, or 2, and that's exactly what our case statement has. So he's going to be easy, angry, or whatever. And one other place we change it, right here, is whenever we load the game. So in other words, whenever a new game starts because you won or you beat him, we go ahead and give him another behavior to set up and to use and to fight you differently. So now when we play the game 3 or 4 or 5 times in a row, he might trick us and do something different that he wasn't doing before, or he acts completely as if he's a different fighter, or now he's mad and he's just trying to push me and that's it. He's never dodging, and so on, with just a couple simple extra lines of code. That's really all we added to that whole setup.
It adds a lot of depth to the game too, right?
That's right.
And replayability, which is always important when you're making a game, right? You want people to come back and play it over and over again.
That's right. So, and that's the overall goal of really that behavior part of the setup. And now my slides are all the way back to the beginning. Yeah, so that's really all there is to the AI. It's simple, it's basic, but it gives enough depth. It gives that play, it does what the AI is meant to do. Okay, it's not too hard, it's not too easy, and all of those things that we talked about earlier on. And really that's what you are looking for when you set up an AI like that. So it does present a challenge to the player, it appears to be intelligent, and at the same time it is fallible. Right? Those are the 3 key points that I always try to get people when they're first going out trying to make their own AI. Those are the 3 things that you want to keep forefront in your mind whenever you're developing something like that. All right, so where do we go from there? Do we leave it just as it is? For this game, I say we leave it just where it is. That's good enough. It's got a good depth. It's got a good range. We're happy with it, and we could go and take it out into the wide world after that. You may not be happy with it. You might want to improve it to the next level of an AI agent known as the model-based reflex agent, where it now, when it goes to do something, it checks, what did I do previously in the past? And if I choose this action, what do I expect to happen? So it starts to have a little bit of a memory and starts to consider the ramifications of its action.
It appears like it's thinking.
It starts to, well, the other one appered as if he was thinking, did it not?
True.
The illusion is there that it was, but it wasn't. And in this case, you might want it to, for example, check a new sensor, such as how far away from the middle of the map am I? If I'm way over here, but the player is on the outside of me, I should consider to keep pushing. However, if he's inside of me towards the inside of the mat, I should dodge, right? Mm-hmm. That's this level of AI. You're starting to get into the point where he's considering what happens if he does an action. So should I dodge because I'm going to get pushed out, or should I continue to push because I'm going to push him out? That's the kind of AI level that you're looking at when you get up to this next step, which is the model-based reflex agent. Yeah.
Very cool.
All right, so from this point, we've put together a big game, basically. We've got some things going on. You've learned the basics of DirectX, and there's that DirectX 11 FPS game project that I kept mentioning. It's a great next step for you from here after you've played around with this project a little more and you've tweaked it, worked with it, understand the concepts of it, compare it to this other project here, and see again what they've done to expand the engine effectively. They've pulled out, obviously, my game code is different than their game code, but the structure is the same. In fact, the camera class is exactly the same, more or less. The move look controller is the same, because I effectively reverse engineered theirs, broke it down into this to make even more simpler stepping stone for you to get into development with DirectX. So this is the next step that you may want to take or look at. Of course, we have the DirectX APIs, which can break down Direct3D, DirectX Math, X Input, for anything we didn't cover that specifically you want or you need for your applications. And there's also another simple tutorial there that takes you from the vertices to the rendering stage, that large module that we had to do that took hours. That is a step-by-step also process if you want to do it in a simpler abstract way without any of our game concepts splitting it up and moving the code all around. I recommend you go look at that third link there. It'll step you through in a direct manner, just a direct single kind of class application that lets you get something on your screen rendering. From there, wrapping it up, what did we cover today? DirectX 11 is obviously a powerful suite of APIs. It has a lot of depth to it. There's lots to learn there, right? But if you can think it up, you can dream it up, this is going to allow you to create that crazy game that you've always imagined and get it out there graphically. Even if it's intensive, it doesn't matter. You can do that with these APIs and bring it all together and build it out as a Windows Store app or desktop app or Xbox One and so on and so on. It works on all the platforms and you can bring it all around. The learning curve is a little steep. Okay, we're trying to break it down as simple as possible. The hardest part is, like I said, that one module where we're pretty much getting something to show up, breaking it down from the vertices all the way through. Once you understand that process, that's pretty much the hardest part really to setting up the entire system. After that, you're just doing the same kind of steps every time to make a different object, different model, render it differently, and then it's just tweaking little things like maybe the shader or the way you optimize the vertices with a triangle strip or list and so on.
The foundation rarely changes, really.
Right. You still have to set up a description for your buffer. You still have to get that buffer over. You still have to fill in the data and so on and so on. Those steps never change, just what it is that you're doing with it. So there is also a poll at the end.
Yeah, so please take time to fill out the poll and give us some feedback and let us know what you thought of the presentation today. It's always nice to know how we've done.
And so we can come back.
Yeah, exactly. Definitely take a chance to fill that out, and I'd like to take a couple of minutes just to thank everybody for spending the day with us. It was really enjoyable for us. I hope it was enjoyable for you, and you learned a lot.
Yeah. I can't wait to see your sumo games starting to appear in the store, so I can test them out. That's fine, Make sure you hit you up with some tweets or something so I know that it's out there. So
please. Yeah, feel free to message me on Twitter and let me know where your games are and where we can find them so we can play them and share them with the rest of our
give you comments.
Friends. Yes, exactly. Yeah, well, so thank you very much for tuning in today. I really appreciate it, and I know Brian feels the same way.
Yeah, so. No, it was a great time. Happy coding.
Yeah.